Okay. Let's go ahead and get started. Thanks, everyone. Really appreciate everyone coming to the 30th annual CSM workshop. I'm Dave Lawrence. I'm the Chief Scientist of CSM. Welcome. Really glad to see so many people here in person online. And so we're going to start this morning with a welcome from Everett Joseph, who can't be here because he's at the Board of Trustees meeting in DC. So he's going to kick us off with an opening welcome. So, Everett, sounds good. Thanks. Thanks.
as facilities. At NSF, there's a specific definition for facilities. NWSC, our research aviation programs, our instruments, but I consider models as well as facilities. And we're going to continue to support our facilities, including our models, because we know that these models, these programs, and your ability to access them. And access is important for us at NCAR. It has always been and it continues to be important. Lead to scientific discovery that have far-reaching benefits for society. These models, these programs, further our ability to understand and advance prediction of, for example, extreme events, and to do so at timescales in a way that really matters to decision making. On a lighter note, this is a special year. This workshop marks a remarkable 30 years of CESM. And that is 30 years of innovation and development that has produced one of the most advanced Earth system modeling programs in the world. That is really a powerful tool for science, but not only a powerful tool for science, but really a powerful tool for social benefit, for society and social benefit. It's really 30 years of discoveries that have increased our understanding of the Earth system to the extent that we are better informed on how to make communities more resilient to high impact events, high impact weather. Also as at the benefit of our economy and just our overall security as a society. And it's also 30 years of community modeling. This community is really rooted in community modeling. Of convening and of building a vibrant international and interdisciplinary community of experts and users. The community that really surrounds CSM, and I've learned to appreciate this in the time that I've been at NCAR, and even before I came to NCAR, the community that surrounds CESM has really been indispensable to its success and scientific achievements. It's also a special meeting because we're also celebrating Warren Washington, NCAR's distinguished scholar, internationally recognized leader in atmospheric and climate science. Warren is a pioneer in Earth system science. He's been dedicated to mentor to countless of students and early career scientists, and is a trailblazer for underrepresented scientists. Warren was a personal friend and certainly a mentor to me. And when I think of him, I think of someone who had a rare combination of what I call grace, wisdom, and courage, and qualities that really enabled him to chart a path for our community, for our science, and for many of us to follow. And it's clear that his legacy lives on in our shared passion for Earth system modeling and for science that really benefits society. He was a real champion for that. There'll be a celebration in Warren's honor tomorrow afternoon, and I'm really sorry I'm missing that. There'll be more information in that, I believe, coming. I also want to thank all the plenary speakers here this week on topics ranging from model development, model assessment, to the development and use of data sets like our large ensembles, like our recent Mesoclip project, to more applied work with far-reaching societal benefits. There are also cross-working group sessions at the workshop this year focused on machine learning, AI, and developing and applying CESM at higher resolution. This is really exciting. This is an evolving direction for us, and really exciting to hear the outcome of those sessions. On the topic of AI machine learning, just a few words on that. I want to share very briefly that The approach we're taking at NCAR is one to scale and apply AI on our work. As you all are aware, the last couple of years, new AI models have proliferated and proven, in many cases, to perform as well or better than our physics-based models, particularly at shorter time scales. These are NWP models, shorter time scale forecasts, and larger scales. Um, these models have achieved this performance using really a tiny fraction of computing resources compared to traditional dynamical and physical models. So at NCAR, when we think of this, we really have a responsibility at NCAR to provide leadership in this space of how we apply AI and machine learning to advance Earth system science, to advance our science. It's really what we do. It's what we're here to do, is to help with the development of innovations and to take those innovations and apply them and be a leader in that space. And to achieve that, we have been doubling down. We've been developing what we call an AI initiative or AI roadmap, which really is an effort for NCAR, again, to provide leadership and capabilities in particular in what we call community AI. And this is, you can think of it conceptually very similar to community modeling and the leadership that we provided in community modeling over the years, which this community is an example of. And our plan is to build an integrated framework of data, of infrastructure, framework of that includes computing resources, software tools, modeling systems, and training. Training is really important with the goal of enabling researchers across domains, doesn't matter what domain you're in, across domains, to effectively harness AI and machine learning in their work to advance their science. And a particular thing we want to do is we want to ensure the reproducibility. Reproducibility is important, scalability, and broad accessibility. Again, accessibility is what we do at NCAR. We democratize science, we democratize access to resources. And so that's important here. And accessibility of AI models for weather and climate, for the weather and climate community. And at NCAR, we don't think that AI means the death of physical models. Far from it. We think that physical models continue to have an important role to play, obviously, especially in sort of, the time scale that this community works on. And it's really integrating physical models with AI. At CGD has really been a trailblazer in this space in Earth system modeling of from seasonal to decadal prediction through, for example, like the LEAP project. I mention this because we will absolutely, I talk about AI, talk about all this stuff, because we will absolutely need your input to move forward in this strategy successfully. So we look out for forthcoming communication on this. And then again, there's some sessions this week that will be on in this area. We look forward to the outcome from the sessions this week to really guide how we develop and proceed in this initiative. So I'll wrap up by saying that the development and research that will be shared this week is significant, has always been significant, and I don't expect anything less. And the impact of that work will continue to even be more significant. This workshop really represents a community that is dedicated to furthering national resilience through partnership. So thanks again. Sorry for not being there, but I wish you an insightful and incredibly productive week, as it always is at a CESM workshop. So thanks again. And Dave, thanks for the time. And I'm turning it back over to you, Dave.
Great. Thank you, Everett. Thank you very much for taking the time out of your busy schedule to come give us these nice remarks. And I want to echo Everett's comments about welcoming everyone and really appreciate everyone being here. Here at NCAR, we work really hard with you to build this tool for everyone to use, and it's a reward every year to see the people who are making use of the model and interesting and impactful applications. So it's really fun, and of course this year marks the 30th anniversary, which is again quite remarkable that this activity is going on for 30 really plus years. So I'm going to start off now with the traditional state of the community or system model project talk, and I'm just going to jump right into it. So, this is the 30th year, and what we've achieved over 30 years, we're going to get to discuss over the course of this week. We have a really fun event tomorrow to kind of review some of the early days of CSM, and also to celebrate Warren Washington, and to hear from all the former chief scientists about their perspectives about their time during development of CSM and when they were leading the activity, and also on their perspectives of the future of our system modeling. So just a reminder on codes of conduct: please be respectful, collaborative, consider different opinions, communicate openly, and be mindful of others. This is still true today, as it always is. If there's any issues, please contact either me or Elizabeth, and in particular, if there's any technical issues, also we have this CSM workshop support alias. We have nursing rooms, all gender restrooms, support for anything you need. So please, especially let Elizabeth know if you need anything during the meeting. A few workshop logistics before we really get started. In addition to all the oral science sessions, we have a really exciting program this year. As always, we're going to do a group photo in the Monday afternoon break in the lobby, so right after the session ends. So working group co-chairs try to keep to time this afternoon so we can get that photo done. There's a poster session and reception this evening. There's a faculty network for teaching. I'll talk about a little bit more Tuesday lunchtime meeting. And then there's a celebration tomorrow afternoon, tomorrow night. There's these cross-working group sessions that Everett already mentioned on AI, ML, and high resolutions. And then on Wednesday at the end, we have this summary session. Last year we tried to solicit questions ahead of time. That didn't really work. So this year we're just going to go with having an open session. So be thinking about questions you want to ask of the leadership of CSM during that afternoon wrap-up session. And we have quiet spaces located around if you need to take a break from the 200 plus people who are here. There's places where you can go. And then I want to also really express my thanks to everyone who's made this possible. The National Science Foundation is providing support, especially helping some early career scientists make it to this meeting. And then really this completely would not be possible without the efforts of Elizabeth Faircloth. This meeting in particular is even more complicated than these already complicated meetings with all the celebration activities that we're having on planning going on tomorrow night, and then also all the funding situations that we're having to deal with as well at the same time. So she has been working incredibly hard over the last 2 to 3 months to get this in place. And then the CG administrative team is also providing a lot of help, and the UCAR multimedia services. So really I want to express my thanks to everyone, and I'm sure I'll do that again during the meeting. Okay, I'm going to start with essentially addressing, a little bit the elephant in the room, which is the funding situation. And as Everett mentioned, we're anticipating we can really expect cuts to NCAR, and really everyone here is experiencing cuts within their own programs. So one of the things we're trying to do to address this is, better characterize the impact and use of the CSM activity so that we can be arguing with whomever was willing to listen to us about the value of CSM, potentially looking for alternative sources of funding if necessary. So please, you should have received this already in your email last week, and we'll send it out again. But please fill in this survey. We're really looking for hopefully to come out of this with a list of the top 10, 15, 20 most impactful science contributions, and then also use of CSM outside of the academic context, so by private industry, by government, by stakeholders. And here's just an example, a nice example that Alice DeVivia sent to me, about how CSM, the large ensemble, is being used coupled with ecology models, ecosystem models, to inform Antarctic conservation initiatives. So working with NGOs to develop assessments of the vulnerability of ecosystems in the Antarctic region. So a great example of the kind of thing we're looking for as we try to make the case for the utility of CSM. And then another slide here that I got from James Dunn, or adapted from James Dunn, about the reinsurance industry, which likes to use Earth system model output, and particularly CSM and the large ensembles to understand risk out at 1 year, especially timeframes, but even going a little bit longer. And they're really interested in the frequency and intensity of weather events, which are material to their losses, right? Directly material. And they really want to know about outliers, tails, and not the mean. That's where large ensembles really come in to understand it. You can't even really look at the observational record and really get a good understanding of those outliers, the big events, and large ensembles are what you can use that. And especially the CSM1 high resolution ensemble has proven to be quite useful. So these are just a couple of examples of kinds of things we'd like to hear about from you. So please share the survey link with your colleagues, especially colleagues from the private sector, NGOs, government institutions, et cetera, who might be using CSM. And then in the same vein of impact, I think education is a big aspect of CSM that sets us a little bit apart from other Earth system modeling efforts. We really spend a lot of our energy on education and not just teaching people how to use CSM, but really teaching people climate science. And we're going to need climate scientists. We're going to need hundreds, maybe thousands of climate scientists to go out into industry and to help companies and businesses and government institutions understand how to deal with climate change. That isn't going to go away. So we're going to need that. So one of the things we're doing is trying to build this network of faculty to get together to help each other, and us to help them, and them to help each other, to be able to bring CSM into the classroom. We're finding quite a bit of interest in the use of CSM in the classroom, and some faculty are already doing this, and so we want to draw on the experiences of existing faculty. So please come on Tuesday lunchtime to hear more about this, or also just keep your eye on our communication channels. Okay, so I'm gonna start today with the science stuff on CSM3. It's been the thing we've been focused on for the last 2, 3, 4 years, and I wish I was up here saying that we have CSM3 ready. So at the 2024 workshop, we were using the term working towards CSM3, a little bit less committing. I want to get us this week to be talking about finalizing CSM3, really moving the terminology. We're already talking about this. John is really encouraging me to push the group to do this. People are working incredibly hard already, but finalizing, we need to get to CSM3 for lots of different reasons. So what is CSM3 going to look like? This is what I showed last year. This has not changed. So the component models have all been upgraded. We have significant updates to all the component models within CSM. The full list of changes is available at this link, and you'll get these slides afterwards. It's also available on the CSM website. And there's 50 plus changes across all the different modeling components. So it's not easy to characterize the 1 or 2 things that are going to be better. It's improved physics, improved capabilities throughout the system. And you really find the details if you go to the working group sessions throughout the remainder of the week. But, and as I'm sure many of you are aware, that our problem child for the last 20 plus years has come back. We had a period last year when everything was looking good. With the lab sea freeze, it was not freezing. We had a series of like 30 or 40 or 50 test simulations where it wasn't freezing. We were feeling pretty good about ourselves and things were making progress. And then we finally got all the component models to really have their final configuration. We put it together, and then the lab sea freeze came back. So it's like embarrassing that this still exists. I will say that this problem is shared by several other modeling centers around the world. This is not just us. Almost every time you talk about it, people say, oh yeah, we've had that problem or whatever. So anyway, it's been our focus for the last 3 or 4 months. It's making it difficult to assess and resolve other issues, and so I'm going to talk a little bit about strategies we've had to move past this so we can be working on those lab sea freeze while also working on other things. And maybe the most concerning thing here is that in this latest run that froze, it was actually 200 plus years in, which is the longest we'd ever seen into an integration where a lab sea froze. We thought that if we got past about 60 to 70 years, we were safe, and then it froze at 200 years. So this is making us, give us a pause, to say the least. And really, I think what it comes down to fundamentally, I mean, there's a lot of potential issues, but it's most likely, fundamentally, there's just too much fresh water coming into the Labrador Sea region. And this is just an sort of evidence of that. This is the East Greenland, Iceland region off the east coast of Greenland, southeast coast of Greenland, and it's the gray curve there is what the MOM model uses for input from runoff from this region, which is observations in quotes, I guess, but it still is more like observations, and then this is what we're getting in a couple of our simulations. So you can see a pretty strong 30-40% too much water coming in. It really has to be coming from precip at some place upstream. So that seems to be fundamentally the problem. There's issues with mixing potentially also in the ocean and other potential sources, but fundamentally there's too much freshwater flux coming into the region, and that's not easy to fix in a coupled or system model. You can't just tune something to make your precipitation go down. So a few things we're doing. One is we just started this activity where we're getting the CGD machine learning group to start exploring whether we can use AI to understand better the signatures of what's happening, because we're putting our eyes on it, a lot of smart brains on it, but the system is complicated, right? It's hard to figure out what we should be focusing on to understand really what's happening, and so we're curious whether or not we can bring AI into this and see if we can identify some signatures that we can't figure out with our brains. So that's one thing that's happening. We do have some relatively good news, and all this is cautious, is that we have some relatively recent runs that are showing quite promising behavior, where we've turned off this Bodner sub-mesoscale mixing scheme just for the Labrador Sea region, something the oceanographers will maybe hold their nose at, but can live with doing that, and it's looking promising. It doesn't look like it's vulnerable to freezing, but of course it remains to be seen. And we're also testing whether the club explicit diffusion can be turned off, which is maybe better way to treat it. Also reduces evaporation fluxes from the oceans, which may also result in lower precip in the Arctic. So we're testing both of those things, and both of those are showing some promise. So it's not all bad. So that's the thing it's been spending a lot of our time on, but of course that's not the only thing that's going on. We've kind of developed 3 high priority biases that we'd like to address. You could look at an infinite number of things in the model, but these are the 3 things we've been sort of spending our time focusing on. Some issues related to ENSO, and I'll go into a little bit more details on here in a minute, especially the El Nino to La Nina transitions. Amazon and Africa precipitation biases, but can really screw up your land carbon cycle if they're wrong, and then excessive Antarctic sea ice. So these are the things that we're sort of thinking that, if we can resolve this Labrador Sea, we'd like to take a stab at trying to resolve these before we finalize. But we may not be able to resolve all of them. That's possible. So this is the problem with El Nino. This is on the left is showing the El Nino autocorrelation. What you see is the observations there in black, and then there's an autocorrelation timescale of about 12 months the transition, kind of representing the transition from an El Nino to a La Nina state. And we had it pretty good in the CSM2 large ensemble, is essentially matching the observations. That's also shown there on the right with CSM2 looking quite good in terms of the transition from El Nino to La Nina. With CSM3, for reasons that we're sort of getting some insight into, isn't really transitioning properly. And this is an older slide from an older simulation, but the problem is showing up in many of our recent simulations as well. So this is important. It has implications for for understanding variability in the system. It also seems to be projecting onto different aspects of the El Nino as well that seem problematic. So we're working on this one quite a bit as well. And one thing we're doing, with that lab sea freeze, it was kind of preventing us for a while from making any progress at all. But then we realized that we could apply this strategy in the ocean that's called salinity restoring in the Labrador Sea region, just the Labrador Sea region, its capability of MOM6, that's enabling us to kind of let the model keep running for long time periods, hundreds of years that you need to evaluate the ENSO problem without freezing. And so that's kind of a nice feature that we realized maybe a little bit later than we wanted to, but nonetheless we're using that now to be able to run longer simulations while we're dealing with trying to resolve the Labrador Sea freeze. We're also trying to set off a set of CSM3 initialized predictions, starting off with focusing on the 97, 98 El Nino, and seeing if we can learn something from having an ensemble of real world El Ninos and see what the transition looks like in that system, and see if it helps us understand things and get to an understanding of what's going on quicker than what we can have with a century scale simulation. So that's another strategy that we've just adopted recently, and hopefully we'll have results on that soon. Another bias that we're trying to deal with is the Amazon and Africa precipitation biases. So up there on the upper left, this is the JJA dry season in the Amazon, at least, period, and it's really, really dry. There's almost no precipitation in the Amazon, and this really kills off our vegetation, leads to pretty warm temperatures. Kind of combination of the high temperatures and the low precipitation tends to kill off the vegetation. It appears to be coupled maybe with a excessive precipitation in the Sahel or the tropical Africa. And Isla Simpson identified, there's a divergence pattern that looks like it's related. What's interesting here is that it only shows up in coupled simulations, or it's much worse in coupled simulations than it is in CAM, AMIP simulations, which does indicate that it's a coupled problem. Maybe it's SST biases in the tropical Atlantic, possibly the tropical Pacific, that are leading to this. So we're seeing some of this in some recent simulations. We're also showing some promise here. And then the other one we've been working on is the Antarctic sea ice is far too extensive, and especially in the winter, in the Antarctic winter. And so what you see there, the greens, the OBS, and the couple of recent simulations are showing quite a bit too much ice. 5 million square kilometers too much ice. And it looks like it's related to maybe some zonal wind, but it's also a coupled problem. It tends to show up, it's much worse in coupled situations, and maybe some combination on the position of the jet along with ocean mixing. So again, something we're trying to explore as a team to try to figure out. So just want to highlight here, we're doing all this as open as possible. So if you're interested at all in tracking or helping out with any of our issues, we have this sort of new process of tracking our bugs and our biases and our simulations in our open CSM dev repository. So these links will be available. These are all hyperlinks here that you can go to, and it's kind of a nice way to see what we're tackling. And if you have any insight, we always are appreciative of hearing any new ideas about how to tackle these problems. But that's not all bad. Some things are looking good too. So other features of the CSM beta simulations, and there's been more analysis in the working group sessions coming up. But one of the things is the global temperature trend. So some of our first simulations, we were a little bit concerned that the temperature trend didn't look right, but it's actually, I think, looking pretty good right now, although it's been a while since we've been able to run a full transient simulation due to lab sea freeze. But this is the observational based estimates at Ensemble called the Descent data set, which is a 200-member ensemble accounting for the uncertainty and observations. And this is what the CSM2 large ensemble looked like. So it looked pretty good. We had that kind of excessive or too rapid warming towards the end of the 20th century due to this issue with biomass burning, aerosols, not smooth biomass burning. Overall looked pretty good. And here was one of the recent CSM simulations. We also haven't done the smoothing, so it does have an acceleration towards the end, which we think will go away once we do the smooth biomass burning. But looking okay, it's within the realm. If you try to break it down over land and ocean separately, these are the time series from the descent observations. What you see is that actually, if you look at separating out between land and ocean, over land, CSM2 wasn't really warming enough over much of the 20th century. It was relatively small warming occurring until pretty late. If you look at the CSM3 beta simulation, it actually looks pretty good, probably potentially even better than the CSM2 simulation looked. And on the ocean side, it looks about the same, pretty good in both simulations. So there's some promise that CSM 3 is looking better in terms of the temperature trends, and maybe it's due to aerosol radiative forcing. Actually, quite a bit weaker estimates of the aerosol radiative forcing in CSM3 at about minus 0.5 compared to minus 1.65 in CSM2. Although that was assessed before we had the new dust emissions, so it has to be revisited. We're also keeping a close eye on the Greenland surface mass balance, and the first simulations that we were looking at were looking pretty bad in terms of the mass balance. So if you look at the red lines here on the right, that's precipitation average over Greenland. Those are from a CSM3 test case. The black line is a quasi-observed data set from this high-resolution model called RACMO, and then the range in the light blue or purple is coming from the CSM2 large ensemble, which we had a decent looking surface mass balance in CSM2. So in the CSM3 test simulations, it was looking pretty bad actually. There was way too much precipitation in the Arctic and way too much melt. The melt was really bad. So looking through it, we really need this reasonable surface mass balance if we want to run interactive ice sheets. So as in CSM2, we adopted this strategy to artificial enhanced subgrid orography along the really sharp gradient coastlines in Greenland, and that reduces the excessive precipitation. So that's the one thing we did. We sort of adopted the same strategy that worked. And then excessive melting seemed to come through a change we made in the snow conductivity scheme, reverted back to the older scheme just over ice sheets, and we're using this new Sturm scheme over land, which is showing good features over the land in terms of the snow densities there. So looks like we've got what looks like is going to be a reasonable surface mass balance. We've been running a few tests now with a fully coupled MT. That's the mid-top configuration that resolves the stratosphere, which is going to be our core default workhorse simulation. And the QBO amplitude is looking good, especially good agreement below 30 hectopascals there on the right. The black is in the observations, and the blue is this coupled test case, so it's looking pretty good. The QBO amplitude looks about right if you look on the figures there in the middle, but the period's a bit too fast, and the westerlies are phases maybe too strong. So we're trying to see whether or not there's some tuning knobs we can do to help make that better. The oceanography group, or ocean model working group, is looking at to see whether or not to turn on the kinetic energy backscatter parameterization, which they've been testing with, and it has some really nice features. These things called the so-called Tsuchiya jets. I don't know how to pronounce it or even really what it means, but not being an oceanographer, but that's these jets here that are occurring at depth in the equatorial region, which were not occurring in POP, and were not occurring in the default MOM6, and are occurring when you turn on this energy backscatter. And so these have some nice features, including better treatment of the oxygen minimum zones, which is, I think, going to lead to better ocean biogeochemistry. So the oceanography group is hoping that this will continue to show good results, good impacts. And then lastly, I just want to kind of return to this issue that we talked about last year, which is trying to address this issue of the high ECS and microphysics in CSM2, and this question of whether or not CSM2 is usable for climate change projection science over the 21st century. And so Margaret Duffy led and submitted a paper with a lot of help from Isla and Christina McCluskey and others, a really nice paper that's now in review at James. We've got their first reviews back, and the key points we learned from that is that CSM2's climate sensitivity is too high, and the simulations are too cold in the ice age climate. So it's raised questions about its skill. But what we're finding is that the changes to the microphysics representation can improve its ice age climate, and it doesn't appear to impact the transient climate response. And that's what you can see on the right there, where both the original and the resolved improved simulations with match the observed ice age are essentially lying on top of each other in terms of the transient climate response, and also within the large ensemble. So we believe that CSM2 is appropriate for studies of historical climate and 21st century warming. There may be cases where you may want to be careful, especially in extreme climates, and we outline that in this paper. And I'll just make one point. We have been testing in CSM3, and CSM3 beta simulations are showing a good ECS of about a lower ECS of about 3.8 degrees Celsius, and it's also passing the LGM test. So that's good news. Hopefully that holds all the way through to the end. And then as we finalize the science configuration and resolve issues, it's a slide I showed last year, but it's the same is true here. We're going to continue, and we are evaluating this broad set of metrics, but we just got to keep in mind CSM2 was and is a really good model. It was matching a lot of observational targets, and so whether or not we're going to be able to beat CSM2 remains a little bit up in the air. We had some things we know are not as good, and some things that are looking better. So we're going to find out about that. But I think it's okay if we don't beat CSM2. That's okay. I think that we're going to have better physics, we're going to have more faith in our model, even if it's not necessarily beating in terms of statistical sense. So really quickly, I want to just go through a few tools and just note that we're working on tools to make your lives all better. We're working on ingesting the CMIP7 forcings, allowing us to make projections out, or historical simulations out to present day. We've got a team working on that. We're testing in the CSM2 Wacom to make sure it doesn't give us some really crazily different results when we move to CSM3. We're trying to do a better job of tracking what we've done as well. So really appreciate especially the team in ACOM here, the chemistry group, who's spending a lot of time working on that. We're working on all our workflows. So a lot of the workflow stuff broke between CSM2 and CSM3 as we moved to machines, as everything moved up to Python. We're redoing everything and trying to make it in a more sustainable way and also more usable by the research community so that you can use all these workflow tools in your own science and make everything easier. I'm not going to go through the details here. We're trying to embed most of it, a lot of it, within this CSM Unified Post-Processing and Diagnostics package called Cupid. So just be aware that we're working hard to make your lives easier, I think, is the main point here. Hopefully we get successful. And on the Cupid side, I don't want to spend too much time on this, so I have time to talk about other things, but we're making a lot of progress on this package to really help you do your science and really enable you to run all the diagnostics that we're used to running here on your own machines. And here's just an example of where you can call at runtime within Cupid and ask for, say, the land model, the ILAM package, which is the land model benchmarking package that we've developed with DOE. You can now call that straight out of Cupid. You don't have to know anything about the package. It just does everything for you. And we're doing as many of these sort of externally developed and internally developed packages all in one place to make it much easier. And you can set it up all at runtime if you want. Okay, and the last thing, we've released this visual case gen in terms of tools. It's a really nice tool that allows you to interactively build a CSM case. It sort of controls what you can and can't turn on. It allows you to, abstract some of the things that you don't really need to know and just focus in on the things you're trying to ask. So it's a really nice tool developed by Alper Atunis and colleagues. Okay, so I just want to have a little bit of word on CSM3 release timing. I'm hesitant to go too far here. I have a scratch in my head here. And we're dealing with a situation with budget cuts and things like that. So that's going to be impacting how we can deliver things. But nonetheless, we really need to finish CSM3 for many reasons. That's to enable new science, to set a new baseline for other activities like CSM MLE, which I'll talk about in a minute, and high resolution configurations and other MIPS. So the CSM working group co-chairs, the SOC and the CAB are going to work towards a plan this week to finalize CSM3. It's going to include some more firm deadlines. I think we're getting to a point where we can do that with some of our more promising recent simulations and really just have to accept that we're not going to be able to resolve all our biases. I'd also like to, while we're finishing this end product here, I want us to be thinking about how to resolve what I'm calling the final mile, or Leo Donner said it's not a mile, it's miles, of the coupled development problem, which is really taking us, it's taken us several years now, again, to try to build a coupled model, even after we have essentially the component models essentially ready. And so one thing, that arose last time is that from CSM2 development, it's a couple early and often. It hasn't really solved all our problems, right? We've tried a couple early and often. We came across the same problems that we had last time. So we thought it was going to help. I wouldn't say that it's actually helped us move faster. So maybe we need new strategies. Maybe emphasize, bring AI ML into this coupled model problem, maybe initialize predictions, et cetera. So just again, we're going to be thinking about that. Okay, and move on to some other CSM activities. I gave this slide last year about the forces that are driving our system model development. I'm not going to read through it all, but it's need for detailed information on what climate change is going to be and how it's going to impact people. Earth system prediction, focus on Earth system prediction across different timescales, high resolution configurations going from standard high resolution all the way up to kilometer scale, machine learning, and all the things that it's doing and totally disrupting the way we're thinking about things, changing computing architectures, and the need for getting things to the global south. So in terms of this, we have this big ensemble now of CSM high resolution simulations, which you've been hearing about for several years now. We're really excited about this. It's really impactful set of simulations. You'll hear more about that throughout the course of this week. These simulations, really useful. And so we really need to produce a CSM3 version, we think. We skipped the CSM2, we ran out of time. We need a CSM3 version of the high resolution, and we're starting to do some work here. So this is some work done by Julio and Ben Stevens and Cecile and Colin Zarzicki to look at a CSM high resolution configuration in CAM7 simulations and just comparing the cyclone tracks from observed in CAM5 compared to CAM7. And what we're seeing is action is shifted towards the west and south with respect to what it was in CAM5. It looks like the recurvature is better, and there's some indication that this is going to be better, result in better impact and landfall statistics. Remains to be seen. The tropical cyclone count was too high in this first set of simulations, although Julio is saying that with some more recent simulations with some different parameter settings, it's looking better. And we're also using this variable resolution configuration to really reduce the cost of these simulations, especially when we're doing these test evaluations and exploring the other sensitivities. So things are looking actually pretty good, even though this isn't the main focus yet. And we're trying to lay the groundwork so we can move quickly towards a CSM3 configuration once we're done with high resolution configuration once we're done. We continue to work on kilometer scale capabilities. It's a joint effort between CSEG, SEMA, earthworks, storm speed, and 3 different labs at least, CGD, CISL, and M cubed. And it's really a cross-lab, cross-institution activity for sure, and we're going to need to continue to rely on help from the community to make this happen. We have been able to start running some diamond simulations. We are behind the game here in terms of what some other modeling centers can do, but we're catching up, I think. And so we've run some Diamond 1 simulations. We're running some Diamond 2 simulations now too, the winter case, and actually uncovered a snow depth bug that's sort of strangely occurring there, but it looks like we've resolved it. And we're putting in an allocation to run a long timescale 1-year simulation soon. So huge thanks to Brian Dobbins, Adam Harrington, and many others across the Earthworks, SEMA, and Storm Speed projects to make this happen. It's been a big effort. We resolved a lot of issues over the course of this effort, and now we have, I think, the basis of a capability which we can move forward with. And this is just one example of what you can do. Adam was looking at some simulations and seeing the first try, when you had just the club shallow convection turned on, the other convection was resolved. It looked very patchy. The deep convection looked very patchy, the image there in the upper right. And when you move to the second simulation where he turned on the club plus the multi-flux plumes, seeing much better looking convection, more realistic spectrum of clouds, improves the transitional cumulus regimes with less patchy work. So, just some indication that with maybe relatively small changes, we can get a better simulation. So thanks to all of them for that work. In terms of Earth system predictability, a priority of NCAR definitely is going to be, I think, a priority going forward, even in a reduced budget situation. We have a couple things to highlight here. A new seasonal prediction hindcast that we've run with a high vertical resolution, where we replaced the CSM2 vertical resolution with CSM3's vertical resolution, but still running in CSM2, done a set of initialized hindcasts, and showing with that new higher vertical resolution quite a bit better skill sort of in the upper troposphere, lower stratosphere, which is kind of interesting to see that improvement there. We're trying to understand this. This land is expected to be a key source of predictability at subseasonal to seasonal timescales, but CSM2 is not really showing that peak in the hypothesized and sort of proven in some cases predictability at weeks 1 to 3 or 4. We're not showing that in CSM2, so we're kind of working to understand why that is. And Meg is leading a team that's working on that. There's going to be a workshop next week about this. We're already finding that maybe if you start to do conditional analysis when you're sort of more in extreme conditions, that there is some predictability even in the CSM system. And then finally, in terms of the new things we're working on, there's working towards this machine learning enhanced version of CSM, CSM3 MLE, we're calling it, which is basically taking Earth observations or high fidelity simulations and using them to develop new machine learning based parameterizations that we can replace specific parameterizations within CSM to more rapidly advance our Earth system modeling capabilities, and also drawing on machine learning based parameter optimization methods to use those observations to make a better model. And so we're making a lot of progress here on both the land and the atmosphere side. We have machine learning estimation tools in place that we're using at least partially in development of CSM3, and we'll fully exploit them for the CSM3 MLE. So thanks to the teams that have been working on that, and you can hear more about this at the machine learning session on Wednesday. In terms of ML-based parameterizations, we have a bunch of candidate parameterizations that are in development across the LEAP and M-squared lines projects that we're considering for inclusion in this MLE, CSM3 MLE. And so just putting the list here, it's spanning all the different components. These are all candidate parameterizations at the moment, but some of these hopefully we'll be able to make it into an MLE. And we've also built in this ability to couple PyTorch or all the machine learning tools, AI tools you have within the Python ecosystem into CSM through FTorch. And so making it easier for the community to do this stuff. And we've also got a team focused together to really try to make this happen, an integration team. Okay, and then just want to conclude for the last few minutes here about a few science highlights. Just try to demonstrate again the scope and the breadth of the CSM activity. I've talked a lot about sort of the core activity of the CSM3 development, but really CSM encompasses so much more than that. And here's just one great example of a high-resolution Whack-A-Mech simulations where they've taken a look at the Hurricane Helene for this quarter degree NE 120 configuration of the WAC-MX. That's really a really expensive simulation as far as I understand. But they're able to show that you can produce hurricane-induced gravity waves that reach the upper atmosphere at approximately 400 kilometers elevation, and the sort of concentric circles you're seeing up in the upper troposphere in the WAC-MX simulation. Winds, that's total electron content on the top, and then the simulated vertical wind on the bottom there. And it's matching up with what you see in the NASA observation. So that's a pretty cool feature. And these gravity waves are generating these small-scale perturbations in the ionosphere, which can impact communications and navigation signals. So this has a real-world impact. The chemistry working group and the ACOM group here have built and are working with a CSM chemistry forecast system to understand, do initialized predictions of atmospheric chemical constituents. And here's just an example showing carbon monoxide from a fire in the Canadian fires from earlier this year, or earlier this month, sorry, just a few days ago. Those big fires were happening in Canada. And so this is a cool feature that's being used fairly broadly by different groups around the world, and they're working on, they have a built-in CSM2, and they're planning to move up to CSM3 and moving to Musica and Musica version 1 to enable like regionally defined capabilities and really get detailed information in particular regions. Another cool application is this CSM applications for mountain glaciers. I think it's the first ESM to include dynamic simulations of mountain glaciers, and we can now use CSM and CTSM for regional glacial hydrological assessments. And on the right here is showing the committed loss for these glaciers in the Bernese Alps. If there's no further climate change, we see dramatic committed losses for the glaciers. So this is another cool capability. And then here's a sort of impact-oriented example. This is work done by Iris de Vries, who is at ETH, I think now at Harvard, if I'm right, looking at whether CSM can simulate record-shattering events. So in this case, an extreme precipitation event, one-day extreme precipitation event. And what you see there on the bottom is observations. We had this really massive event, a shattering record that occurred in 2020 or 2021, I guess. And so can you get those in CSM large ensemble? And what you see didn't have any of those really over the historical record, but then there is a really shattering event that's occurring out, in this case, out in 2070. So really, many standard of deviations away from the norm, and so that's indicating an interesting feature. And if you look at the sort of spatial pattern of the atmospheric dynamics for that event, you see it matches up quite well with what actually happened in 2021, although it's happening out in 2071. So that's just an interesting kind of result. And what she's also finding is that the impacts on the probability of a shattering event, record shattering event, is as likely due to changes in variability as it is to changes in the mean. And what you see there, this is showing the amplitude of the changes in variability. So in the changes in the mean, the probability ratio on the top, and on the bottom, the same thing, probability ratio due to the variability. And so you're actually seeing greater strength coming from the changes in variability than changes in the mean. And then lastly, I just want to highlight this novel emissions-driven CSM 2.1.5 configuration that Peter Lawrence has put together. This set of simulations is our first effort to run emissions-driven simulations for a wide range of ensembles with interactive CO2, but also interactive fire aerosol emissions and interactive BVOCs, and also this new feature in the ocean, coccolithors, which allows you to force the feisty fish model. So a really cool configuration. These simulations are available, to really ask questions about what is the potential impact of interactive CO2, interactive fires under low and high emission scenarios. So that's it. I want to stop there. And I'm not sure I'm going to take questions. I think we ran a little bit over with Everett, and I'm right on time here. So let's just stop there. And I'm not going to take questions because this is also a hard one for people to ask questions of. I've realized that, and also because I want to make sure to give time to our Distinguished Achievement and Graduate Student Award winners, because we really want to recognize them. Please keep your questions and bring them to me personally, or bring them at the end of the week on Wednesday. So okay, I'm going to move on then to our Distinguished Achievement Award. So I'm very excited to actually, oh yeah, well, I had a slide here, but I guess we've already moved on. So I'm excited to announce that Dr. Ping Chang from the Texas A&M University has been selected as a recipient of the 2025 CSM Distinguished Achievement Award in recognition of his exceptional leadership in advancing the high-resolution Earth system modeling with CSM. Dr. Chang led groundbreaking efforts to develop and apply CSM's high-resolution capabilities, particularly through the creation of the International Laboratory for High-Resolution Earth System Prediction, IHESP, now known as the MESA-CLIP project. His work has resulted in the largest ever comprehensive suite of global climate simulations capable of resolving tropical cyclones and ocean mesoscale eddies. The MESA-CLIP simulations are transforming climate research, enabling novel insights into extreme weather events, climate predictability at seasonal indicators, timescales, and long-term climate projections. His work has helped establish CSM as a leader in high-resolution modeling with profound national and international impacts across research, policy, and other stakeholder realms. So please join me in congratulating Dr. Ping Chang on this well-deserved honor.
Thank you so much. Can you hear me?
Yeah, we can hear you. So unfortunately, Ping could not be here in person. He had a previously scheduled trip to, I think, the ECMWF. In the UK, so he's going to give his presentation here remotely. So thank you, Ping. Appreciate all your work, and go ahead and take it away.
Thank you so much, Dave. Good morning, everyone, and greetings from UK Met Office. Actually, I mean the UK Met Office, not ECMWF. But anyway, the first thing I want to say is that how truly surprised and deeply humbled I'm to receive this news that the recipient of the CESM Distinguished Award. I really apologize for not to be able to join you in person, and particularly in this particular 30th anniversary of CESM events. I really hope that you have a great and successful workshop. And second, I want to emphasize that this award is just not for me. Really, it's not for me. It really belongs to the entire project team. And from the very beginning, and this has been a collaborative effort. As many of you know, Dave mentioned already, the project actually began as an international partnership in 2019 and under the IHESP initiative. And it's later evolved into a US-funded MESA-CLIP and IPOX project. So this recognition reflects the dedication and the hard work of every team member. So as you can see from my slides, there are a long list of names here. So unfortunately, I don't have the time to individually acknowledge all the individual contribution, but I want to thank everybody, and really, I feel incredibly fortunate to work with such a committed and a talented team, and to advance high-resolution climate modeling, and to make a meaningful contribution to the CESM community. So thank you again for the tremendous honor, and I think it really meant a great deal to me and to our entire team. So with that, I'd like to just spend a few minutes to highlight some of the key accomplishments we've made over the past 6 years and using the high-resolution CESM. So next slide, please. So first, let me quickly just introduce to you what the high-resolution CESM is. So for those of you don't know this already, and the high-resolution version we're running is actually based on early version of the CESM 1.3, and as described by Mio et al. 2019. And this model was really derived from earlier high-resolution CESM 1.1 version and described by Small et al. In 2014. And the reason we choose this older version of the CESM for primary two reasons. One is the computational cost, because we knew this project is going to demand a lot of computational resources. And we realized that the CSM2 is actually computationally a lot more expensive than the CSM1. And the other main reason is that there's no readily available high-resolution configuration of the CSM2. But on the other hand, the CSM1 already have a high resolution configurations before they tested. So that's the reason why we went with the older version of the CSM1. So in terms of the model configuration, we have atmosphere cam 3.5. We use the SE die core with a 1/4 degree horizontal resolution and 30 vertical level, and the same resolution for the land surface model, CRM 4.0. And for the ocean, we use the 1/10 degree or 10 kilometer horizontal resolution and with 32 vertical level. And we turn off the Jan McWilliam mesoscale 80 parameterization. We also turn off the sub-mesoscale parameterization and overflow parameterization. And then the CIS model is the same resolution as the ocean. And for the coupler, we did backport to the CESM2. And we have ported code to multiple HPC system, including Fonterra at University Supercomputer Center TAC, and also Duran at NCAR. So just give you a sense of the computational speed on 223 CPU processors on the nodes at Duran, and we can run this version of the model 5 simulation years per day, and with the with high frequency output. So that's very efficient. And finally, I just want to mention the cost ratio between the high res and the low res is about 100. So you run 1 year high resolution model, you can run 100 years of low resolution model. So far we have accomplished many sets of simulations. And so on the right side of the panel, this slide, you can see all the simulation has been mostly completed. So the first we completed the high resolution MIP ensemble. And then the majority of the time we spend is actually completing this CMIP DAC simulation, which consists of 650 years pre-industrial control simulation and 3 10-member ensemble simulations, including the historical ensemble, RCP 8.5 and 6.0. And we also performed a single-member simulation of RCP 4.5 and 2.6. And then we complete the 2 climate sensitivity simulations, the 1% CO2, the transient climate sensitivity, and the quadruple CO2 equilibrium climate sensitivity simulation. And so far we completed the 4-member ensemble of AMIP simulation. So that's the entire DAC set we've been working on for the past few years. And then in addition to that, we're also still working on the high resolution decadal prediction a set of simulation, and the results is already published in 2023 by Steve Yeager et al. So in addition to that, since we're using the IC die core, and so we also run as comparable corresponding low resolution sets of simulation, so we can do a apple-to-apple comparison between the high resolution and low resolution. So if you're counting all the simulations I've done so far, so cumulatively we have integrated the model for 6,000 years, and we generated about 7 petabytes of data, so very large data. And finally, I want to emphasize that the data has already been published, and not all the data, but lots of data. Most of the 10-member ensemble data has been published already, and the PI control simulation has been published already. So if you go to our project website down below here, you can actually get access to all the data. Next slide, please. So in the next few minutes, I just want to show you highlight some of the key difference between the high resolution and the low resolution, and to see what the new features we actually can learn from the high resolution model. So this slide just compared the global mean temperature simulated in the high resolution ensembles and the low resolution ensemble. So the red and the orange lines are showing the high resolution simulated the global mean temperature, and the blue and the gray-blue kind of color line showing the low-resolution model. So you can see the high-resolution model agrees much better with the observation. The observation is showing in these shorter lines here. So the red is showing the SST, and the orange is showing the surface air temperature. And the black here is showing the GISTEMP 4.0, the version 4 global mean temperature. And you can see the high-resolution model actually very nicely simulates the observation. The low-resolution, on the other hand, has a obvious cold bias and by about 1.5 degree or so. Next slide, So not only so in general, the high resolution model is actually warmer than the low resolution, but that's not all the case. So if you look the eastern boundary upwelling zones, the high resolution model is actually produce a colder upwelling zones. So in this panel, you can show you can see the comparison of the observed CESM temperature along the eastern boundary current region. So in California, Canaria, Peru, Chile, and Benguela region. The top panel is showing the observation. The middle is showing the high resolution model, and the simulation. The bottom is showing the low resolution model. So you can see the high resolution model is able to capture this narrow cooling tongues along the coast. So it's very nicely simulates the upwelling, the ocean upwelling system, much better than the low resolution model. So this could mean that the high resolution model can have more credibility to project the future ecosystem changes, and potentially important for the future fishery planning and so on. Next slide, please. So the other interesting thing is that if you look the climate sensitivity, so this is the transient climate sensitivity comparisons. It turns out that the high resolution model and the low resolution model has very similar climate sensitivity, and the difference is about 10%. The high resolution model is slightly higher. But on the other hand, if you plot the temperature difference between the high resolution and the low res as a function of location, and then you can see there's some really large differences. Particularly the high resolution model, the climate sensitivity is much higher in the Arctic region, implying that the high resolution model actually has a stronger Arctic amplification. But on the other hand, the high resolution model also showing a much lower climate sensitivity in the southern ocean, in the southern hemisphere. And so that's also very interesting. And so we had a paper published last year and showing that one of the reasons the high resolution model have a stronger Arctic amplification is through the Bering Strait ocean heat transport. So it turns out that in the high resolution model, the model resolved the Bering Strait transport is much better than the low resolution model. And in high resolution model, there are a lot more ocean heat transport from the Pacific into the Arctic Ocean, which causes a rapid sea ice melting and give you a much faster warming in the Arctic region. So that's very interesting results. So next slide, please. So that relates to the Southern Ocean. The low sensitivity in the Southern Ocean is also reflected to some extent in the cooling trend simulation of the model. So here I'm showing you the trend of the SSTs over the last 4 decades, from 1980 to 2022, and the top panel is showing the observation. So the ERSST, the SST cooling trends, you can see in the Southern Ocean and in the tropical South Pacific, and then that corresponds to sea level pressure trends. See this very strong, the pressure gradients in the southern hemisphere, and then the trends in the westerly winds in the Southern Ocean. And if you look at the low resolution model in the bottom, and the low resolution model shows almost no trend at all. in SST, no cooling trends in SST. Everywhere you look is the warming trends. And the sea level pressure trends and the wind, the westerly wind trend is also much weaker compared to the observation. But if you look the high resolution model simulation, now we start to seeing the cooling trends in both the Southern Ocean and in the South Tropical Pacific. And we also see a much stronger the trends in the sea level pressure and winds. So next slide. So if you plot the ensemble spread, compare the ensemble of those low res and high resolution model here, choosing two boxes. One is in the South Tropical Pacific, and the other one is the zonal average of the Southern Ocean, showing the bottom here. And you see this, the blue dots represents the ensemble spread of the high resolution model, and the low resolution model from the same model, right, is showing in the green. We did a 10-member ensemble of the same model at 1 degree resolution. And then the purple dots showing the large ensemble, CESM large ensemble. So you can see none of the low resolution ensemble capture any of the cooling trend. None of the ensemble member actually is able to simulate the cooling trends. And but the high resolution model, at least 3 of the high resolution ensemble actually showing the cooling trends, right? So the red line here is showing the observation. So you can see that the observation is the ensemble spread of the high resolution seem to be able to encompass the observation nicely. So next slide. So this improvements in the Southern Ocean cooling trends also translate to the improvements of the decadal prediction scale. And this is the paper published by Steve Younger in 2023. Steve essentially shows that if you compare the anomaly correlation coefficients of the high resolution decadal prediction and the low resolution decadal prediction, and look in the difference, which is showing on the right panel, upper right panel here, you see that the Southern Ocean is showing a much greater improvements. And the bottom panel here just showing the time series averaged in these boxes here. And you can see the top panel or the top row here is showing the low resolution, and the bottom row here is showing the high resolution. And you can see that the low resolution in many of these regions showing this spurious warming trends, where the high resolution model does not have this the warming trends, unrelated warming trends, and therefore give you a better scale in prediction. And in this paper, and Steve also argues that the high resolution model actually increased the signal to noise ratio significantly compared to the low resolution model. So next slide, please. So finally, I just want to show you some of the results for the extreme precipitation, and this is still work in progress. So what we show is that the high resolution model is capable of simulating extreme precipitation much better than the low resolution model. Here we're comparing the extreme precipitation trends in the the extreme precipitation, not the trend, the total extreme precipitation measured by the annual maximum daily precipitation using the Hadley-centered data. And in the middle, showing the high-resolution 10-member ensemble, and the right is showing the low-resolution 10-member ensemble. And you can see the high-resolution model reproduce the amplitude of the extreme precipitation much better. Right? And in the bottom panel, we're showing the difference between the high-resolution and the low-resolution simulation, showing the panel A here. And the panel B is showing the contribution from the resolved precipitation. And panel C in the bottom is showing the contribution from parameterized contribution. And you can see almost all the contribution in the high-resolution model, improvements in the high-resolution model, is coming from the resolved component. In fact, the parameterized component is actually doing the opposite. Next, please. So it turns out one of the reasons the high-resolution model is actually better simulating the extreme precipitation is its ability to simulating mesoscale convective systems. So this is the result using the MOAP tracking algorithm developed by Andrea Prey. And so we save the hourly output of the high resolution model, and then apply this tracker, the MOAP tracker, to the simulated data, and then compare to the observation. And so the top left is showing the observation. This is MCS occurrence frequency measured by days per year. And the middle is showing the high resolution model results. And the right panel is showing the low resolution model. As you can see, the low resolution model, notice the color scale has changed, reduced by a factor of 50. So the low resolution model essentially does not have any MCSs, right? And the bottom panel is showing the phenomenon most frequently occur during the extreme precipitation. And you can see in many parts of the world, the MCSs is really accompanied with the extreme precipitation. And this orange color indicates the MCSs. So you can see that the high resolution model is able to capture this feature very nicely. And the low resolution model essentially has no MCSs. So most of the extreme precipitation in the low resolution model are accompanied by jets and fronts. So it's a very different physical phenomenon, or the mechanism. Next slide, please. So finally, because we are able, the high resolution model is able to simulate extreme precipitation and MCSs better. So we can look in the future projection and look at the comparison of the low resolution model projection and the high resolution model projection. And you can see that the increase in the extreme precipitation projected by the high resolution model is significantly higher than the low resolution model. And one of the reasons for the much higher increase in the extreme precipitation, the high resolution model, is really due to the changes in the MCSs. So it turns out that under the future warm climate, we'll actually see a shift in the PDFs of the MCSs. So there's going to be more stronger MCSs, more the number of stronger MCSs occurring in the future. So the low resolution model missing these features altogether, and we speculate that's one of the reasons why the low resolution model projects a much lower increase in the extreme precipitation. So next slide, please. So just a few takeaways, and we have developed the first high resolution CMIP DAC ensemble and released that to the public. So we have done a long pre-industrial simulation, historical and future scenario simulation, as well as the decadal prediction simulations. And we found that the high resolution model offers substantial benefits. It reduces the climate biases, and it improves the prediction scale and signal to noise ratio, and is able to produce a more accurate simulation of extreme precipitation. And so we believe the high resolution model is a more reliable tool for the future projection, climate projection and prediction. So the other thing I want to point out is that even though at this resolution the model is not resolving convection and mesoscale, sub-mesoscale ocean features, but the high resolution model is able to improve the simulation of many of the mesoscale phenomenon, such as MCSs and the mesoscale ocean eddies, and the interaction between the ocean atmosphere and mesoscale. And finally, I want to point out that I think these advances open the new frontiers for research and technology in the future, including machine learning, machine learning-based model, and some of the novel diagnostics for understanding explicit and parameterized physics in climate modeling. So with that, I end, and be happy to answer any questions. Thank you.
Thank you, Ping. Excellent presentation. Do we have any questions for Ping? We can take one or two. Yep.
Thank you. Thanks for a nice talk. So I was just interested in asking you about the Southern Ocean sea surface temperature. Specifically, have you seen what we say, the signal to noise ratio in sea surface temperature in the Southern Ocean? Because I've seen there was a bit of a warm patch near the Antarctic Peninsula. So would really like to ask you about that. Thanks.
Yes, I think Steve has looked into the signal to noise ratios in detail. I think Steve is probably attending the workshop. Perhaps you can talk to Steve in more detail and to learn his analysis. And in his paper in 2023, he showed a metric and showing the enhanced signal to noise ratio. I'm not sure if the signal noise ratio is particularly analyzed for the Southern Ocean, but overall there is an increased signal to noise ratio in a high resolution model compared to the low resolution model.
Thank you so much. Thanks.
Great. Another question or? Okay. Yeah, Isla.
Also had a question about the Southern Ocean temperature trends. I hadn't really appreciated how much more variable the high res was, and it seems like maybe almost there's some members that look like the low res and then another set of members that are doing something different. Have you looked into why there's so much more variability?
Yeah, I mean that's absolutely true. There's quite a bit of ensemble spread, and but some of the ensemble member. I think one of the ensemble members looks very, very similar to the observations if you look at the spatial structure, and others are very different. So, yeah, I mean, this is definitely a problem we're still working on. And but in the end, I still think it's the cooling trend is primarily a forced response, and it's not internal. But we're still working on that.
Great. Yeah, one more.
Looking at the improvements in the eastern boundary upwelling and the improvements in the subtropical highs and subpolar lows, it seems like I'm just wondering if there's any relationship between that, if there's some feedback on where that cold zone in the ocean is, and if that's feeding back to improvements in those trends in the subtropical highs. Thanks.
Yeah, that's a great question. I mean, the upwelling, the improvements of upwelling, we wrote a paper about that. We think it's really related to the improvements in the coastal winds. The high resolution model actually gets a much better coastal, not only the strength of the winds, but also the structure of the winds, which actually contributing to the wind stress curl along the coast. So it turns out that curl, I think Justin Small had some paper examine this question, that it turns out that wind stress curl is actually very important to drive the upwelling. So one of the reasons is that. Now, in terms of the sea level pressure, I do believe there's an inference of the improved SST on the sea level pressure pattern. Yeah, but we have not looked into in very details for this problem.
Thanks.
All right, thank you, Ping. Appreciate it. Great talk, and obviously a lot of motivation for why we're moving towards trying to build a CSM3 high resolution. We need a photo. We have your award. You're going to have to come get it. Just kidding.
When I get a chance, I
want
will.
to get a photo with you as well with it next time you're in Boulder. But so let's thank Ping again for his congratulating.
Thank you so much.
And then last in this morning session, I want to announce the Graduate Student Award winners. In this case, it's two. So we had a statistical tie for the awards, and we had this ranked choice voting. I decided I didn't want to deal with that. I just want to recognize two different people who did great work. So it's a better way to do it anyway. So our two winners this year are sitting near the front here. Giovanni Sejo Ellis, stand up. And Jonas Shaw. So they're each going to give a short presentation. So Giovanni is going to go first. We do have awards here, which I'll hand out to them. You guys are going to get this. We'll get a photo after, okay? Okay, so Giovanni has been selected in recognition of his pioneering contributions to regional ocean modeling within CSM. As a PhD student at University of Colorado, Giovanni led the development and implementation of the regional CSM MOM6 component model, introducing a completely new capability to CSM. His work not only advanced our understanding of salinity variability in the Caribbean Sea, but also created essential workflows and documentation that now support downscaling CSM simulations to high resolutions of 1 to 10 kilometers. Though Giovanni is now a faculty member at the University of Puerto Rico at Mayagüez, he remains a valuable collaborator in CSM and MOM6 regional modeling efforts. We congratulate him on this well-deserved award.
Thank you, everyone. Thanks for having me here. I'm deeply honored to receive this award, particularly on the 30th CSM workshop, a great milestone. My name is Giovanni Seijo-Ellis. I'm currently an assistant professor at the University of Puerto Rico, Mayagüez, but not that long ago at all, I was a PhD student at CU Boulder. And today I'm gonna, in a very short and concise way, try to take you to a little bit of the history, my history as a scientist, as a graduate student, and some of the research that I did in collaboration with NCAR and CSM. And I want to start by a very short story. I started my graduate studies in 2017. I moved out of Puerto Rico in the summer of 2017, and 2 months later, if I can advance, there we go. Okay. 2 months later, Hurricane Maria devastated the Caribbean region. In particular, Puerto Rico, U.S. Virgin Islands, the Dominican Republic, and many of the other nations. And it was a very overwhelming time. I was away from my family, couldn't do much about it, but also knowing that extreme events like hurricanes were likely to become more frequent, and just feeling that maybe we haven't done enough. And that sort of set the stage in some ways for a lot of the work that I've been dedicating my graduate studies and I would like to dedicate my career to. Extreme events are only, next slide, please. Oops, there we go. Extreme events are only one of the many changes that the Caribbean is experiencing right now. The last 3 decades have shown one of the highest warming trends for the region, up to 0.2 degrees Celsius per decade, according to the WMO. Sea level rise has accelerated to almost double the global average in the last 2 decades. And the percentage of light corals has declined by over 50% in the last 5 decades. The figure that I'm showing here was kindly provided by the Climate Office of Puerto Rico. Shows the daily accumulated hours with temperatures exceeding 86 degrees Fahrenheit. The purple line that stands out above all of the other lines is 2024, which we know has been a record-breaking year. The Caribbean is very particular, not only because I'm from Puerto Rico. There's a very important, it's a very important part of the world. There's 13 independent island nations, 14 territories, including Puerto Rico and the U.S. Virgin Islands. It has a combined GDP of about 152 billion. It can account for the global 15 to 30% of the global ocean economy. A population of about 45 million, excluding countries in South America and Central America that border or have coastlines in the Caribbean Sea. Ecologically and biologically, it's quite unique, and it's often referred to as a living laboratory, and we're already seeing drastic changes to that. What have I done as a scientist to start addressing and understand better some of these changes and provide some meaningful solutions to the future? One of the things that I did was use the very same high-resolution CSM ensemble that Ping just presented to dive into some of the what projections are telling us may happen in the Caribbean Sea. We examined two periods, a reference period between 1986 and 2005, and the end of the century, to look at changes to different atmospheric and oceanic conditions. In here, I'm showing near surface temperatures of the ocean. And very strikingly, we found that the warming trend in these simulations is about 0.2 degrees Celsius per decade. And as you remember from 2 slides ago, that's exactly the trend that we're observing at the moment in the Caribbean Sea. What's noteworthy about this is that these simulations are under our CP 8.5 scenario, which we often refer to as the more aggressive scenario. And so for the Caribbean Sea, it seems that this scenario is not a highly unlikely case, but because it's very much what we're seeing right now. This slide, this figure shows changes in the salinity, the near surface salinity of the Caribbean Sea. A lot of projections agree that the salinity is going to become more saline. But what I really want to highlight in here are the spatial variability of the changes, highlighting the need for high resolution in terms of what the particular needs and actions that each nation in the Caribbean Sea should take are going to be shaped by this spatial variability. Salinity is changing by many contributions of different other processes, some of them related to the surface freshwater fluxes. We know that the decent sample and many other projections indicate that precipitation is going to be decreasing across the century in the Caribbean Sea, evaporation increasing, all of these contributing to a drier climate and a more saline Caribbean Sea. Now, as being showed, these type of simulations can be quite expensive computationally, and in many cases prohibitive to many institutions and researchers around the world. So towards that end, we developed one of the first regional ocean configurations within CSM, taking advantage of the new ocean model, MOM6. It's a 1/12 degree configuration. You can see here the surface temperatures and surface salinity. It was validated at seasonal to interannual timescales and showing really strong, solid results. So we're hoping that this can become a very useful tool to continue examining climate change impacts in the Caribbean Sea. And sort of my dream with this configuration is to eventually have it coupled to an atmospheric component and potentially a land component at high resolution so that we can continue to do impactful and meaningful science in the Caribbean Sea. And talking about that, and how CSM can advance regional climate science, I just want to highlight that NCAR has many great initiatives that one way or the other are helping develop and facilitate high resolution modeling capabilities, and I think we need to ensure that that support continues. Other partner institutions are doing the same. I also want to highlight the importance of collaboration frameworks and co-production. There's a really big need to bridge the gap between physical and social sciences to be able to reach out to communities that are facing climate change right now, to understand their needs and make our science really impactful like it should be. Two good examples of that are the Rising Voices Changing Coast project that has a strong collaboration with NCAR, and the Raíces initiative at the University of Puerto Rico in collaboration with NCAR also. The importance of this, in my view, is that regional climate science should target local needs. That's the main goal. And as climate modelers, we should start asking the question, not what can we model, but what must we model. So with that, I leave you guys. Thank you.
We're going to skip questions in the interest of time, but thanks very much, and I really like that last phrase. It's perfect, perfect motivation for us. So next we have Jonah, who's going to give a presentation as well. So Jonah is a PhD candidate at the University of Colorado, and this award reflects his multiple impactful scientific contributions, both developing and applying CSM. In particular, he has produced novel work on the climate impacts of mixed phase clouds in the Arctic, and on the seasonality and the emergence of the human-caused long-wave radiation signal in the Arctic. and as well as implementation of a satellite simulator in CAM to enable direct radiation to satellite observation model data comparisons. His work reflects both technical excellence and scientific depth and has earned him a NASA Finest Fellowship. So congratulations, Jonah.
Hi, I just want to kind of echo the sentiments of the other nominees today in that it is truly an honor to be up here, and it has been an absolute pleasure to be able to work with the CSM community during my PhD. As Dave said, my name is Jonah Shaw. I just defended my PhD at CU Boulder, where I worked with Jennifer Kay. And I'll be focusing on one chapter of my thesis where I developed a satellite emulator tool in order to make comparisons between CESM and these kind of direct spectral radiation observations from satellites. And when I say spectral radiation observations from satellites, what I mean are fields that are kind of measured in units of brightness, temperature, or radiance. And so these fields are specific to individual instruments up in space and how they respond to different wavelengths of light. And hopefully I'll be able to convince you that not only are these comparisons now pretty easy to make in CESM, but they're really valuable and insightful, and they're a great complement to how we already do our model evaluation. And I'll ground this by actually taking us back a little more than a year to a really awesome CLIVAR workshop that was hosted in Boulder and organized by a number of folks from NCAR. And it was all about confronting our Earth system models with the trends that our observations document. And the very first talk was an invited talk by Gavin Schmidt, who's the director of NASA GISS. And Gavin's talk was about kind of this art of comparing our models and our observations, and it was framed through a number of philosophical footnotes that Gavin presented to us. And so I just want to take the second philosophical footnote to try and kind of ground this presentation. In the footnote that Gavin gave us was all observations and comparisons are based on models too, or in other words, it's models all the way down. And what I mean by models all the way down is that many of the data sets that we treat as kind of a baseline in which to evaluate our models are actually themselves the result of some kind of inference or post-processing or aggregation step that introduces its own biases. And we should be really aware of all of these kind of hidden structural uncertainties when we evaluate our models. And one really excellent example of this is actually our reanalysis in satellite data sets, which I think are really some really bedrock data sources that we use to evaluate the performance of our models. And I'm going to argue that these data sets often disagree even when they are ingesting the same direct observations. And this is just one example. These are fractional trends in water vapor as a function of latitude and pressure from two different data sets. And you don't really need to know these specific data sets, but what's important is that they're both actually developed by NASA, and they both ingest the same set of direct observations, which are these direct spectral radiation fields observed by an instrument called AIRS. And so we can see that even though these data sets have so much in common, they give us entirely different pictures of what our trends are looking like. And if you ask, well, what about reanalysis? What about Ara 5? It ingests a lot more information. It's a lot more complex. Well, if we add Ara 5 to this picture, we again get a very different image of what our trends look like. And so I think this makes a good point that the differences between these data sets imply this large, unquantified structural uncertainty that's often hidden and really easy to ignore when we evaluate our models. It's a lot more work to evaluate multiple observational data sets. I also want to argue that these differences between our data sets are actually just a conservative estimate of the uncertainty, because they only sample the kind of differences that these data sets have and how they do their inference or what they ingest, and they don't sample the uncertainties that all of these data sets share. And Ray Chemke visited CGD just a few months ago, and I think gave a really excellent example in this paper that I'm noting here, and I think it's really cool to read. And so I want to kind of argue that in the presence of these large uncertainties, our spectral radiation observations, these kind of direct observations, are really some of the most complete and detailed observational records that are available, and that we should try to, in addition to the kind of standard evaluation of our models that we do, also evaluate them against these more direct observations. And of course, there's a reason that we haven't been doing this before, and it's because these comparisons are not easy to make. these radiation fields depend on individual satellite instruments and how they respond to these different wavelengths of light, whereas the radiation fields that our models produce are designed to iterate the physics of our climate system as accurately and as efficiently as possible, and not to provide model evaluation. And so what we need is kind of an additional tool in order to span that gap and start making these other comparisons and kind of ask how much we can test or trust these other data sets that we often rely on. And so I built this tool in CESM, and we are effectively trying to bridge that gap and emulate these direct observations that our satellites would make within our Earth system model. And what's really great about CSM and a few other Earth system models is that they already have this satellite emulator program called COSP. If you're not familiar with it, it's another it's another software package that's built alongside the model. And as CESM runs, it has basically access to the instantaneous model state and is able to pass that state through these emulators that tell us, what would Calypso see in terms of clouds, or what would MODIS see in terms of clouds given the model state, and kind of account for these differences between satellites. Of course, we want to go a step further and evaluate the radiation fields and kind of completely sidestep this retrieval or inference step that kind of adds a lot of these uncertainties. And so what we added here is a radiative transfer code called RTTOV. And just like COSP, it has access to the instantaneous model state, but it reproduces are these radiation fields that are not designed to iterate the physics of the model, but are rather designed just for evaluation and comparison against these basically direct observations that are often contained in level 1 satellite fields. And so we're able to run this emulator kind of in step with our model and in time, accessing the model state and effectively accounting for these different spectral response functions that our satellite instruments have at different channels. And what we get out of this field, or this tool, excuse me, are these satellite-like spectral fields, but critically that have intuitive meaning. And this is just a very kind of simple example to try and build this idea, is that on the right here, we have a surface temperature field from CESM, and on the left, we have something that looks identical, but is actually a spectral radiation field that's been produced by this emulator. This is effectively just a very transparent region of the spectrum, and we're only taking our rate of transfer in the absence of clouds. But the idea is that on the left, we have something that can be really fairly compared with this direct observable, and it still has all the intuition of the model state. Of course, I said this is a really easy example. We can move on to kind of other climate processes or variables that we're interested, like temperature in the upper troposphere, which is in the top right corner. And on the left is just another spectral channel that is much more opaque and is effectively sampling the upper troposphere. And so it's a really excellent proxy for that field, but again, is much closer to a direct observable. We can even think about things like clouds. So in the bottom right, we have our cloud field from CSM2, and in the bottom left, we just have a really simple proxy where I've taken the difference between our clear sky and our all sky radiation fields for this really transparent channel. And this is really just the thermal contrast between the warm surface and the tropics and the subtropics and the much colder emission temperatures from our clouds, but we can see that it's a really good proxy for the actual cloud field within our model. And so these are just two examples, and I just kind of want to make the point that these spectral observations, this instrument that I'm emulating here has more than 2,000 spectral channels. There's a huge amount of information in them, and these are some of the simplest proxies that we can construct, and there's a lot more that you could do if you're interested in specific climate processes. So whether these fields are of interest to you or not, I think there's value for this tool in so many different places. And once we've established this intuition, we can do just like very standard climate model analysis with these fields. So now we're looking at that field that sampled the upper troposphere, and we're comparing our observations from the NASA AIRS instrument from CSM2. This is in a region in the tropical Pacific, and we can immediately effectively identify a cold bias in our model. And we don't have to be worried about kind of uncertainties in the retrievals as long as we have that really strong intuition. We can move to another region. This is a mid-latitude region, northern North America, and we can start to interrogate the seasonal cycle and identify a very strong wintertime cold bias in tropospheric temperatures. And again, I think that the specific kind of physical processes are more meant to be illustrative in kind of trying to ground ourselves in that these comparisons are free of many of the uncertainties in our retrieval products. If we turn now to that cloud field, we can, again, just kind of apply this very simple analysis and see that our model is performing quite well in this tropical region with clouds, but is struggling much more in the mid-latitudes. And so what I mean to the point I mean to make here is that the standard methods that we have for model evaluation, whether it's you're perturbing your parameters, you're running a hierarchy, you're nudging, can all be applied to this tool just like CSM output. And so it's really a complement to the ways that we already evaluate our models. Another example that I'll kind of give, and this is a bit of a pivot, is that mostly I've been framing this in terms of how we can kind of use our observations to do a better job evaluating our model. But the benefit of this tool really flows in both directions, which is that we can also benefit the observational community. These are other spectral radiation fields, but they're emulated for this instrument called PreFire. And PreFire is 2 CubeSats that were launched a little less than a year ago. And the kind of novelty of these observations is that they're measuring, in addition to kind of standard 5 to 15 micron channels, also beyond 15 microns in this far infrared region that historically does not have observations. But these CubeSats, because of their kind of design, will only be up for 4 or 5 years, and so they don't have enough time to observe effectively internal variability or the climate mean state, a lot of the things that are really important to being evaluate our model. And so what we can do with this tool is emulate over a much longer time period what this instrument would see and effectively generate those statistics of internal variability or forced change on our side so that we can take those observations, put that in that broader context that an Earth system model can provide, and draw as much valuable information from these observations as possible. And I think this is a really kind of cool application for CSM2 in order to kind of partner with satellite missions. So to summarize, hopefully I've convinced you that a lot of our observational data sets have these structural uncertainties that are often kind of hidden and we don't actually fully understand, but that we can complement those comparisons by returning to the direct observations, which are these spectral radiation fields, which again are really information rich, they're globe spanning, and they go back multiple decades. And so it's just a way to complement our already the evaluation methods that we already do. And yeah, I think that's it. Thank you so much. And again, it's really an honor to be here.
All right, thanks. Congratulations again to Giovanni and Jonah and to Ping. So that concludes this morning's session. Please find Giovanni and Jonah and congratulate them, ask them questions about their talks and their careers as they're going to move forward now. So we're going to take a break. We're going to come back with a plenary session on sort of societal applications and integrating humans into our system models after the break. So yeah, let's thank everyone again, and see you out in progress. Great. Okay, thanks everyone for coming back. Let's get started with our plenary session. We have 3 nice talks. We kind of put this together to be a set of presentations about sort of the societal, beneficial applications of CSM. You know, it's in the vein of this, we didn't really know at the time, but sort of we did, in the vein of the CSM use and impact. So we have 3 nice talks, and by sort of different people than we've had at this meeting before, although Hansi has been a member of this community before, so she's moved on to a different position. So I'm really looking forward to this. It's going to be, I think, really thought-provoking and interesting. So we're going to start off with Hansi. So Hansi is the CSO and co-founder of Planet Incorporated, a climate tech startup specializing in year-ahead forecasts of environmental variables and extreme weather risks. Before Planet, Hansi led the Climate Dynamics Laboratory at the School of Earth and Ocean Sciences at the University of Victoria. Her group researched the physical climate system, particularly the myriad interactions between the atmosphere, ocean, and ice that give rise to Earth's climate. And she is an outgoing co-chair of the Polar Climate Working Group. So welcome, Hansi. We're looking forward to your presentation. Point to the screen for a second. Hold it for a second.
Okay. Oh, cool. Ah, okay. Well, hello everyone. Thank you so much for being here. It's like super exciting to be up here addressing y'all on this 30th anniversary. So I'm going to talk a little bit about my journey, particularly from being an academic scientist and a researcher to doing things in the real world, which is messy and crazy, but to me, it's been amazing, and I probably feel like I should have done it sooner. So you'll see. So before I get started, I want to get out a few shout outs. So first of all, it's Pride Month. Happy Pride Month, y'all. And yes, okay. And it's 2025, but guess what? Black lives still matter, so we support that. And 2 more really key shout outs to your colleagues at NOAA and NSF who might be dealing with a lot of drama and storminess in their lives right now. Please give them a hug if they like hugs. Okay, and say thank you. I'm really grateful for all of the work that they do, who have made so much science possible in the earth sciences. So today, I'm going to talk a bit about my career story, how I decided to found Planet AI. I'm going to talk about AI for the earth sciences in general. I'm going to talk about taking the leap into the real world from the academic and research world. I'm going to talk a bit about the business of forecasting, and then I'm going to offer some unsolicited advice, particularly for early career researchers who are interested in making the leap into the real world. So this is my career timeline, and it looks like the career timeline of a squirrel. Like if a squirrel could have a career, this is how they would have the career, because they would jump from one thing to the other because they couldn't decide what they wanted to do. And that's pretty much what I did. So I got my BA in physics from Rice. In the last century, which is kind of scary. And then I spent a bunch of time in the real world, dancing, traveling, doing some small business entrepreneurship, starting a family. And then I did my PhD in atmospheric sciences with a master's in applied math at the University of Washington. Finished that in 2015, spent some time with the US Department of Energy as a Linus Pauling Fellow. And then I was an assistant professor in the School of Earth and Ocean Sciences at the University of Victoria. And at that time, that's when I decided that I wanted to start a company, found an amazing co-founder who I will talk about in a bit, and decided to just, got to the edge of the cliff and decided to take off. So that is sort of the overview. So career of a squirrel, here we are. So what is Planet? So Planet is a mission-driven climate tech startup. We are committed to build climate resilience around the world using a combination of the latest science and the AI. So far, we've gotten over $3 million in funding. We have 5 team members. We have 15 B2B users and this is growing. Not all of them are paying yet, but we're going to make them pay. And then we have expert advisors, some of whom are sitting right in this room today, which is amazing. And then, you know, we have training data, because you know what? This is one thing that us earth scientists are really good at making, so much data. So we have tons of data. And so one day we will train on all petabytes of it. And just recently, we became an NSF SBIR portfolio company. So that is super exciting. So thank you, NSF, once again. And amazingly, we didn't get our funding pulled, so. So a little bit about our founding story. So this is Dr. Kalai Ramea. She is Planet's co-founder and CTO. I'm CEO. And so whenever you start a company, there's always a founding story. For both of us, I was sort of moping around at the University of Victoria. This was around 2022. Kalai was a technical director at that time at Xerox PARC in scientific AI. And so, we were introduced by Dr. Phil Rash, which many of y'all know. And he was like, Hansi, stop moping around. Here's a friend, make a friend. She does AI, do something cool with her. And so we did. We actually got together and wrote a proposal for DARPA and got $1 million to spend from DARPA and led some cool projects on geoengineering, and particularly geoengineering teleconnection emulators, which, sure, maybe in some future sci-fi world, you might be able to use them to, create your optimal geoengineering forcing in order to, produce the desired climate effect. And I have to keep track of the time because I talk a lot. Okay. And so we got this money, and as soon as we got this money, we're talking every day. I literally talked to Kalai more than I talked to my husband, which is kind of crazy. And so, started talking, we were like, oh my gosh, we need to bring some of this into the real world, because great that DoD gets to play war games with emulators, but there's so many other uses of this science. And so much of it hasn't quite made it out from the research world to the real world. And so that's what we decided to do. We decided to start Planet. So the paradox of the earth sciences is the fact that it is a science, and science is all about research and empiricism. And it's fun to know just because you want to know. It doesn't even need a reason, right? I mean, that is basic science. At the same time, today, we are sort of in a global environmental crisis. And therefore, society really needs our science. And so both of these things are happening simultaneously. And for many of us, it's possible that we actually do earth system science because, we first got into it because we were like, oh, I think society really needs this. I know for me, I started in math, and I came into the earth sciences because I was like, oh, this is societally relevant. You can actually use math for cool things that matter. So the challenge here, of course, is that we have to bridge the gap between what science wants, which is rigorous, empirical, reproducible inquiry into just how the world works, without necessarily any practical applications other than the fact that it's cool, and then what society wants, which is insightful, valuable technology that solves something that is a problem or a pain point for them. So this is actually, this bridge, that's what companies do well when they work well. And so this is what, our goal is, to be able to bridge this gap between science and society. So what we did was we had hundreds of conversations with folks in a whole bunch of different industries to try to understand what is it that these people want. And, the thing is, I am a nerd, and I work very, particularly on nerdy things and computing and math. And so, I might think I know what people want, but I don't know what they want until I talk to them and I listen. And so this is what we did. And there were many insights that we got by just having a ton of these discovery conversations with people in a whole bunch of different industries. So some of these people were just friends. We were like, hey, do you want to know anything about how your house might be underwater in 50 years? And they were like, no, please don't tell me that information because I just like outbid 10 people to get my house. So please do not tell me that. So, you know, we talked to friends like that. And then we were talking to insurers, we were talking to farmers, we were talking to reinsurers, we were talking to logistics folks, we were talking to data center folks. We talked to so many people. And so there were some things that we learned just kind of generally about how climate information is used. So first of all, I know we love longer term outlooks, but the kinds of outlooks that people want to hear is not scientists scolding them necessarily. I mean, we should scold them. Don't worry, we should. Let's keep scolding people about long-term outlooks and how dire things are. But people also need practical information, and that practical information is the nearer term information. It's not the, you know, let me tell you what a mess things are going to be in 2050. Like, nobody wants to really hear that, and like, they might not even want to pay you for that. They probably don't want to pay you for that, in fact. So what people want is nearer term information, and they want good quality nearer term information. Who wants this? Well, people that need better environmental security. There are many industries that are extremely environmentally vulnerable. Think about forestry. Think about farming. Think about insurance, which, you know, in the state of California, insurers are running around like chickens without a head. And, you know, this is happening around the world and in many different markets. And so, you know, people want a little bit more certainty. People also want information that's insightful more than they just want raw data. I mean, if they wanted raw data, maybe they would go to NOAA, right? But they want actually insightful information that can tell them very particularly things about their industry. And then they want these insights to be packaged in a way that is understandable to them, because not everybody is a data scientist, not everyone's gonna pull up Python, not everyone is going to, you know, be able to understand your, you know, giant data file that you provide them in NetCDF format. So you really gotta make this so that it is usable. So this is how society sees future outlooks. I know this is not actually where the science is, but this is how people see it. So what they see is like, okay, I got these weather forecasts on my phone. They go out to 10 days. And then they hear on the other side all the scientists being like, things are going to get really bad, and they're getting bad, and, you know, what are you guys going to do? Stop emitting, right? Which is great. They should hear that. But people literally don't know that there is actually science that can address forecasts beyond 10 days. Like, they just, like, that's just something that unless you're an energy trader or someone that is like, oops, in like maybe Citadel, unless you work at Citadel or D.E. Shaw, or unless you're an energy trader, like, you literally think that this is impossible. And in fact, when I was first going around pitching Planet to venture capitalists, they were like, I think they literally thought I was Elizabeth Holmes. They were like, are you messing with us? Because we don't think that anyone can do this. And I was like, scientists have been doing this for 20 years, y'all, right? But the problem is that, like, we're not good at communicating this stuff. We're not good at operationalizing this stuff. We're not good at, like, giving this information to actual humans in a way that they know that it exists and that it solves their problems. And so this is how our work fits in. So we fill this S2S gap. We provide forecasts from next week. Our goal is to eventually go to 5 years. I'm telling you, like, humans are like squirrels. We pretty much don't want to know anything beyond a year. So, you know, that's about the sweet spot. Next week to next year, that's where people want to know information. And beyond that, it's like, sure, maybe if you're a forester, you know, you're like, yeah, my trees take 30 years to grow, guys, so you might want longer term information. But in general, this is sort of the time scale that people think is important to them for their decision making and where they wish they had more information. So there are huge opportunities for AI in the earth sciences. So we know that weather forecasting has really been revolutionized by AI in many ways. It has a long way to go, of course, but there's been huge leaps and bounds and advances. So the big question is, what comes next? So where else can AI be applied in the earth sciences? And I would say S2S to D forecasting is probably one great area where AI can be applied and make a great difference. So in terms of these different opportunities, first of all, we have training data. Like, we have petabytes of training data available for models to learn dynamics. So, I mean, you just got to train them, right? Earth system model output, satellite observations, maybe even sparse measurements so that you don't even have to rely on some sort of analysis product, right? So many different data sets to use. And then there are so many different architectures. Now, please don't ask me any details about these architectures. If you would like to know details, our machine learning engineer, Anisha Paul, is right here. So make friends with her. She has a name tag. Anisha, raise your hand. Yeah, thank you. And she is amazing, and she is like the smartest gal you'll ever meet. So talk to her if you want to know like real machine learning engineering. And so many different ways of creating your machine learning architectures, so many exotic, weird operators and nets, transformers. I thought that this was a toy, but it's not a toy. It's not a robot. It's like an actual architecture. And then latent space representations as well. So, and then there's so many different modeling approaches, right? You could do brute force training, but you could also use physics-informed models. And then you can also use foundation models to learn like the real way in which a system operates using a ton of data. And so that's where that petabytes of data come in, and that's where, NSF is like, we want to fund you for this. And so that's why we're an SBIR company. So how do S2S forecasts inform businesses? So there's many different ways that they can. And so kind of let me walk through this kind of different ways that information can be presented. First of all, there's just the raw forecasts, and these are for users that are extremely data savvy. So if you go and you work with like D.E. Shaw, right, they have like an energy trading division. These people already use NOAA forecasts and ECMWF forecasts. So, they have algorithms. They literally will not tell you anything about what they do other than they're doing something with energy because they don't talk. And they will use your forecasts. Like, that's it, right? But most people are not D.E. Shaw or your neighborhood energy trader. So they need a lot more help. So this is where perhaps generic data layers might be useful. So instead of telling people, this is what we forecast the temperature to be, we then say, okay, this is what we think the heat index might be, and this heat index might be not good for your outdoor workers. You might be putting them in harm's way. And so, you're providing them a bit more insight than just the raw data. And so this is for users who might need basic weather insights for making their decisions. And then finally, at the very end, you might provide more tailored insights using customer-specific data. This is where you get into a lot of, potentially security and data compliance issues. So this is an area that we're very careful in, and we haven't quite gotten to that area because then that means you're saving customer data, et cetera, and that is, highly regulated. But basically, this is for people who need insights right at the intersection of weather and their business operations, and they need very, very, very specific information. So think about like a logistics company. They might have all of the different nodes of their supply chain, and they might want to know, hey, tell me how I should design this in such a way that over the next year, I am least likely to have weather disruptions, right? So this requires a lot of, knowledge from them on their specific operations, and then it requires using the weather data on top of that. So our customers are in sort of many different areas. So finance, those are real fun customers there. Insurance, shipping and logistics. This is a pretty cool area, especially if you like maps. Utilities, that is a tough nut to crack, y'all. Yeah, I don't know. If someone knows the secret to working with utilities, let me know, because we have a utilities customer, and they're tough cookies. And then humanitarian organizations. So we do a ton of pro bono work with humanitarian organizations, and in particular, humanitarian organizations that work in the developing world. And the reason why is because, as we know, climate change is a huge environmental justice issue. In particular, the effects of climate change, as we all know, are much more dire in the developing world, not only because of fewer resources, but sometimes of even greater impacts. And so what we do is we provide forecasts, S2S forecasts, to various NGOs that operate for humanitarian causes in the developing world. So we are working with NGOs in Ethiopia and other countries in East Africa. We are also working with NGOs in South Africa, particularly dealing with malaria, because malaria kills a ton of children. And guess what? Like, if you know when the rains are gonna start, you can actually spray properly for those mosquitoes and get the maximum bang for your buck. Because once the rains start, you're out of luck. You're gonna have, an outbreak and children will die, right? So it is totally essential to be able to get information like this to folks. And this is an area where we are super committed to wanting to do better in terms of really being able to predict the beginning of the twice-a-year monsoon rains that you get in various places in Africa and South Asia. And then we are also working with some big NGOs, including Mercy Corps. So this is super meaningful work, and we do it for free because it is insanely important. And the reason why we can do it for free is because, guess what? We make the rules, right? That is the beautiful thing about having your own company. You can do what you want. You do what you want whenever you want it, right? And so I can literally build my own version of capitalism the way that I want to. And if that includes, giving free things to people that should get them for free, then we do it. That's it. So some unsolicited advice. First of all, I know we think that we know everything, but we don't. Please listen to people to understand what their problems are. You might hypothesize that they have a problem, but talk to them and figure out if it really is a problem. Because if you don't talk to them, then, you're just going to think something is a problem, and then maybe you'll build something for them, and then they're like, nope, this is not a problem, and I'm not going to use this, right? Which is kind of not great. So make sure you listen to people. Work directly with stakeholders or interested parties, if you want to say it that way, or work with somebody who does. So, there are some, sorry, keep on checking the time to make sure that I'm not going over. There are some foundations, I'm not going to name any, that have a ton of money that do work in the developing world, and they literally come down, they swoop down, and they say, y'all need this. And they literally, sometimes spend millions of dollars on whatever this is. For example, some sort of GMO plant that they're like, hey, you should plant this because it's drought resistant. And, climate change is causing a lot of drought. Well, guess what? They never talk to the farmers. And the farmers, it turns out, they're like, no, we're not going to do any GMO plants. And so literally you have solutions that are built and then are just languishing because no one actually bothered to have a conversation with an actual farmer. Okay? So don't be like that foundation. And then finally, find a complementary buddy to work with because, I got my co-founder who is my best buddy who I talk to more than my husband. But it's great to work with other people. And, I think that if you were going to start a company, for example, it would be real lonely to do it by yourself. So find a friend. Find a friend and make sure that they're complementary because if they're just like you, that's, not quite great. So these are some of our, this is a photo from our recent trip to the Ethiopian highlands in Gamo district. This is near Arba Minch, and this was in April. And I think that this kind of includes all of those elements here. So I'm there with my buddy, who is CTO of Planet. And, we are talking directly to farmers in the highlands. You can't see them, but on the other side of that photo is a translator. And so we directly ask questions about their farming practices, about how S2S forecasts might help. What kind of information do they want? That's when we learn, like, oh, the start of the rains is really important, or how long the dry season is going to be is really important, or, how much might it rain this year? That's super important because then, they can actually determine what crops to plant, for example. So I think that having that opportunity to talk to the real people that are impacted by the work that you do is just priceless. So any opportunity that you get to do that, you should do it. So founding a startup is great, but it's also terrifying. It is magical and terrifying at the same time. So first of all, as I said, I can do what I want. So we can provide free forecasts, we can provide paid forecasts, we can do whatever we want, we can create a new business strategy and model, and we can run it our way. Okay, great. But at the same time, it's like a very lonely journey. Even if you have a co-founder, you get obsessive and compulsive, and your family is like, what's wrong with you? You get really rewarded for a job well done, which is great. I feel like sometimes in academia, people don't. But at the same time, you're constantly stressed out because you're in charge of so much stuff, right? So this takes a special kind of person, kind of a masochist. But if you are that masochist, and you need advice, you can talk to me. Because, I think it's really fun. I think that this is true, but at the same time, I feel like, the rewards are worth all of the pain. So even if you're not a masochist, there's so many cool things to do out there in the real world. There are so many big companies that need Earth system science. They need your expertise. So go talk to them. And this is not just big companies, right? There's so many nonprofits out there as well. People doing great work. And then, of course, there's all these small and growing companies that are trying out new business models, new ways of doing things. Work for one of them. Or, at the same time, if you like to build new things, there are so many new companies to build because there are huge opportunities here. People need this information. I think that that is sort of the crux of it. So, thank you so much. And yeah, I did not run over, so that is good.
Thank you, Hansi. Excellent. Any questions or comments for Hansi? Paula?
You emphasized that people don't want to make decisions based on long time scales, but I kind of feel like they should be. Do you see there being a role for you not only listening to people and what they want, but also trying to persuade them that there is this information that they should be factoring in as well?
Yeah, I agree with you that there's information that they should want. But to some extent, I think that presenting them information, say, beyond the weather scale, it starts to get into that kind of longer term information, right? Because, one of the reasons why I think S2S forecasting in particular is potentially so critical right now is because of the fact that weather that people used to think was normal is no longer normal or expected, right? And so because of that, you're automatically having the climate change conversation, even if I'm talking to a banker that doesn't believe in climate change, right? So we have to figure out ways to get in with these people, and I think lecturing them is not going to do it. So when it comes to people's bottom lines, that's kind of where it actually hits people and where people are persuadable, I think.
It's coming to your 1 petabyte of data, and I'm just wondering what the mix of that data is.
Yeah, totally. We love CSM.
Is it all, is it observational? Is it data to be trained on? Is it actual forecasts? Or just interesting?
Yeah. So for training data in particular, CSM is a treasure trove. And as you saw earlier today, CSM2 is one of the best Earth system models out there, right? So why not use it? If we're particularly, concerned with variability, then, I mean, it has a lot of it out there. So Aiden, Dr. Aiden Sweeney, who's right here, Aiden, yeah, there he is. He'll be presenting a poster on training a AI model for ENSO using CSM. And I know people complain, they're like, oh, ENSO and CSM is not good, but guess what? Like, we produced a model just using that data that predicts ENSO amazingly well. So if you do, you know, like all of the back testing, the hindcasts, and look at the ACC. So yeah, CSM is where it's at. I mean, of course, there's other good models out there too. CSM is the best.
Hi, yeah, thanks for sharing your story. I was wondering if you can expand on the tough nut to crack with the utilities, and maybe more generally, do you encounter potential partners that are skeptical of model data in general, but really like observations and like want to rather rerun like the worst drought of history rather than trust any climate model looking forward?
No. So the major thing, okay, answering the second question, in general, sure, people want quality data, but the people that want the highest quality data, those are the people that are like the hedge funds. So if you want to sell data to hedge funds, then sure, shoot for like, okay, you know, we want amazing high quality forecasts. For most people, they're functioning on nothing in the S2, S2D time horizon. And so for them, like, you know, if you start talking about quality, like, you are ahead of yourself. You are way ahead of yourself. They literally just want some kind of insight into the future that has skill, right? So there's that part. I think, sorry, what was your first question? The utilities, right? Yeah, utilities are very conservative and they don't like new things. And, you know, I think for a lot of them, they have not really wrapped their heads around climate change. So there's one utility that we are working with, and I don't know. My hunch is that they look at forecasts and pray. Like, that is all I think they are doing with the forecasts. So there we are.
Okay, thank you.
Yeah, thank you.
Okay, so next up we have Paula Buchanan. Dr. Buchanan is a practitioner academic, a pracademic. Is that your term? I like that. A sociohydrologist and disaster and emergency management researcher. She researches sustainable drinking water access issues, focusing on the intersections between public health, risk and science communication, sociology, and emergency management. As a sociohydrologist, her research focuses on how people interact with drinking water systems and human behavior's impact on these systems that support drinking water to sustain life. As a self-proclaimed data nerd, Dr. Buchanan is also passionate about using data science, information technology, and data visualizations as tools to more effectively communicate with target audiences. So welcome, Paula.
And thank you to Hansi for adjusting the microphone for someone who is also vertically challenged. I greatly appreciate it. Hello, everyone. Okay, I'll try this one more time. Hello, everyone. Okay, yeah, you're awake. And thank you for adjusting that for me as well. Thank you. As Dave said, I'm Dr. Paula Buchanan, and I swear I only met Hansi today.
Could you get a little bit closer by the mic?
Get towards it. I'm so used to moving. Sorry, guys. So yeah, I just met Hansi today, but we have so many similarities about what we think about, and you would almost think, I was discussing this with a colleague in the back, that we had planned our slides and our content together. We didn't. We just think alike. So yes. So the title is Bridging the Gap, from Hansi, Communicating Earth System Science to Stakeholders, Communities, and Decision Makers. So this is what we're going to be talking about in the next couple of minutes. Going to give you an introduction, going to talk a little bit about that topic of SciComm or science communication. I'm going to give you some tools and tips that you can use in CESM, SciComm tools that I've used in the past, and bridging the SciComm gap. I'm going to give you a really cool, neat sample example of using SciComm that I have used in the past as a sociohydrologist, Gonna do a conclusion, and hopefully, if I can get through this quickly enough, some time for Q&A. So let's get started. So, introduction. So, I see this as a theatrical performance, right? We're on stage, and I am Act 2. We got our Act 1, we got Act 3 coming up. We're right here in the middle. We started talking about system predictability. I'm going to be talking about communication, then there's going to be someone coming and talking about human systems. So I am that bridge. Again, the concept of the bridge. Communicating science, as I call it, SciComm for short, for real world impact. Because the science that we do, it could be fun, right? But you'll see me, I'll say this a lot in this presentation, so what? It's one thing my dissertation chair used to always say. Oh, that's really cool that you want to, when I was in public health, for example, you want to look at obesity and the connection possibly between this and obesity. So what? Who cares about that in the real world? It's kind of cool and neat to do, but like, what are the practical implications? And that's something we have to really start to focus on. So a little bit about me. Yes, both of those pictures are me. The first one is me. I participated in a program in the city of Atlanta where I'm based called the Citizens Fire Academy. It's a place where, it's a program where people who are residents of the city can actually go through fire and EMT training. And so that is me in full turnout gear in August in Atlanta. It's about 20 pounds. And if I put in the oxygen tank, it would have been another 25, so yeah. And I managed to smile, so that's me. I also worked, that's why I'm gonna call out Hansi again. I actually worked for the City of Atlanta's Department of Watershed Management. That is me actually in the field doing a sludge judge, as we call it. So I've done work with fire, EMT, and of course in water. So as Dave said, I call myself a pracademic. I'm a practitioner academic. You might also hear people call like a practitioner scholar. It's basically the same thing. My doctorate is actually in emergency management, so I do focus on disaster and emergency management, sometimes called EM, sometimes called DEM. And I'm also a socio-hydrologist. How many hydrologists are in here? I'm just curious. You too? Oh my God. Who else? Keep your hands up. All right. Who's a socio-hydrologist in this room? There's just me. Yeah, we're pretty rare. So my background is actually not as a hydrologist/engineer, it's as a sociologist. So I'm the person who deals with the people who are going to be using the systems that, say, a Dave would make. I do the UX to make sure that it works properly. As Hansi was saying, you have all this great technology out there, but did anyone talk to people about how it's supposed to be used? That's very important. And then also I do a lot in the SciComm or science communication space, which is why you guys wanted me here today. So let's talk about science communication. Gonna do a little bit of a deep dive. So what is it? It's sharing your knowledge, right? It's communicating with stakeholders. And it's a personal story. A lot of us are scientists because we're passionate about something. Someone might want to become a cancer researcher because their parent or a loved one died of that same cancer. So we all have these personal stories about the science, but then we talk in a very, what I call, wonky way, right? We use all these fancy acronyms and words, and we have to remember why we started doing the science in the first place, you know? Why is it you decided to be a researcher? Why did you decide to be a socio-hydrologist? Why did you decide to be in public health, and so on? So yes, we're going to be showing the outcomes, then the results, right? And again, as one of my dissertation chairs would say, those biases, assumptions, and limits, you got to put a fence around those. What is your fence? Because if you're looking at cancer, what type of cancer, and so on. You have to put that fence around what you're doing and then what biases, assumptions, and limits you have based on what's in that fence. And then again, I'm going to keep saying this. So what? Okay, you're doing this really cool dissertation. You're going to be doing all this stuff with GIS data. So what? Why would my grandmother care? Why would a 3-year-old care? Why would a family that's poor and like living on the edges of society or living in the global south, like Hansi was talking about, why would they care? That's very important. And then you also have to think about how SciComm translates into science policy. The science policy of so what? What are those actionable steps that will be taken, hopefully, ideally, if you are good or effective at science communication? How can your science be communicated so people care? They don't ask, so what? They just like, okay, what can we do? What money can we give you to continue this research? What policies and legislative actions can we take to support what it is you do? So, why should everyone in this room, CESM people, care, right? Without effective communication, without effective science communication, science fails to influence decisions or the science policy. You're working in a vacuum. It could be really fun, but it's more navel-gazing, and you're not making an impact on society. And I think that's why a lot of people become scientists, right? So you have to think about that. You're failing to influence decisions. Again, the so what. I called myself a practitioner academic, a practitioner scholar. My research, from my perspective, whether I'm doing emergency management, whether I did public health in the past, whether I'm doing sociohydrology, working with water utilities, my research is used to better inform practice. It is not in a vacuum. Practitioners should be able to take what I'm doing and use it. Or even better, I communicate with those farmers, Hansi, like you were saying. I communicate with the water utility people, and yes, they're conservative and can be difficult, so we'll talk later. But yes, that's so important. What is it that we can do to help you as opposed to I alone can fix you, right? Sound familiar? So stakeholders must understand the research that you do in order to find it valuable and also to use it. So, science policy, why should you care? You're a scientist, you don't care about science policy, right? That's wrong. As a scientist, you should care about policies that impact the research that you do. Science policy connects that science to the so what, the actionable steps, government decisions, public policy, and also laws, like I was saying, legislative actions, and funding to support the research that you do. So the science, you use SciComm, and then that translates into science policy, which then can be used to further fund science. So it's almost like even though it's linear here, it's almost like a little bit of an oblong circle. You're just kind of going in like a flow, so to speak. And what you do here at CSM is some nerdy stuff. I remember when my colleague actually asked me to look at like what some of the work, and I was like, wow, this is wonky. It's cool, but it's wonky. It's hard to digest though. And so it's really important to take all these complex models and translate them into something that is clear, understandable, and actionable, whether you're 90 years old or 9 years old or 29 years old. That's really important. Transform that so what into an action. So I'm going to give you a couple of case studies of SciComm, or science communication in practice. As I was saying earlier, I actually used to work for the city of Atlanta in the Department of Watershed Management. And for those of you who know Atlanta, who's been to Atlanta before besides just going through the airport? Yeah, it's a big place, isn't it? It's a little intimidating. It's sprawling. It's big. Yes, that's Atlanta. It's a big urban city environment. It's also, interestingly, from a DWM standpoint, it's a huge urban forest. One of the things you'll notice, there's a lot of forest, like 5 minutes from downtown. And there's watershed issues aplenty. Whenever it rains, it floods. The infrastructure is trash. It is, because people don't want to pay the money to get it retrofitted. So one of the things that my office decided to do when I worked for DWM was to create a public education campaign. So as Hansi was saying earlier, there's all that earth science data out there, right? We at DWM had a lot of data. So what are we going to do with it? We're like, okay, let's flip this a little bit. We're actually going to take this data and look and try to figure out what is the human impact of water systems, right? What is it that we do as human beings that negatively impacts the watershed that we have, the urban forest that we have, and then how could we educate and train people to improve their behaviors so that our watershed is more sustainable? And so that's what we did. We had all this water data, we analyzed it, we talked with community leaders, and we actually started improving the watershed through the Safety Ambassador Program. I was in the inaugural class of it. I really enjoyed it and loved it. And it's so important to have programs like that that get people, everyday people, engaged in the research and the science that we do. And now I'm going to pick on you guys, right? Because I'm here. So you're a case study here. You got this complex data that you're trying to translate into actionable insights for stakeholders. So 2 ways you do that. You actually have been able to mitigate urban heat issues. Good for you guys. Clap for yourselves. Come on, you got to be your best cheerleader to get people. Come on, clap for yourselves. All right. And you also use that climate data to improve one of my areas, water resource management. Second clap. Yes, yes. So you're already doing some of this. It's just you have to think a little bit more on how you could do it so it has more impact. So you're already ahead of the curve, which is great. So some tips and tools for you and the audience to learn how to be awesome SciCommers. So first of all, you have to think about what type of media you're going to use, right? There's traditional or legacy media, as it's called, print, radio, lectures like this, right? That's fine and dandy, but I can say this as someone who is older, it doesn't appeal to the young people. It really doesn't. You need to think about other ways. You have to think about multimedia. Even though I'm not the biggest fan of podcasts, they're really popular. They're really, really popular. Think about podcasts. Think about photography. That's actually a more traditional media, but there's ways that you will see, spoilers in the presentation, where you could use photography and illustrations. And then you could also make videos. We're going to talk a little bit more about that later. So there's all different types of tools you could have in your toolbox, but I'm going to just focus in the interest of time on 3, and I've used all 3 of these. Having cross-functional teams, knowing your audience, and storytelling. So first of all, cross-functional, or as some people call them, interdisciplinary teams. So like disaster and emergency management, which is my field, earth sciences deals with what you call those wicked problems. You've heard people say that before. They're really complex. It almost feels like when you're doing research, you're almost doing whack-a-mole. As soon as you push down one way, it goes up another way. People are involved and human behavior is involved, which means it's gonna be a wicked problem. There's just all these different things you have to deal with. So we're dealing with complex, wicked problems. So it's important to have the scientists like us around. But it's also important to have community member input. You know, as Hansi was saying earlier about the farmers, if you're going to be doing something with farmers, you should probably have some dealings and interactions and trustful relationships built with those farmers. You need communicators like myself because we help to translate your science into something that more people can understand. We're going to need the modelers because I can do a little modeling, but I'm dangerous in a bad way when I do modeling, so need you to do that. You need the practitioners, the people with their boots on the ground doing the work, and you also need project managers. I actually, that's, in full disclosure, I love being a project manager. It's one of my best jobs ever. I love it, even more than doing the communicating, so shameless plug for the importance of project managers. So when you have these cross-functional teams, you basically see those wicked, complex problems through more diverse lenses, more diverse perspectives. And when you get all of those different perspectives together, things make more sense. You understand more effectively those wicked problems. And this is really important, and this is why I put it in the middle, because this is like the meat of the 3. Know your audience. You have to know how to communicate with people. For example, if I am doing this talk on science communication to 6th graders, this is going to be really different. There will be one thing that will be exactly the same, and I'll see if you can figure out what that is, but it will be very different for 6th graders to seniors at like a convalescent home. It's going to be very different. So you got to know your audience, know their culture. That fosters trust. Trust is key. A quick sidebar, ever since I finished my dissertation, I started doing some work with tribal nations, indigenous populations, and that's a hard nut to crack because understandably, they don't trust us. I get it, right? But now, in my Rolodex, I have about 5 or 6 different people from different tribal nations that will call upon me and my expertise because they trust me. And forming those relationships is hard, it's complex, and it can take years. But when people trust you, they're more likely to work with you and believe what you say as a scientist. And I don't know if anyone knows Dr. Raj Pandya. He used to work for American Geophysical Union. He's now at Arizona State with Michael Barton, who is right there. And this is one of the things that he always told me. He's one of my mentors. When you go to these community meetings, you show up, preferably on time. Most importantly, you shut up and you, like Hansi was saying, you listen. You are there to listen. You are not there to say, only I can help you with this. No, you are there to listen. And bring good snacks. Always bring good snacks if you can. That's like a great, food is like people open up when you bring them food, especially when it's good. So speaking of which, knowing the culture, give you a sample example. Who in this room knows what a challenge coin is? I see one. Anyone else? All right. Sir, would you mind telling me your name? Steve Rabin? Sam, okay, forgive me. I'm like old and my hearing's bad. So Sam, question for you. What is a challenge coin? Yes. So I'm going to give the crib notes. So a challenge coin is something you see in the military, and it's a little piece of metal. It looks like Franklin Mint-like stuff. It's not worth anything monetarily, but it's worth a lot in emergency management, which has a lot of people from fire, EMT, law enforcement who have a military background. And what you do is it's a way to say, so Sam, guess what I got for you? I know it's hard to see, but this is a challenge coin. And if someone would mind bringing this to Sam, thank you. So that little hunk of metal in my field, the disaster emergency management, means more than any degree I have ever gotten. No joke. So I understand how important those are to the people in my field, and I actively trade them. I go to conferences sometimes just to trade coins, and I'll show them pictures of my collection, and they're so impressed. They don't really care about the doctorate or the MBA. Oh, you have a challenge coin from the White House. Wow. So that's a good sample example. And I will say, if anyone's like online, because I know some of y'all are, look at the Wikipedia page for challenge coin and learn about it. It's really a fascinating culture. I almost did my dissertation on it, but I never served in the military. So I felt like I would be kind of like a little bit of a poser, so I didn't. So knowing your audience, it builds credibility with you, and more importantly, the science that you're talking about, right? Science communication must resonate with the audience, not just inform. It must inform. And then storytelling. If anyone has kids, grandkids, nieces, nephews, is an auntie or an uncle, you probably hear kids say all the time, tell me a story. Everyone loves a good story, right? Everyone loves a good story. So I know there's a whole bunch of map nerds in here, so I'm not going to call you all out because it might be the entire room, but raise your hand if you know what Esri's story maps are. Okay, there's a few. Keep them high. I want to see. Okay, who's actually, of the people who have your hands up, who's actually used them? One, I see one. Okay, I might have a challenge coin for you later if you come find me, because thank you for using those story maps. This is one of the coolest, wonkiest things that is, in my opinion, an effective science communication tool. It's called Esri Story Maps. You can take all kinds of data, put it on maps. You can put qual data in, quant data, totally mixed methods. You can put in visual elements. So you see there's maps, there's high-res photography like I was talking about. The link is right there. I don't know if they're sharing slides later, but it's called The River of Resilience, Esri Story Maps. You could look it up. And they're really, really neat. You want to see me like nerd out? Get me on some story maps. So as a result, I found out somebody else has their own story map. So there was this organization called the Community Climate System Model, CESM's predecessor. Look at that. You already have been doing it and might not have even realized you've been doing it. So this is a large-scale model, right? Made into these wonderful looking story maps. So I challenge you all, let's make some CESM story maps, right? They're fun, trust me. So we're gonna go on to bridging the SciComm gap, a SciComm to science policy sample example. So as I was saying, I've done work in the water space, work for the city of Atlanta, I've done SciComm, and so I got a little tiny piece of funding to do some SciComm to better inform science policy issues in the city of Atlanta. And so what I did is I produced and animated my first short film. Yes, I did. It was so much fun. Called it The Attack of the Evil Fatbergs. So this is a science communication, a SciComm product, an animated short film that impacts and informs science policy. And that was specifically drinking water infrastructure, which we talked about. So I'm gonna actually show you the 2-minute film if we have time. But just in case the technology gods do not like me today, I want to give this to you. It's on YouTube. The QR code should work. There's also a bit.ly, a short URL there. And so let's get into it. Fingers crossed. Everyone cross their fingers. Let's see if it works.
There's a monster lurking in your plumbing, and you may have been unwittingly feeding it.
In most kitchens, it's common to find fats, oils, and grease. Unfortunately, in many kitchens, these fats, oils, and grease end up going down the drain.
The hungry fatberg waits to feed on these fats, oils, and grease. The more you pour, the bigger it grows.
Until eventually, or worse, all these little fatbergs may join forces to clog pipes backing up sewer systems. Fatbergs threaten our water supply by dirtying water and straining water infrastructure.
What can you do to fight fatbergs? Well, I thought you'd never ask.
Responsibly collect your fats, oils, and grease. Safely dispose of them. Together, we can defeat the fatbergs.
That's the so what. That's my name. Well, thank you. So I was watching the crowd, and I always there's a young lady here who's wearing a black and white shirt. You look like you've gone back to childhood, and it's like Cartoon Saturday here in the United States. See what that did, that 2-minute film, right? I went and got the money from AGU and from the Union of Concerned Scientists. I think I directed and produced it for about $800 to $1,200. I mean, does that look like that's like that cheap or inexpensive? No, but I figured out a way to make it work. So thank you for enjoying my film. And if you do want to look at it, it's on YouTube. So just wanted to say that. So recap, getting towards the end of Act 2, my act on communication. So science and the science that CESM is doing is important. So is getting the message about that science and what it can do. The so what, the science communication is also important. So effective science communication is essential to translate that data into action. So a quick conclusion We should always ask ourselves questions as scientists, right? That's what we do. That's what we're in the business of. When you're doing the SciComm thing, there's just a few questions here you should ask yourself. Who is your intended audience? Because again, you got to know who your audience is, right? What barriers do you face in that communication process, and can you overcome those? How are you going to measure your successes? One of the successes of my YouTube video is I have X number of hits. That's not really why I did it, but that's like a measure that you could like use, right? And what's the best way to tell your story? Sometimes small, intimate lectures like this are the best way. Sometimes an animated short film is not the best way. You have to figure out what it is that works with your audience, right? Think about, like, for example, if you speak more than one language, if you're ESL, you're immigrants, a lot of times video works really well because it's kind of universal, even without like language in it. So you have to figure out what's the best way, and then how can your SciComm strategy support science through actively engaging with your stakeholders. And thank you for your time. And feel free to ask me questions. And it's so weird. Usually when I speak, I walk around, so I'm trying to stay in the same spot. Oh, no worries. This is a beautiful podium to have.
Hi. This is Ali, from graduate student from UMass Lowell. I was thinking, do you believe that scientists really fail to communicate science? And if we failed, what lessons we have learned from that failure? And do you think also, my second question is, like, who are the audience, and we should like proactively engage in churches, or we should like open the university? What we should do to fill the gap, like for the failure that we have, like if we have.
To bridge the gap, as Hansi and I were saying, yes, thank you for that shameless plug. So first of all, I will say, and I could probably say this about everyone in this room, I don't think any of us ever had a science communication course. As an undergrad, grad, no. It's not something that we're trained to do. For me, I got lucky. I was at a university that had a pilot program with the theater department, and we actually had a SciComm pilot course. Now that is a course that is offered at that university, but that was like a one-off. We didn't even think we'd have funding to do it. So we have to realize, number one, we're not trained to do this. It is important, but we don't have the training. So a lot of times we're gonna have to go out and find it for ourselves. There's a lot of SciComm tools online now. AGU has a Voices for Science program. Unfortunately, there is also an NSF-funded program for scientists of color that focuses on science communication that got the axe, so that's no longer around. So it's going to be harder to find it, but it's like we have to figure out where those resources are, whether it's just connecting in small informal groups, like just, hey, look at my slide deck. Does this look good? You know, is there too much stuff on the slide? That's a basic SciComm thing that we can do to help each other. And then the second question was about your target audience, right? Target audience. And it was about trying to identify them. Is that what that was?
I was trying to say we have failure in science, like presentation, how to like that failure. If you think that was failure, what we can do and what we should change, and should we find like specific target or specific group and audience that will be proactive in churches, what we like can do to figure out that for the future what doesn't.
I think the main lesson we should learn as scientists, whether we're bench scientists, social scientists, earth and space scientists, we're not perfect, nobody is. We are fallible, humans are fallible, it's by design. That's why we have so many failures in things that we design, because we are fallible and anything we design will be too. But I hate to quote Will Smith after what happened on that stage, but he has a video out, and it's basically about the concept of failing forward, learning from your failures. There's also, I think, a Chinese proverb that a cousin of mine told me. It's like, you get knocked down 7 times, you get up 8. So you have to keep plugging away, but we also have to be very self-aware. We have to be like, yeah, this messed up, I'm gonna do better next time. you can learn more from your failures than your successes. I can definitely attest to that. Does that help answer? Did I answer it? Good.
Great. Thank you. Thank you, Paula. I do like the idea of an animation. I've always thought it'd be fun to try to animate what actually CSM is, just even for our own sake. Could be kind of fun, yeah. Yeah, I'm not sure how we do it. Okay, so then our final speaker in this session is Michael Barton. Michael Barton is a complex systems scientist in social change at Arizona State University. He's also the executive in social change at Arizona State University. He's also the executive director of the Open Modeling Foundation, a global consortium of organizations to promote standards and best practices in computational modeling across the social and natural sciences. Michael's research centers around long-term human ecology, landscape dynamics, and the multidimensional interactions between social and biophysical systems, integrating computational modeling, geospatial technologies, and data science with geoarchaeological field studies. So Michael, welcome. Well, there's a pointer if you
advance. I don't think it'll advance because it's on Zoom, so it's okay.
Okay.
We're okay. Where's the pointer? That one? Okay.
The pointer sort of sometimes works.
Oh, it's on. Oh, it's online pointer. Yeah. I can use my mouse.
Okay.
Cool. Yeah. So I want to thank Dave and the leadership of CESM for inviting me here today. It's good to be back. It's a real honor to talk to you all, especially at this 30th anniversary here. I do want to echo something Paula said, and that is no collaboration or communication between the people talking this morning, no prompting from Dave, and all of us ended up talking about different dimensions of how we need to bridge a perceived gap between the kind of climate science that all of us in this room do and the human systems we all live in. And so I'm going to continue with that theme today. I do have to say that CESM is a success story, a scientific success story, starting out actually more than 30 years ago in a lot of the work. It was a computer tool for a few nerdy scientists, and now it's grown from just being a model of the atmosphere to an Earth system model, informing, as we've heard already today, a wide range of different kinds of global policy and global action. It started out as an atmosphere model. How and why did it evolve to an Earth system model? Well, it was because people doing this recognized that the dynamics, atmospheric dynamics, are influenced in a lot of important ways by interactions and feedbacks with other components of Earth's critical zone. Oceans, land, sea ice, a lot of different things. And we've heard about that already. We'll hear more about it this week. But how many here are confident that we fully understand all the Earth systems and we're modeling it? I don't see any hands. We've been studying atmospheric circulation for over a couple centuries, and we still don't understand all the processes, and we either can't model or choose not to model everything that we do know. And this is the case also for the physics of oceans and thermal properties, its biogeochemistry, and the land. But in spite of all this, right, I think everyone would agree that the kind of modeling that's done with CESM has proven extraordinarily useful for understanding past, present, and future of many different aspects of the Earth's critical zone. And of course, in addition to making a lot of important scientific contributions to understanding the atmosphere and its dynamics, it's demonstrated a lot of other things, like the impacts of of greenhouse gases, right, on current and future climate, assessing the impacts of anthropogenic climate change on food production, urban health, urban heat, environment, infrastructure, things we've already heard about in a couple of the talks this morning. And like the atmosphere, oceans, land, and ice, there are important feedbacks between human society, human systems, and all the other components of Earth systems, but these are not modeled in CESM or any other Earth system model today. So I need to remind you all, right, that the Earth system is a coupled natural and human system. That's the one we live in today, right? And I'll put out, in addition to the Earth system modeling, CSM modeling, there's some factoids. I love little factoids sometimes. This is one of my favorite web comics, XKCD. If you're nerdy and you don't know XKCD, you should look it up. So the mass of all of us and our domestic animals is greater than all terrestrial vertebrates combined, right? And our mass and our agrobiomass, over the 3 billion tons, is more than all the vertebrates on land and the sea. And then the stuff that we've made and used, all human mass, exceeds all of the planet's biomass. And then the energy that we're producing and using now is coming close to being the same as the total planetary net primary productivity, right? Almost half of the habitable land is in crops or pasture for our food. Over 30% of all forests have been cleared in the Holocene, and there's a bunch of forests that are still there that were cleared and have grown back. Our coastlines are engineered. Over 70% of fresh water is used for our food production. There's more nitrogen cycled by human activity than non-human processes, and more sediment transported by human processes and than non-human processes, right? So if we accept CESM simulation results, all this work that's been done, if we accept that global scientific data of the impact of over 8 billion of us on the atmosphere, land, and oceans, if we accept the data that people are significantly impacted by climate, that we are affected by that, and that our decisions and actions respond in many different ways to changes in the environment, we have to acknowledge that the way they are now, our system models are missing a critical component, just like they could be missing the oceans or the land, right? And the simulations that we do, no matter how important they are and how valuable they are less reliable and useful than they could be otherwise. So how do we begin to bridge this gap between the missing human systems in our Earth system models? There's a project that I've been a part of that's been working with NCAR, Louisiana State, and Duke University over the last couple of years, generating actionable research to investigate combined climate intervention strategies for stakeholder use. And the main part of this, headed by Peter Lawrence here at NCAR, has been trying to use CESM to model the environmental and social impacts, potential impacts of different kinds of climate intervention strategies. So everything from different kinds of decarbonization to solar radiation management. So what's that going to do to the planet? And I think Peter's going to talk about some of that this afternoon, some of this work. Our role at ASU, the main part of our role, has been to try and develop a prototype modeling environment to bridge this gap for simulating interactions between the biophysical systems and human society for climate interventions. Basically trying to come up with a proof of concept for a new kind of modeling component that could be coupled into CESM and coupled with its biophysical components, right? And so our project focuses on climate interventions. That's what the funding was for. But our broader vision has been to try and develop components that are potentially flexible enough to simulate other aspects of human systems that are relevant to Earth systems, right? And so what we want to do is try to come up with this platform where you could carry out experiments on the potential and consequences of feedbacks between climate impacts, right, including the impacts of climate interventions, and human systems decisions and actions, including climate intervention policies, so we can simulate those and model them in ways that you can't do now, right? So how many here believe that in the near future, climate intervention strategies, geoengineering is going to be done in this nicely unified world, scientifically guided for optimum human benefit, right? Yeah, neither do I. But this is the way that Earth system modeling is done today. And this can be useful, right? So this is useful to get an ideal kind of outcome, right? But it's imperative to also understand the consequences of climate intervention policy in a more realistic, non-unified world in which we live, right? So what we've been trying to do in this project, Societal Dynamics Model for Climate Interventions, is to come up with a platform that recognizes that climate intervention policies and strategies will be driven by policies at national or supranational levels, responding to significant climate-driven impacts on regional populations, not global temperature averages, right, and sociopolitical conditions. So it lets us try to represent, at least in a simple, in a beginning way, diverse geopolitical actors in different societal scales, right, in different geographic locations that experience societally relevant impacts of climate change differently and that have different kinds of goals and capacities for action. So how are we going to do this? What we've tried to start to do is create a gridded multi-agent formalism with this kind of a model that could interface with CESM inputs and outputs more easily and more flexibly, because this is the kind of formalism that CESM uses. Right? So we have grid cells, groups of grid cells that can represent human systems at multiple scales, from cities all the way up to nations and economic blocks. A cell, just like in the land model, can contain subdivisions representing agents at finer spatial scales. Uh-oh. There we go. Sometimes it doesn't advance. This kind of modeling representation lets us represent social actors, either all the way from individuals to groups, right, as heterogeneous agents with different histories, biases, contexts, relationships to other agents. And this allows these different agents, grid cells, groups of grid cells, right, to implement algorithms to respond to conditions from simulated biophysical and social worlds, just like CESM grid cells do in terms of independently activating algorithms to represent from thermal conditions in adjacent cells and things like that. Right? Because grid cells, agents, right, are in different geographic space, they can experience geographically different simulated conditions. But they can also do some things different than CESM normal grid cells in that they can also interact with other agents, grid cells, in other parts of the simulated world, not just adjacent ones. So teleconnections, you can think of that. This kind of formalism lets us try to simulate potential impacts of climate intervention strategies in this more realistic social world, where climate intervention policies are carried out by different geopolitical agents, each with different agendas, and they may be working with together, or they may be working against each other, or working independently. Decisions of each of these agents on climate interventions can be influenced by unique, different combinations, right, of the simulated biophysical conditions that they experience, climate impacts, right, as well as actions of other agents. And their choices can also potentially, maybe or may not be influenced by CESM simulations, scientific guidance on what may happen if they take these choices. So how we're thinking about doing this, and we've done kind of initial work on this, is that the modeling will be able to connect with CESM through loose coupling so that CESM has starts and stops the simulation at regular intervals, like annual intervals. During the simulation pause, each agent can read and parse simulated conditions from the biophysical world that comes out of CESM, from CESM output files, and then decide on a climate intervention action, or nothing, do nothing. Right? And then this platform aggregates those different decisions together into a forcing file that goes back in and alters the parameters of CESM on a restart, and do this on an annual basis. So here's a little schematic to give you a sense of how this works. What we've done now is it's coded in Python. It's a modular architecture, so it's very flexible. We have this loose coupling with CESM using netCDF files for input and output. We're designing this with CESM in mind as a way to couple it with this, but our goal is to make it flexible enough that it could be used with any other Earth system model that can be stopped and restarted and used as netCDF or some other kind of file for this kind of I/O and coupling. We've also been exploring the potential of using this with Earth system modeling emulators, and you can hear more about that. I think on Wednesday there's a paper on that coming up. So this is just another schematic of what each geopolitical agent does, and this is a group of cells at, and to be convenient to work with CESM, either with the resolution of CAM, the atmosphere model, or the land model, that corresponds to a geopolitical entity like a nation state. So if you can imagine the grid cells that are equivalent to, we've got Russia there, or Brazil, or North America, right? So each of those agents will parse CESM output, right, for the corresponding cells. Right? And then it will also parse information about other geopolitical agents, what they're doing, come up with a decision or action, and then these is combined into a forcing file. To get started with this is a big job, right? So we have to start somewhere. We're focusing on solar radiation management, specifically stratospheric atmosphere injection, for a couple of real pragmatic reasons, right? One is that an SAI forcing approach is already worked out. So these have already been worked out, and a Python controller scripts have been worked out for the ARISE simulation. So they're already something to work with. And this SAI, if it's implemented, can have relatively near-term impact as opposed to growing forests or something, which is a longer-term impact, with the potential for benefits and risks in the relatively medium term, and that they can vary by place. So something that's good for one group may not be so good someplace else, and vice versa. So there's these differences. And so it makes simulating SAI in this more realistic social simulation especially useful. We're also looking at, for an impact, we're just starting with one impact and using extreme heat. Again, this is something that's likely to have growing impacts in the future, and something that can be affected by stratospheric atmospheric aerosol injection. Right? And so right now, rather than just take temperature, we're interested in extreme heat that could actually have impacts on human society and move the policy needle. And so we're using an index developed by Jenny Vanos, and it can be calculated from CESM input. And she has like two different kinds of indices. One is livability, and this is the ability to actually do stuff outside, so it has economic impact and things like that. And then survivability, and that's the risk of dying from heat stroke, things like that. We've combined those into a single impact matrix. You can kind of see here. And the idea is it pulls in, we can calculate this from 3 different outputs from the atmosphere model, and then we can calculate the daily heat stress, aggregate it for a year, and then compare it to a reference, a mid-20th century reference amount, and then weight it by population to find out what the impact is per country. This would actually go into the policy decisions at this point. And what are the decisions? Well, there's a lot of different ways of simulating human decisions that people have worked on for a long time. Right now, just to get started, we're doing a simple kind of deterministic probability of a decision. So we have information you can see up there. I'm not going to bore you with the math right now. You can look at it later if you want. But the probability of investing in a particular climate impact. We've thought about making that more sophisticated by taking a Bayesian approach, where each kind of information will update an actor's decision making and increase or decrease the probability of investing in different climate intervention strategies. And then kind of further out there, but it seems important in the discussion we've already had this morning, is thinking about large language model impersonation, that's AI, and with the idea that contextualize and prompt this large language model to impersonate a different geopolitical actor, a different country. And so you could give a prompt like this and do it. We've done a little bit of experimentation with that. So here's just a little video to kind of show you a little bit how this sort of works. I have a couple of these. And on the left, you can see this is the effect of picking a particular SAI injection point and what its impact is on different places in the world over a 10-year interval, right? And on the left, I guess the left up there, say it. And on the right, it's what this would look like if different actors chose different injection points. Just to point out that there's different effects depending on what kind of choices get made on this. And then this is a quick simulation of, or a video of a simulation where we've just created 6 different likely actors, large countries or country blocks, and then they perceive heat impact, and that gives them a probability of wanting to invest in SAI. And you can see how this changes as the colors change on on the outlines of the countries here. And you can also see the actual heat impact changing in the world there. So this is what the actors experience. Right? So the plan, right, would be to include other extreme impacts beyond heat, extreme drought, agricultural failure, extreme storms, floods, wildfires, sea level rise, things that likely would affect policy in different ways. And then, of course, have other climate intervention strategies. This whole project was to try and simulate the impact of up to 8 different strategies, everything from reforestation to SAI and some things in between, right? But in the future, a platform like this one perhaps could alter other CESM parameters using the same approach to change things like greenhouse gas emissions in response to societal decisions. So the idea is to kind of create this framework that could be used for a variety of different kinds of things in Earth system modeling. So I think it's in the world that we live in today, especially right now, it's more than ever important to try to represent Earth system models, human systems and Earth system models. You know, the changes that we are making to Earth systems are generating many, many different kinds of extreme events, ones that are hard to predict, and these have significant impacts to human survival and well-being, things that actually may change the policy needle in some ways. At the moment, human society globally is getting less unified instead of more unified, and with the potential for, I think, significant cascades of societal transformation, to be a little bit euphemistic about it. And there's a growing potential for independent climate intervention actions by global actors that want to seek relief from extreme impacts in some way or score political points locally. So these things are all, I think, happening, which means we need to at least try to understand what the potential is in this looking forward. And so we need to recognize this is a serious issue. So a number of people have written about this recently. And we need I think, a concerted, collaborative effort to try and develop these kinds of representations of human system dynamics within Earth system models. And so this is, I think it's important, especially in a collaborative community like this. Right? ASU has been doing this as part of this project, right? We can't do this alone. This is obviously not something for a single university or anything else. And we're at the end of our NSF funding for this, right? So we've gone as far as we can go with the current funding, and in spite of how important it is, the potential for getting new resources to continue any of this kind of climate work are diminishing rapidly. We all know that, right? But even if they weren't, right, in a different world, even with significant funds, right, trying to create this kind of a prototype to simulate more climate intervention strategies and other human system dynamics inherently will take a large-scale collaborative effort. You know, keep in mind, CESM3 that we heard about this morning builds on like 6 decades of developing global climate models, right? Global circulation models. So we know that these things take time and effort and benefit from collaboration. There are a lot of other groups besides what we're doing at ASU to think about modeling this kind of things, that have thought about how to model the interaction between human systems and Earth systems, right? So this is going on now. There's a lot of stuff out there. If there was a framework for more collaboration and coordination together, a lot of the work that's ongoing right now could accomplish a lot. The kind of working groups that are here at CESM are recognized umbrellas for this kind of collaborative research and for sharing knowledge. So they've been vitally important to the development of CESM as the world's premier Earth system model. There was a societal dimensions working group that was created a decade and a half ago. Unfortunately, it dissolved under conditions similar where we face now, but they're not quite as bad. And this working group can't be revived as it was before. I mean, that was 2011. That's a long time ago. But we still need some kind of a new working group framework, I think, within the Earth system modeling community to support the kind of collaborative science that's needed to develop a human systems component, and bridge this gap between human systems and Earth systems. And so, as I would say, like I said, I think the planet's most sophisticated Earth systems model, and perhaps the largest collaborative group in developing this system model, and I want to challenge you all to maybe try to lead the way in organizing this kind of framework that can help bridge this gap in human systems and Earth system modeling. So thank you very much. Thanks to all the people that collaborated with this, and I have a reference section if people want to see the slides later. Thanks.
Questions at the end?
Thanks for an interesting and provocative talk. We struggle with communicating sometimes the uncertainty in the results of our physical models. There are huge financial incentives for predicting the evolution of human systems, and it seems to be very difficult to do, even given those incentives. So I'm wondering if, in the fusion of these two systems, if you foresee an explosion of the uncertainty of future scenarios, and then how do we communicate that? You know, often we like to give error bars. Are you thinking more that you talk about representative storylines? How do you communicate that huge space?
So the first answer is yes. I would expect an explosion in the amount of uncertainty and things like that. Having done a much smaller scale coupling of human systems and physical systems, that is indeed what happens. Communicating uncertainty to others, especially outside the scientific community, is difficult. I mean, this is reality, right? I think one of the things that we need to do is be honest, and this includes for the kind of climate modeling scenarios that we do now, the storylines, you say, I mean, that's one way to do it, is to point out that we're not predicting the future of human society. We're not predicting the future of climate on the planet. What we are doing are trying to anticipate potential futures given a series of things that we do, of incomplete modeling that would help give us guides. So I think I tend to try and really try to talk about this kind of work as carrying out experiments on potential outcomes given a certain set of conditions, rather than say, this is what's going to happen and you've got, be prepared for it. So, but this is a difficult thing, and I think it clearly, as the other speakers this morning have pointed out, it's difficult for the kind of Earth system models that we're producing right now is to communicate these things. I think adding humans to it make it more complicated, but also potentially more appealing and maybe more useful to more people on this. We have to acknowledge the limitations.
Thank you. I had basically the same question, but now I want to be more specific. So we've been prescribing human system by designing emission scenarios.
Right.
And that's basically a simplified way to quantify the uncertainty associated with human activities. And I guess my question is, how do you envision in the future, what factors in the human system are important to quantify the uncertainties?
I mean, that's a really important question. And it echoes the same questions we wrestle with all the time in biophysical models. We don't represent every single thing that's going on. We make choices, and sometimes we make the wrong choice. but we try to make useful choices on these things. And so for the kind of little prototype we're doing now, I mean, horribly simplified. We're just talking about one set of decisions, one kind of impact, and one kind of decision. But I think that's still useful. And so I think the important thing is to move beyond simply thinking of people as a parameter to input into these models, but as to begin to represent the feedbacks and interactions with people, even if we do it in a simplified and unrealistic way. It adds, I think, much more value to the models that we do. So thanks.
So my comment is similar to the first two ones. So if you move the scenario uncertainty into the model, the IPCC projection will be just one big distribution, and you take human agency out of that, and it'll be difficult to communicate what good and bad is. So taking human agency out, I think, is a very dangerous thing to do.
I'm not quite, I understand your question.
Because you're moving the uncertainty associated with human activities into the model. And if you do an IPCC projection with this comprehensive human natural systems model, into multiple scenarios, you'll just get one wide spread. And it'll not be clear what we need to do because it's a complex model.
I think we need to think about it maybe in a slightly different way. And so again, we're not predicting the future of human society. The question is to say, what would happen under the following circumstances? And so we end up specifying the boundary conditions, just like we do in physical models. We specify boundary conditions for human systems. We can't model the individual behavior of 8 million people any more than we can model the behavior of fish in the ocean or the molecules of nitrogen in the atmosphere. What we can do is try to say, these are, as you were asking here, these are important dimensions that are worth asking. What would happen, what might happen if these dimensions were set in these ways? And so think about it in terms of setting up experiments and trying to represent the great uncertainty in knowing what global human society is going to be in the next decade, much less several decades.
Yeah, thank you, Michael, for for a great, inspiring and interesting talk, thought-provoking. Group sessions after lunch, and then at, I think it's around 4:30, 5 o'clock, we have the poster session and reception. So look forward to seeing you all there. Thanks again to all the speakers for a great session.
Righty, are we good to go? Yeah, okay. So on behalf of Cecile Henne, our AMWG Science Liaison, and our two external co-chairs and myself, welcome to the summer version of the AMWG. During the summer meeting, we are not as model development centric as we are during the winter meeting, so I just have one slide here. If you need a refresher of what's new in CAM 7 compared to previous versions. As Dave mentioned, we're in the final stages of development. We're only allowed to make changes or major changes in the model if they really reduce biases, and they need to be approved by the SSC. So as far as I am aware, this is CAM 7. In terms of our shallow convection schemes here at CLUB, we're still using CLUB, but we now have prognostic momentum fluxes in there. We're still using ZM deep convection scheme. There are some changes necessary to deal with high boundary layer resolution. Pumas here is, I could also call it MG free. There has been some updates to how some processes are handled. Last we looked at climate sensitivity. I think it's those changes that reduced climate sensitivity compared to CSM2. Radiative transfer model has been updated, but it's still ROTMG. We're using MAM4 aerosols since we have specified oxidants, but if we one with stratospheric chemistry, it's MAM5 that's active. Then there's been a number of changes in the world of parameterized gravity waves and drag. So in particular, we now have a new source of gravity waves in the model. It really helps some of our biases. After free model versions with the finite volume dynamical core, we've swapped it out with the spectral element dynamical core. We've increased the boundary layer resolution, and also we have now raised the lid. So for a couple of decades, the top has been around 42 kilometers. Now we have an 80 kilometer top. Horizontal resolution still stuck at 1 degree, but we also would like to develop a high resolution version of CESM at a 1/4 degree as well. And then in the other components, major change, the ocean changed to MOM6. Luckily, Dave showed a lot of these slides here because my slot is only 6 minutes. I'm just going to show one science result here. This is the zonal mean wind in the 80 kilometer model. And as Martina has plotted here, our wind biases in the southern hemisphere here compared to ERA 5 look really, really good. There's still some work to do with the northern hemisphere jets. Dave showed this slide with the QBO, so I'll skip over it. He also showed this slide from Adam Harrington on the Greenland mass balance. But I would like to highlight this. So we spent a lot of core hours before AGU last year running 1/4 degree simulations, and we would like to make the community aware that this data is available. So we ran the high top and the low top version, also reverted to the CAM5 vertical grids. We experimented with the club momentum fluxes and also did plus 4K SST experiments. Dave showed the results from some of these simulations earlier today, but if you would like to dig into this humongous data set, please follow that link up there and or contact Cecile. Alrighty, the way we've chosen to lay out this meeting here is to give everybody an oral slot. So if you take 90 minutes divided by the number of participants, you got approximately 12-minute slots. So speakers have 10 minutes and then 2 minutes for questions. Please notice we need to finish on time because we have the group photo here at 3 p.m., so during the break. And in the interest of time, let me switch to the next speaker and not take questions. You can grab me in the break if you want to chat about something. But our first speaker here is Vince Larson. He's going to talk about the use of tuning diagnostics to understand CAM's behavior.
Great. Well, thank you so much for giving me an opportunity to talk. My collaborators on this are Ben Stevens, Jun Guo, and Luis Hasenauer. It all started innocently enough. We wanted to reduce precipitable water, which is TMQ in CAM's parlance. And so we shut off Club's background diffusion. So Club's background diffusion, it's sort of a historical artifact at this point. It was introduced many years ago in order to improve marine stratocumulus, but it doesn't really do that anymore. And so it's sort of an ugly wart that I would like to get rid of in the model. And it has a side benefit: if we shut it off, it reduces TMQ and improves it. So if we run default CAM, this is model minus OBS here, we see that it has a moist bias, a pretty strong 1.39. If we shut off Club's background diffusion, which just is lofting up moisture and heat using a simple eddy diffusivity while Club's higher order closure moments are going on, then the moisture bias is reduced to 0.22, which is good, but it leaves this dry patch here in the Western Pacific and in the Indian Ocean, which is bad. So we decided to retune using a semi-automated tuner called QuadTune, and that helped, but biases still remain. So this is where we were with this dry bias here, and then this is where we end up after tuning. The dry bias in the Indian Ocean is reduced to some extent, but the dry bias over the Eastern Pacific is actually made worse. So why doesn't tuning parameter values remove these model biases? It feels like parts of the model structure must be preventing further improvement. There's just a model structural error. And the question is, can we get at some hints about where those model structural errors lie by exploring the tuning trade-offs? Okay, so in the remainder of the talk, I'll talk first about tuning trade-offs in cloud brightness, in other words, shortwave cloud forcing, and then I'll talk about tuning trade-offs in surface precipitation, aka PREC-T. Okay, so after tuning, the shortwave cloud forcing improves, in other words, the clouds dim in the southern hemisphere storm track. So this is where we were when we had shut off the background diffusion, but before tuning. And you can see here in the southern hemisphere storm track in this yellow box, there's a very bright region. It's so bright it goes off the scale there. But after tuning, then it dims somewhat, which is good. Likewise, in this pink region off the coast of Japan, it has this ugly brown shade here, which after tuning is turned into a much more pleasing taupe color, which means it's dimmed as we want. But the problem is here. So over here in the Peru stratocumulus region, it looked fine before tuning, but retuning makes it too dry. So then the question is QuadTune, this automatic tuner, sacrificing this stratocumulus region in order to improve the storm track or the coast of Japan? And it's kind of hard to tell looking at this. Both of them are too bright. They both get dimmer, so it's not clear what the tension is. But we did some experiments. These involved basically finding many sets of parameter values, each of which produces a good climate. So it's sort of a calibrated physics ensemble. Each scatter point corresponds to one parameter set. And then we just looked at how these behaved in these two regions, off the coast of Japan and off Peru. And we want all the points to lie on this green triangle of no bias, which would mean that we can fit both regions. And in fact, we do find some points that are pretty good fits, so that's good. It doesn't seem like there's a trade-off between Japan and Peru here. But with the storm track, it's a different situation. Here we want at least one parameter set to land on no bias, but in fact, there's this trade-off. We can either fit Peru or we can fit the storm track, but there's no single parameter set that matches both regions. So it feels like there's some basically model error involving those two regions. So why is that? We can get some insight by looking at this chart of biases in different regions. So what we see is in the storm track, there's a very strong bright bias to begin with. That's the vertical black bar. And in Peru, there's less of a bright bias, but it's still a bright bias. But after tuning, then the clouds are dimmed and brought closer to zero, where we want them for the storm track, and that's the end of this horizontal bar. But then, unfortunately, Peru is over-dimmed. It becomes too dim. And we can look at how the parameters are achieving this dimming. There's a parameter C1, never mind what that is, but it brightens Peru, it brightens the storm track. We have C8, that dims both. We have C14, that dims both. The parameter dependencies are very similar. So red, red, blue, blue, green, green, and so on. So you can kind of see that it's sort of hopeless to bring the storm track down to the proper brightness without over-dimming Peru. And this surprised me, frankly, a little bit, because I think of storm track clouds as being very different than marine stratocumulus clouds, and I was expecting to find a parameter that could regionally tune the storm tracks, but I haven't found it yet, even though Adam has given me lots of helpful hints about microphysical parameters and ZM parameters, so I'll keep working on it, but this is sort of the state. Now, off Japan, it's quite different because the parameter sensitivities are different. This blue is different than that blue. This lime is different than that lime. So we have some hope of tuning them independently, and in fact, we do. Okay, so now if we look at the precip biases, the precip has sort of a similar trade-off between the Indian Ocean and this Eastern Pacific ITCZ region in purple here. So the Indian Ocean, this is before tuning, starts off with not enough rain, but then after tuning, it's mitigated to some extent. The Eastern Pacific ITCZ starts off fine before tuning. After tuning, it has too much rain. So it sounds like the similar sort of bias that we were seeing before, where the initial biases are very different. We, tune up the rain everywhere, and then that makes one region better and the other region worse. Okay, but what's interesting here is the Indian Ocean here is too dry. Off the coast of Japan, it's too rainy, and both those biases improve. So that's a very different situation. Something different is going on there. We can look at that, and we can see, okay, Indian Ocean and Eastern Pacific ITCZ, they have this sort of trade-off. We'd like them to be here, but we don't have a single point that does that. For off Japan and Indian Ocean, it's very different. If you improve one region, the rain in one region, you improve the rain in the other region, which is very nice. That's quite handy. Why is that? Well, we notice here that the Indian Ocean, it's too dry to begin with. It becomes moisture through tuning, more rainy. Off Japan starts off too rainy and becomes drier, which is beautiful. And these parameter values, they have a remarkable similarity, but with the opposite sign. So this pink is like that pink, this lime is like that lime, pink is like that pink, and so on. And what seems to be happening, so the very same parameter that makes Indian Ocean more rainy makes off Japan drier. And what seems to be happening is basically the vertical velocity is very tied up in this. There's an amazing correspondence between surface precip and vertical velocity in these particular runs. And the circulation is changing so that basically we're getting more ascent in the Indian Ocean and more subsidence in the coast off Japan, which is just what we want. And so then that's what seems to be helping us here. But there's still a problem with the Eastern Pacific ITCZ. It seems a little strange that, for instance, this Cape limit parameter, it both boosts the precip in Indian Ocean and ITCZ. So I'm not quite sure why that's happening, but again, we're working on it. So conclusions are, if we tune, we can dim the storm tracks, but in so doing, we dim the Peruvian stratocumulus too much. So we need a parameter that's more specific to the storm tracks. But in the process, we learned something about the physics, namely that the clouds in the storm track and in the marine stratocumulus regions respond remarkably similarly to each other, which was surprising to me. But then also we learned that tuning is very much complicated by circulation changes. And then we also need to deal with the Eastern Pacific ITCZ. So yeah, thanks for your attention. Okay. Thank you. document it. Oops.
Hi, very nice talk. I'm a grad student, Papu Paul, from University of Illinois. My thing is like, as you are tuning, it improves one region and it degrades other region. So why not we are trying to make the localized parameter for different region, like the MPAS model, where we increase the resolution in one region to improve the model performance. Why we are not doing the same kind of thing for parameter tuning to make the parameter for regional? Yeah, this is the parameter set for Eastern Pacific. This is the parameter set for Western Pacific, and so on and so forth.
Yeah, it's a good question. I mean, we want to keep the model simple. And then in addition, the hope, we don't want to sort of bake in a certain change in a certain region, and maybe in a different climate, that region has shifted, or, so we don't want to force the answer too much. But we do have some parameters that are specific to land or ocean, so.
Thank you.
So you alluded to this a little bit about what do you think about the hypothesis that if you want to make a differential change one region, like more precip in one region, less precip in another region, that you want to change the circulation through your parameter tunings. But if you want to, or if you do manage to just tune, like if you're just changing cloud parameters, like you're probably going to affect clouds the same way everywhere. Is that what you've seen?
Yeah, so that's what I see. So basically, when we want to tune the clouds, the parameters basically dim or brighten globally. So if we start with clouds that are too bright here, too dim there, we don't really change things. With the precip, it changes. Precip is more constrained, right? So if you have more precip here, you sort of have to have less there in an F-case type run. But it still was interesting to me exactly where the circulation changed, like over the Eastern Pacific, that apparently we didn't have the same subsidence that we enjoyed off the coast of Japan. So there's a somewhat local circulation, which is helping us in one place but not another.
Great, thanks.
Thanks.
Thank you, Vince. Next up is Ben Stevens, who is going to talk about cyclones and quarter-degree simulations.
Thank you. This is kind of an expanded version of a talk I gave at the AMWG winter meeting earlier this year, with some updates about some tuning we've done. I want to especially acknowledge Julio and Colin, because my experience is mostly with club at 1 degree, so cyclones at quarter degree is basically all new to me. So I'll bear with me as I try to convince you that we're doing better now than with Cam 7 than we were with Cam 6. So Cam 5 and Cam 6 both used a down gradient scheme for the momentum fluxes. As part of the work that I've been doing with the momentum CPT, we've now incorporated prognostic momentum fluxes into Cam 7, and you can see the equation for that here on the right. It's the full prognostic equation that you would get from the Reynolds stress tensor, with terms that are closed using Club's PDF, and other terms that are closed using standard pressure closures. So as far as the large-scale characteristics of what we're seeing in these quarter-degree runs, and these, by the way, are fully quarter-degree runs. They're not regionally refined. A couple of things I'll highlight are just there's too many cyclones. It turns out there's too many after an analysis by Collins Arzicki, but we do think that the prognostic momentum looks better in the East Atlantic than the diagnostic case over here. I know this is a text-heavy slide, but I wanted to give Collins takeaways because he knows more than I do. But basically, it looks like we're doing better even than CAM5 in some ways, and even with the diagnostic momentum flux version of club. But the prognostic momentum flux improves on that a little bit in some cases. So one of the things that, in particular, that he pointed out was that one of the challenges is that there's just too many tropical cyclones, about 2 times what the OBS would show. And so we were interested in seeing if we could maybe improve that somehow. And that's sort of what this last comment is about. But hopefully those of you who are familiar with tropical cyclones can take a little bit away from this slide. So let me move on. So these are some more recent runs that we've done now. The one on the left here is still a fully quarter-degree run, but it's now done with the ZM tau parameter reduced from 3600 to 1200. This is intended to reduce the number of tropical cyclones, and it does. It reduces the number of tropical cyclones by about 40% or so. And the numbers, if you look at them, are actually pretty close to OBS at this point when we reduce that parameter. And I just thought I would include this plot on the left since we started doing, I think this was the last of the fully quarter-degree runs we did. We started doing regionally refined runs, but this is sort of the corresponding case on the regionally refined side. Okay, so before, when we were just playing with the diagnostic versus prognostic momentum flux, I took a look at some of the smaller scale storm structure, in particular inflow angles and inflow depths is one of the things I looked at. And we do see an improvement using prognostic momentum flux. So you can see that the inflow angle increases by a few degrees in both the Northwest Pacific and the North Atlantic. And then there's a corresponding decrease in the inflow depth. So this is looking good. Although observationally the inflow angles are higher. I think observationally they're maybe in the low 20 degrees. Although Colin has said that for quarter-degree simulations we might aim for something more like 17 or 18 degrees. And so actually we are able to get a handle on that using one club parameter in particular called CUU shear. When we increase that parameter, it basically reduces turbulent production in the horizontal momentum flux equation. So we expect to see maybe a shallower boundary layer in that case, and that seems to correspond as well to an increased inflow angle in both basins again, and again with reduced inflow depths. So it's nice to know that we're able to get a handle on this using just a single parameter and get numbers that we like a little better. These are some plots that show composites of storms in the different basins. This is for diagnostic momentum flux. So what we notice here basically is that the prognostic looks a little better. The winds are sort of pushed, or the radial winds are kind of lower down in the column as where we would prefer them to be. And it's the same situation roughly in the Northwest Pacific. This is again just diagnostic versus prognostic momentum flux. So we see that feature where the winds are, the radial winds are lower. With some tuning, with using the reduced value of ZM tau and the increased value of CUU shear, I think we see that we're getting a little bit of a further reduction in the height of those radial winds. There is a caveat here. I wasn't able to use some of my latest results on the right-hand column here. I ran this experiment out for longer, which might, I think, improve the statistics, especially in the North Atlantic, where I think the N value is maybe a little small. but because of the computers being down, I wasn't able to get to that just before the talk. This is one of the last plots. So this is thanks to Collins Arzicki. He created this plot. I noted what the colors correspond to here in the text, but basically blue is OBS. Red is where we were with Cam 5. This is the pressure wind plot, by the way. Cam 6 showed a degradation in this metric. That's down here with green. If you look at the diagnostic versus prognostic cases in our updated version of CAM, they're kind of right on top of each other. It's the orange line and the purple line, if you can kind of see them. They actually are on top of each other out here, but you can sort of see them separated over here. So there's not much benefit, I guess, from turning on the prognostic momentum flux for this particular metric, but we do see improvements in other ways. Tuning CUU shear and ZM tau gets you this yellow line, which is a slight improvement on the high wind speed end. So yeah, basically the momentum CPT has made prognostic momentum flux the default in Chem 7. 2 preliminary 10-year runs by Cecile show a number of improved results when using the prognostic momentum flux versus diagnostic. We've learned that overproduction of TCs can be mitigated by reducing that ZM tau parameter. Prognostic momentum flux shows better results for inflow angle and depth. We also see improvements in the composite storm structure using prognostic momentum flux. Pressure-render relationships, there's still room for improvement there if we can maybe get a better handle on it with some tuning maybe. And then finally, yeah, tuning also further improves the inflow angle and inflow depth, yeah, with that club parameter. So that's kind of where I am currently with the tropical cyclone stuff at quarter degree. Thank you.
You remind me of the improvements that we see with the prognostic momentum fluxes. You said you weren't seeing in the wind pressure relationship. Where else?
Oh,
Yeah.
well, in the storm tracks we see it looks better in the East Atlantic. I think there were maybe too many tracks over that region for the diagnostic, but the prognostic looks better compared to OBS. Also, the inflow angle and inflow depth look better with the prognostic momentum flux, and the composite, the contour plots that are averaging over many storms look better. The radial winds are closer to the surface, which I think is what we, as I understand it, that's what we like.
Staying on schedule. So my colleague here, this is not João Teixeira, this is Adam Harrington. He's going to give a presentation on the Club MF project.
Yeah, so thanks everybody. I'm going to talk about the Club MF approach, results from the Unified Mixing Parameterization CPT project. So the Club MF is just one leg of that project. João Teixeira is the PI, and yeah, unfortunately he wasn't able to make it here today, so I'll be giving this talk for him. The NCAR PI is Julio Backmeister, my advisor, and Xianan Jiang also contributes to Club MF. He's at UCLA. So we'll get started by stating, which should be obvious to a lot of us, that convection occurs over an extremely large range of scales in the atmosphere. This schematic here is showing starting over here in the region of the eastern boundary currents, you have a colder ocean with a stratocumulus top boundary layer. As you progress towards the tropics, the SST is warm and you end up with a shallow cumulus transition. As you go further down into the equator region, you end up with your trade cumulus, mid-level convection, and all the way to your ITCZ where you have deep convective anvils. And so we seek to try to parameterize these transition of different convective regimes in some way of a unified way. There's also the temporal transitions in convection over land. This is the diurnal cycle problem that a lot of GCMs struggle with, where the convection sort of shoots off too early in the day. And so we'll seek to improve that aspect. And in particular, current GCMs usually parameterize these different convective regimes using different schemes. And so you'll have your PBL scheme down here in the yellow. That's the wrong button. Down here in the yellow, so that's just doing your PBL mixing, and usually is actually pretty effective at producing stratocumulus clouds. Your shallow convection scheme is going to be doing the shallow cumulus, and your deep convection scheme is going to be doing your deepest convection. I have these boxes overlapping over convective regime because it's, not all schemes have explicit separation between convective regimes, and things like mid-level convection might be partially represented by the deep convection scheme. The shallow convection scheme might try to take a crack at it. Some of this sort of depends on actually how you do your time splitting in the physics loops. So you could be a little smarter in your process ordering to prevent this sort of overlap behavior, but it is a bit of a side effect of this approach. And so to unify these convective regimes, we're going to start with the eddy diffusivity mass flux approach model. And so it's a convection scheme that computes the turbulent fluxes from convection into a down gradient diffusion scheme that would do your small scale turbulence, and then a mass flux plume model, which will handle your cumulus convection. And so the actual mass flux plume model that we'll be using in ClubMF has an explicit ensemble of plumes that we initialize by constructing a PDF of the subgrid vertical velocities in a grid box, and initialize our plumes from there. We compute the lateral entrainment, and each one of these, this must have been converted to PowerPoint or something. All my formatting is a little different. That's okay. This is the fractional entrainment rate that each plume ensemble feels, and it's stochastic, and that's given by this squiggly P, which is referring to a Poisson distribution with a mean of the layer thickness over L, which is our entrainment length scale. So the entrainment length scale is defined here as the vertical distance a parcel undergoes before experiencing a single entrainment event. And so this squiggly P will return the discrete number of entrainment events that have occurred over the layer delta Z. And then we integrate a steady state updraft equation vertically with these entrainment rates and the buoyancy. So there's no convective quasi-equilibrium assumptions in this scheme. And the way that we will try to parameterize different regimes is by varying this entrainment length scale. And so we want this dynamic in time and space, where a small entrainment length scale would be shallow convection, a large entrainment scale would be deep convection, and mid would be in between. Yeah, this is a bit problematic. So I will just state what's underneath the figure here. With ClubMF, what we did is we swapped out the eddy diffusivity term with club. So club, as Vince just talked about and Ben talked about, cloud layers unified by binormals. It is a prognostic turbulence scheme, and it closes the higher order moments in the prognostic equations using an assumed distribution method. That assumed distribution method is a two trivariate normals. And then what we do is we couple these mass flux plumes to the club solver in the 5-diagonal club matrix that solves for the prognostic fluxes. And so the ClubMF equations look like this, where the club solver will spit out the total fluxes due to mass flux plumes and prognostic turbulence. So there's 3 different versions of ClubMF of varying complexity. We started with the just one that targeted shallow convection, and that's we set this entrainment length scale to something fixed that you just set as a nameless parameter. It produces a pretty nice result. So this is a single column model simulation of the shallow cumulus Bomix case. And it's a grid point in space and time. And so what is shown here is the subgrid distribution of liquid water potential temperature on the x-axis and total water on the y-axis. The faint PDF lines here are the PDF you get from an LES model. So we ran an LES model to be our truth. The club joint PDF is this darker oblate shape here. And you can see, so it's quite a bit narrower than the PDF produced by the LES solution. And so the mass flux plume, this is the explicit ensemble of mass flux plumes, so I think there's 100 plumes in here. And as you can see, they kind of fill out this skewed tail of the PDF that isn't being represented by club's joint PDF. So then we extended to deep by coming up with an entrainment length scale formulation as a function of the environment. And the latest, greatest version I call Club MF Arrow down here. And here the entrainment length scale is a function of plume history properties. We also have an explicit downdraft ensemble. And that actually allowed us to make a cold pool feedback on the entrainment length scale. And these three bullets here kind of give us this diurnal cycle over land that we've really been targeting. And so this is a single column model in the LBA case, which is convection over land. And this is the top of the plume ensemble. The dashed black lines is the LES solution, and the red is our latest, greatest Club MF version. So it does a pretty good job, and it has, the precipitation rates are just as predicted by the LES. So now moving into 3D model simulations. So this is a 20-year AMIP simulation. And what is shown here is a PDF of the precipitation rates in the tropics. The black line is the iMerge observational data product. The blue and cyan are CAM6 and CAM7 respectively. And the yellow here is Club MF. And so this drizzle problem that gets expressed in CAM6 and CAM7 is shown as where the line is more probable than observations for rain rates of about 10 millimeter per day or less. And Club MF seems to improve that quite a bit. It also produces more extreme precipitation events that you don't get for CAM6 and CAM7. Another look at convection in the tropics in the simulations. So these are Hofmahler plots. The left column is this GPM DPR data set that's not globally continuous, so there are extrapolated values under the regions where it's shaded. The top row is the convective precipitation rate. The middle row is the stratiform precipitation rate. And so GPM DPR actually has these components broken down using this bright band proxy for what they consider stratiform rain in the observations. And so we utilize those to provide the ratio of the convective precipitation over total precipitation. And so the values are usually around 50% on average in the observations. In CAM6 and CAM7, it's about 80 or 90% convective precipitation rate occurring in the tropics. And Club MF, which we were really happy about, was able to bring that down to closer to 50%, more in line with the observations. Now I want to talk about the latest, greatest version of Club MF, and I was able to, again, this is missing an attribution here, but I work on SEMA. SEMA is developing kilometer scale capabilities in CSM along with help from Earthworks and the CSM project. So we were running these 3.75 kilometer simulations. The cloud field in the Western Pacific looked like this in that solution. Mind you, the only convection scheme active is Club. We've turned off deep convection. And what you have is all these sort of sprinkles of deep convection occurring over almost everywhere and very intermittent. It's just like a mosaic of deep convection occurring everywhere. And so what I think is going on here, and I certainly didn't come up with this myself, but these 3 kilometer models, they can support these 10 kilometer updrafts, 10 kilometer wide updrafts. However, the entrainment rate responsible for mixing that updraft for the environment, those are from order 100-meter eddies. So they're not resolved, and they still need to be parameterized, and they're not really explicitly parameterized in these models, except that the Diacor has scale-selective numerical filters. In this case, MPAS uses a Smagoriski scheme, which is doing a little bit of mixing, but it's not parameterizing the entrainment process correctly. And so basically the only convection this model can support is like a very deep undilute mode with a high level of neutral buoyancy. And it kind of just does that everywhere. We think you need to have some type of parameterized convection to handle these transitional cumulus regimes. And so this bottom panel is a rerun of the simulation with Club MF. And you can see our sprinkling of deep convection problem has for the most part gone away, and we have much more organized structures coming about. And this also manifests in a better skill score. So this is a Diamond 1 simulation that's initialized from ERA5 on August 1st, 2016. So the first several days of that simulation you can consider initialized prediction. And so the RMSE for CSM out of the box is the gold, and the red is with Club MF. And so we brought our RMSEs, with respect to precipitation in the iMerge data set down significantly. This is the MQ Diamond 1 simulation, so we're not quite as good as them yet. We plan to spend the next several months sort of calibrating this configuration a little bit more to bring down our RMSEs, playing with what in Club MF is helping a lot and what is maybe not helping. Essentially, really hone in on an optimized version of the kilometer scale configuration with Club MF. So that is everything. And so I'll take any questions you guys have.
Move on because we're out of time. Well, if my boss has a question, I can't go against it, I guess.
Is there a danger in using RMSE as a score that you're just going to drive yourself to smoother fields, basically? So it was smoother, which it possibly wants to be, but even smoother still will probably continue to improve the RMSE. So you might want to think of another way of analysing it to perhaps cloud scale structures or something to get a bit more confidence.
Yeah, okay, will do. Thanks. I would imagine pattern correlations would have the same problem.
Okay, thanks, Adam. Next up is an online presentation by Brandon Duran. He's going to talk about aerosol effects in the ice clouds in a CAM6 perturbed parameter ensemble. Away.
Yeah, thanks. Thanks to the organizers. Sorry I couldn't be there in person, but excited to talk a little bit about a high cloud response to aerosols in a perturbed parameter ensemble. I want to thank my co-authors, and then also want to thank Brian, Truda, and Christina and Car, who have kind of helped through the process of this. So I'll jump right in, give a little brief overview of the PPE that we're looking at. So we're running this PPE with the version of CAM 6.3. If you're familiar with the PPE that was ran a couple years ago by Truda and a few other folks, it's pretty similar to that, except that we've really reduced the amount of parameters that we're looking at. So we only look at 19 parameters, focusing strictly on aerosols and microphysics, but we essentially inherit most of the parameter ranges themselves from that original CAM6 PPE. And we run a set of 162 different simulations across a variety of these parameter perturbations. And so to give a little more detail about what we're thinking about, we're really focusing on aerosol forcing. So we have kind of two different types of simulations that we're looking at. Each are run for 2 years long with fixed SST. So we have a pre-industrial and a present day run. And the two of them only differ in the aerosol emissions that we prescribe. So in the pre-industrial run, we're looking at 1850s aerosol emissions, whereas in the present day, we're looking at 2010. And then these are nudged runs, so we're nudging horizontal winds above the boundary layer. And I just show these two kind of basic zonal mean plots for our ensemble, just to give a sense of what's going on. And so essentially just what to take away from this is the green curve, which is showing the present day simulations. You can see on the right this kind of strong increase in the northern hemisphere in the vertically integrated droplet number concentration. So that's really just highlighting the aerosol forcing that we're going to take a look at. And then to kind of just orient ourselves, there's kind of a few methods that are usually used for diagnosing aerosol forcing. Given how short this talk is, I won't really go into them, but typically a lot of people use this GON method, which is just uses aerosol-free radiative fluxes from the model, and then APRP is another kind of common method that's used. But actually in our talk, or in this talk, and then kind of in the results that I'll show, I'll kind of focus on this method on the right, which is this new cloud radiative kernel method that we've developed quite recently that relies on satellite simulator output from the models. And really the reason we hone in on this is because we're able to kind of separate the contributions from liquid and ice cloud changes, which can kind of allow us to get a deeper sense of what's going on with aerosol forcing. So I'll just kind of briefly touch on what this method is, just to kind of give you guys a sense of how this works. But essentially there's two components to this method that, so on the left, what we're looking at is GCM output from the MODIS satellite simulator. And so what you're looking at is just an example of the change in global mean ice cloud fraction. And the nice part about this simulator output is that it's showing cloud fraction according to two kind of key cloud properties, in this case, effective radius and ice water path. And so we're able to not only see changes in the total amount of clouds, but also in the properties of the clouds themselves, which are radiatively quite important. And then the other component of this method is this cloud radiative kernel, which is generated offline using a radiative transfer model. And so you can really just think of this as dTOA over d cloud fraction, so measuring the effects of changes in cloud to the radiative fluxes. And just on the right, this is kind of showing basically that as you move from the bottom to the top, you're moving to clouds with more cloud water, which are thicker clouds, which reflect more incoming shortwave radiation. And then as you move from right to left on this plot, you're moving from bigger ice crystals to smaller ice crystals. So you're increasing the surface area and the albedo, enhancing the reflectivity. So that's a kind of very brief overview of this method. And I'll just kind of jump right into the results here. So this is the ensemble mean shortwave ERF ACI for just ice clouds. And I really just want to draw attention to the top left plot of this kind of figure, looking at the total aerosol forcing from ice clouds. And so what I really want to point out here that's interesting to us is that the ice cloud response is quite heterogeneous. And so you can see there's kind of this dipole of warming in the tropics and then this cooling over Asia and its outflow region. And this is quite interesting because it's really in contrast to what we see with liquid clouds. And so what I'm showing here is just the ensemble mean changes on liquid and ice cloud fraction from the MODIS simulator. And what you can see is that with the addition of aerosols on the left here, liquid clouds tend to increase almost everywhere across the globe with a few small exceptions. Whereas on the right here, the ice cloud fraction kind of has this heterogeneous pattern. So this is really interesting and something that we want to try to understand better in this PPE. And then I just show here that no matter what method of kind of diagnosing aerosol forcing, this warming effect in the tropics is observed. So we kind of want to dive into understanding this, and everything that I'll share from here on is pretty preliminary, so we're still kind of trying to unpack what's going on. So what I'm showing here are longitude and pressure plots over kind of the tropical Pacific, 10 south to 10 north. And just to kind of orient the picture here, on the left, we're seeing the pre-industrial control cloud in the model, and then on the right, we're looking at the change in cloud. And so you can see that this warming effect that's happening in the tropics is largely coming from this pretty strong reduction of high clouds over the kind of western and central Pacific. And so kind of to try to understand what's happening here, I'll walk through a few other plots. So on the left, you're looking at the change in cloud ice number over this same region. And you can see there's kind of this strong decrease in the tropics, in the upper atmosphere. And on the right here, I'm showing the change in the activated ice number from homogeneous nucleation. And what you can see is really that reduction in cloud and cloud ice number that we're kind of observing in this upper layer of the tropics could probably be coming from this strong reduction in homogeneous nucleation. And there's potentially a cool story here, which is that the same plot on the left that I just showed you, which is this decrease in homogeneous nucleation, is kind of, there's this corollary increase in heterogeneous nucleation in this upper region of the tropics. And despite the fact that kind of the magnitude of these changes is quite different, this could be an indicator that there's maybe this increased competition where heterogeneous nucleation is occurring at kind of lower supersaturations and really suppressing the homogeneous nucleation. But that's kind of a pretty early story that we have here, and we really need to do kind of more testing to try to unpack whether it's the microphysics here that's really driving this, or whether there might be some macrophysical changes potentially related to kind of changes in the transport of the vertical transport of water vapor that's getting up to this upper layer of the atmosphere. So that's kind of all we have here. Definitely an ongoing work in progress. Hopefully we can get some ideas moving forward. And I'll kind of just leave these conclusions up on the screen. And yeah, hopefully there's some time for a few questions.
Right, doesn't look like we have any questions, and it's just been brought to my attention that Trude canceled her talk, so we actually have plenty of time here before the break. So let's thank Brandon again. Then the next talk is also remote from Norway, so thank you for staying up late. It's Ara Jamson. Ara Jamson is going to talk about the impact of model resolution on climate in the Norwegian version of CESM, so ESM.
Thank you, and thank you for letting me present. Do you hear me?
Yes.
Yes, good. Okay, so my name is Ara Jamson, so I'm an associate professor at the University of Oslo and also a researcher at Met Norway. And I'm in the coordination team for the model development of NORSM. So I'll show some first results today, and we are still very much developing the model, but yeah. So just short, what is NORSM? So it's been developed since 2008. It's a consortium effort, so we have 7 Norwegian institutes contributing. So it's not one partner responsible. We're doing this jointly. We contributed to CMIP 5 and CMIP 6. We have more than 60 national developers, and NORSM is used in more than 50 research projects every year. So on Norwegian scales, that's pretty good. We are currently developing NORSM 3 for CMIP 7, a model resolution similar to CSM 3. And we plan to freeze the model development on the 15th of June. At least have a chill. Just to show you, so we share a lot of components, or it's a lot, in large part based on CSM. So here I show in blue some boxes which are the CSM-based components, like CAM, CLM, Mozart, and CICE, or size. But then we have some unique components, like the ocean component is unique to NORSM, and also the ocean biogeochemistry. And we have a different aerosol module with aerosol physics and chemistry, and also how aerosols interact with radiation and clouds are different in NORDSM compared to CSM. Also, we use CLM, the land model with dynamic vegetation and fates. So the development and fates and also the land ice system, that's done jointly with NCAR. So in large part, a lot of similarities, but we also have some differences. So if you compare the CMIP 6 versions, so CSM2 and NORDSM2, so this figure was shown by Dave earlier this morning. So you see it's based on this is from the Fasulo paper. So it shows performance for the CMIP 6 models on pattern correlation, and different radiation and heat variables. And we see that CSM2 was ranked top, but then NORDSM2 with similar resolution as CSM was also ranked high, which is maybe not so surprising given the similarities. But if you look at the climate sensitivity, there are differences. So CSM2 was ranked or was among the highest climate sensitivity models in the CMIP 6 ensemble, while NORDSM2 was among the lowest with a climate sensitivity of 2.5 for both the 1 degree resolution model and the 2 degree resolution model. Just some experience from the CMIP 6 versions of NORDSM. So we had 2 versions, a core resolution version with 2 degree horizontal resolution for atmosphere and land, and 1 degree for ocean and sea ice. And then we had a medium resolution, which was a resolution similar to CSM2, so that's 1 degree horizontal resolution for most components. What we found was that even if the coarse resolution performed worse when it comes to patterns and pattern correlation and precipitation patterns, for instance, when we consider the climate feedbacks and also the forcing, the 2 model versions performed very similar. So here you see, for instance, the feedbacks from a 4 times CO2 simulation. And black is the coarse resolution, and orange is the medium resolution, and you don't see the black circles because the orange circles are above because they have the same values. We also saw that this is showing the top of the atmosphere radiative imbalance for the 1 degree resolution in solid and a 2 degree in dashed. Also very similar. So what we ended up with was to use the coarse resolution model version for a lot of the CMIP 6 production runs. Not all, but a lot, because it's so much faster and also lower computational costs. And it's also used extensively at the universities because of that. So now we want to have a 2 degree horizontal resolution also for NORDSM3. So we are using CAM7. So the main motivation is then to develop a faster and more cost-efficient version of NORDSM3 based on the 1 degree configuration. So we want it as similar as possible. We also want to, we aim then to tune the 1 degree resolution version of NORDSM using results from the 2 degree resolution. So CAM7 in NORDSM, what we used is in large part what is developed at NCAR. We have some differences, the aerosols, which I mentioned. We also had a modified atmosphere ocean flux calculation. We used the ocean flux scheme 1, which is the core parameterization scheme. We have a different secondary ice scheme, and also the coupling to the ocean is different, and aerosol emissions, or DMS, for instance, because we have a different ocean model. So we're using this NE16PG3 grid for atmosphere and land. Then we have a different mask for the ocean. And we're using the same files and setting as CSM for topography and spectral element type, core, drive deposition, and so on. So this is the tag, the CAM64085 tag. When we start running it, just not changing anything, having it exactly the same file names and name lists and parameter values as the 1 degree version. We show here the surface air temperature for the 2 degree and the 1 degree and the difference. And we see that the 2 degree is warmer almost everywhere except over Antarctica. And this was the same that we saw in the CMIP 6 version, that the 2 degree is much warmer. For precipitation, we get a more pronounced double ITC set, which was not maybe so unexpected, but not maybe so desired either. And also we have a drier Amazon compared to the 1 degree version. If we just look at some globally average time series, we see that the 2 degree version, it exhibits a more positive top of the atmosphere imbalance. It's warmer at the surface. It also continues to warm. It has similar short wave cloud forcing and similar drift in the sea surface salinity as in the 1 degree version. But the long wave cloud forcing is more positive, which is also, it's too positive already in the 1 degree version. So that was not so desired either. So what we have done now is, this is more like a test of a method than, so it's like a mini PPE. We will expand this in the future, but we tested first with just 4 parameters at 25 members. And we want to do this in coupled configuration, because what the experience for CMIP 6 was that we did a lot of like PPE work on atmosphere and land, and then we coupled it with the ocean, and then everything was different than how it looked in just atmosphere and land alone. So we want to do this in fully coupled configuration, but then using the 2 degree version. So this is just a start with 4 parameters, 2 from the microphysics, 1 from the convection, and then 1 club parameter. So we so member 1 is the reference, which is identical in the setup as the 1 degree version. And then we have all the members below that, and this is a very intense color scheme. I'm sorry about that, but we have then ranked them with this normalized RMSE. And we want to find members which not all need to be ranked like top, but they need to span the whole range of model behavior. So we want members which are not showing like similar, if it's doing very well on precipitation, for instance, it's good if it's not doing as well as the one we're comparing to. So they kind of rank differently from the different variables. But from this, we picked 4 members, which we continued. So here you see the same time series. And then this is the time where we branched off and with these 25 members in this mini PPE. And then we continued after that 4 members to try to find out how it behaves on the on longer timescales, since this is a coupled configuration. So we see that with only these 4 parameters, we span already a large range of values, and and they don't all behave the same. So we will continue then a subset of these members and then investigate the long-term behavior of the model to see then if we can use this, but we will do it a bit more, use more parameters to tune for the PPE in the future, where we have actually freeze the model development. But then we'll see if we can use this as a method for tuning the 1 degree version. So we need to further investigate if this 2 degree version of NORDSM3 exhibits similar forcing and feedbacks as the 1 degree version, as we found in or saw for the CMIP 6 model version, but that's not necessarily applicable to the CMIP 7 version. And then we hope to tune the CMIP 7 version at 1 degree resolution using the results from this 2 degree version. PPE in a couple mode. And we also aim to streamline the workflow, so building, running, and analyzing the PPE. So it's straightforward for NodeSM developers to use, because we are all kind of running this model together. So we had to have like a common workflow. Yeah, and the code is on GitHub. And if you have questions, you can ask here, or you can also contact me. Yes.
Any questions for Ara?
Hi, Ada. Nice talk. On the last slide you showed with the time series of the fully coupled with the different parameter sets, two of the experiments, the long wave cloud forcing changed a whole bunch. I can't remember if it went down by like 5 watts, but what parameters did you find that were so strongly important for changing the global long wave cloud forcing?
Yeah, that was this, it's from the micro physics, this VTRMI factor. So it scales the ice and snowfall speed.
Gotcha. Okay, so that was pretty much the thing that was branching the two different long wave cloud forcing extremes, was that fall velocity parameter. Thanks. Okay. Actually, one more question, since apparently we have some time. I'm curious what like kind of throughput you're getting with this 2-degree model, and like in core hours per simulated year. You know, ours is about 6,000, so I'm just curious.
Yeah, so now we have some problems with the 1 degree, so that we can only run like 8 years at a time, because we have a memory leak, so that's also coming into here. Then we have to resubmit, so this one we can run as long as we want. We don't run into that problem, but the throughput is 18 years a day. But I should remember the cost. I think it's like 2,500 to 3,000 approximately. Yeah.
I'm curious if you've compared your 2-degree PPA with some of the earlier 1-degree PPEs that we've done here at NCAR to see if the parameter sensitivity is comparable.
Yeah, so we took this, we chose the parameters and also the range through this paper. But we haven't, I know Ben Sanderson, he's also working with NodeSM, so he has done some actually analyzed the data. But we should compare that, absolutely. We haven't done that yet.
It would be nice to do PPEs at 2 degrees and not 1 degree.
Yeah, I agree.
Okay, let's thank Ara again.
Thank you.
Okay, next up is Wayang Lee. I don't know if it's online. No, you're right here. Yeah, sorry about that. You have all the time in the world here. You have until 3 p.m.
That's good.
I'm just going to talk about the development of high-resolution Taiwan Earth System model.
Sorry. So this one is okay. Back. Okay. So thank you for this opportunity to give a talk here. As you may already also know that we got in Taiwan we got a funding cut from our government. So in the last time I got to collect enough funding to come here. So yeah, and today I'm going to talk about the development of the Taiwan Earth System model in high resolution, and this is our list of our team, and yeah, then. So our TIESM is based on the CSM 1.2 with only some modification because we have only very limited manpower. And so in the atmosphere part, we add a trigger function for deconvection. Basically, this is borrowed from NOAA global forecast system. And then we change the cloud fraction parameterization. We call it GTS. And then we use a locally developed aerosol scheme, which is a prognostic 3-moment aerosol scheme. Consider not only the number and also the mass and also the surface area. And also, we modify the land model to consider the 3-dimensional interactions between radiation and topography to consider the effect of the shadow and the reflection between topography. So our goal is to improve the ability to simulate the climate variability in the spatial and also temporal scale. So there's some features of CheSM that meet our goal to improve the simulation of variability. For example, the monsoon rainfall in 4 major monsoon regions, such as Africa, South Asia, East Asia, and Central America. And these numbers are CMIT models, and the CheSM is red cross, and the ensemble mean is orange cross. You can see that in most regions, CheSM performs quite well, particularly over the East Asia, which is surprising for us and meet our goal. So and then we can consider the extreme precipitation in East Asia for the May season, which is in the spring, and also the typhoon season in the summer. As we can see that the also for the indexes of extreme precipitation, CheSM performance is also quite well. And also for the most of the tropical regions, the precipitation extremes also perform pretty well. So it's basically it's meet our goal, although we don't really know why. But we think the CheSM1 is quite good for simulate the extreme event, such as it has the potential to simulate them, such as typhoon or monsoon or frontal systems. So therefore, we would like to, based on this CheSM1, to do a high resolution simulation to see how it works out. And then so we carry out several experiments. First is the, of course, is a standard low resolution CheSM1, which is 100 kilometer for atmosphere and ocean. And also carry out a prescribed SST for high resolution atmosphere using 25 kilometer atmosphere. And also for high resolution couple simulations, we carry out 2 runs. One is the high resolution atmosphere, low resolution ocean. We call it HALO. That is a compromise because although most of the chips are manufactured in Taiwan, but we academic sectors actually cannot afford it because most of the chips are already sold out to the big companies in the United States and, for example, China previously. So we only have very limited computing power. So therefore, we try to do such a way that to simulate using a low-cost strategy. So, and the other one is, of course, the high-resolution atmosphere and the ocean, using 25 kilometer atmosphere and the 10 kilometer ocean, and then compared to observation. So the table in the right-hand side shows the global mean of these variables. As we can see that, for example, the surface air temperature, all the simulations are quite close to observation. And also for the type of atmosphere radiative budget residual, it is also quite close to observation with a little bit positive value indicating a global warming. Although this variable seems quite well, one thing we need to consider that is the cloud forcing is too weak for CheSM particularly for high resolution. As we can see, the short wave cloud forcing is too weak, and also long wave cloud forcing too weak. Although the total cloud amount is a little bit more than observation. So this is an area require more investigation. And so first of all, we'd like to see the SST deviation from observation. So this is observation, Hadley SST, and also high resolution HALO and HALO. So we can see that in high resolution difference, we can see, first maybe you can see that the HALO minus Hadley SST, the temperature is a little bit lower than observation, particularly over the North Pacific, but it's and also colder in the North Atlantic, but in the Southern Pacific, it's basically warming. And for HALO, this the deviation is significantly smaller, as we can see that in warming in the Northern Hemisphere, quite remarkable. And they will affect the phenomena that we will show later. So yeah, in the North Pacific, and also we can see that in the Khotan regions, although the high resolution ocean does not necessarily perform better in this region, we still don't know why. Okay, so we focus on the tropical cyclone simulation, and the bottom panel shows the observation IP tracks, and the upper panel is the low resolution TISM. So of course, we know that 100 kilometer resolution cannot resolve tropical cyclone pretty well, so there are very low number of tropical cyclones. When using the high resolution atmosphere model, we see that the number is quite comparable to the observation, although in the Northwestern Pacific, the region that we focused, because Taiwan is here, so the number is still too low, and we have too many TC in the Eastern Pacific. And when we use the HALO configuration, we found that, okay, right now the Northwestern Pacific has pretty well performance, and also in the Eastern North Pacific. However, in the Atlantic, most of the TC disappear, particularly for those TCs originate from the coast of Africa. Most TC are only appear in the North Atlantic. And yeah, for the high resolution atmosphere and the high resolution ocean, we see that it's a booming, that in almost everywhere, all the ocean basin, the TC number increased a lot. Okay, so first we would like to investigate that how coupling changes the TC number in the Pacific. As we can see that in the Pacific, this type of panel shows the vertical wind shear. It decreased a lot in the Western Pacific, and yeah, so it favored the generation of TC, and also in the mid-troposphere, specific humidity also showed a similar trend. And the bottom panel shows, I think, is the most important factor, that the warmer sea surface temperature in the maritime continent generate lots of TC, and in contrast, in the Atlantic, the lower sea surface temperature decreased the number of TC generation here. And one other thing noticeable is that the much colder North Pacific suppress the movement of the TC into the Northern Pacific. So it also decreased the number of the genesis in the Eastern Pacific. And then the other thing is more related to the larger scale dynamic pattern that we can see in the AMIP simulation. Can I see here? Okay, in the ME simulation, the Pacific high is very strong. It extends all the way from the Pacific to the Philippine Sea that suppress the genesis and also the movement of TC in this region. And in the halo simulation, we see that Pacific high is more close to, the region of Pacific high is close to the observation, also in the halo simulation. So it allows more TC to genesis here. And also this panel shows the annual cycle of TC numbers that we focus on Western North Pacific, that here. And for the halo and the halo, they can both simulate pretty well the annual cycle, although the peak occur a little bit late compared to observation. And in the Atlantic, we see that the number of the AMI run and is close to observation. And also, as we showed before, although the halo simulation has pretty good number compared to observation, its peak is significantly lower. That is compensated by the TC genesis in winter. That is not good. So and also for the TC intensity that we see in the halo simulation, we create lots of weak TC in both Northwestern Pacific and the Atlantic Basin. And in the strong TC, the number is very comparable to halo simulations. So we have 2 weak TC in halo and also too many TCs in winter. And it implies that the algorithm for detecting and tracking TCs may require adjustment, not related to the dynamic itself. And one thing we like to turn to the ENSO simulation. This panel shows the standard deviation of SST. The top 2 are observations, and this one is low resolution TISM historical, and this one is halo simulation. We can see that the amplitude of TISM is a little bit stronger than observation. And turns into the high resolution ocean simulation, we see that the variability almost disappear in the equatorial Pacific, which is not good. And also we know that this phenomena also occurs in some other models, such as maybe NOESM or the Australia model. And one thing we also noticed that is the very strong variability in the Northern Pacific out of the Japan region. It is a common feature for TISM, or even in the low resolution version. So this one may result in a very cold bias in the North Pacific, and it requires additional investigation. And then this figure shows the power spectrum of ENSO. Maybe not very clear. Okay, so the top 2 are observation, and this one is low resolution TISM. We can see it's not very clear, sorry about that. Okay, the amplitude of the low resolution TISM is comparable to observation. However, when changed to high resolution atmosphere, the ENSO variability is way too strong. The vertical scale are different from this one to others. So you can see this one is very strong. However, in the high resolution ocean model, the variability is very weak, particularly for higher frequency one, such as 2-year or 3-year peak, almost disappear. And the right-hand side is the wavelet analysis. We can see that, this upper 2 are also observation, and this one, low resolution one performed pretty well, and the high resolution atmosphere is too strong. However, in the high resolution atmosphere and the ocean, it almost disappear. So So this is summary that we try to establish the high-resolution atmosphere model using a different resolution of ocean, and it can using the high-resolution atmosphere model can reproduce pretty well the TC numbers and the tracks in the Northern Pacific. However, ENSO are too strong in the low-resolution ocean model, but almost disappear in the high-resolution ocean model, and we still try to figure out why is that. So I will stop here. Thank you.
I didn't think I would be saying this, but thank you for going over time.
Okay. Yeah.
Are there any questions for Wei?
You only showed like 35 years from the Halo simulations for ENSO, and you said it's too strong, but you could, I mean, the middle period there, I know it's only a few years, it's kind of weak. And do you think you have enough years to say that what you put on your summary slide, that it's too strong? Because the spin up, I mean, you're starting from zero there, what are the trends like at spin up? Because we find that in general you get
take
quite a
20
bit.
years for spin up.
Okay.
And then after 20 years, the TOA balance is almost reached, and also temperature does not have significant change. So we consider it's already spin up. Yeah.
Could you show your Halo versus HAHO SSTs? Looks like the upwelling is actually stronger in the low resolution model than in the high resolution model. That seems kind of unusual.
Yeah.
Okay.
Yeah, we surprisingly found that. We don't know why, actually.
Okay.
Another ENSO question, nice talk. So is it safe to assume that maybe the higher resolution ocean model, the submesoscale eddies, are reducing ENSO amplitudes in that? Or why do you think you might be having such a weak ENSO with high resolution?
Actually, we don't have any clue at this moment. And our guessing is that maybe we need to, I'm not quite sure because I'm not familiar with the ocean model. Yeah, but some of our colleagues consider that maybe we need to tune the mixing parameter. Yeah, maybe you'll help. We are working on that.
Let's thank Wei again. All right, we will reconvene at 3:30.
everybody. Welcome back. By the way, for those of you who don't know me, my name is Hui Wan. I'm at PNNL. I'm one of the external co-chairs of AMWG. In the second half of this session, I will help Peter a little bit with the logistics and introduce the speakers. Our first speaker of this session is going to be Aaron, who is going to talk about aquaplaning simulations and QBO.
All right. Well, thank you, everyone. So today I'll be talking about using an aquaplanet model to understand future changes in the QBO. And so just to refresh your memory, the quasi-biennial oscillation, or the QBO, is an oscillation of the stratospheric zonal winds. And so as you can see, I've kind of highlighted this area in the black box. That's the tropical stratosphere. And so essentially you have descending regions of westerly and easterly zonal winds. And so if you focus on a single pressure level, you'll get an oscillation back and forth between westerlies and easterlies with an average period of 28 months. And so the QBO is driven by a wide spectrum of vertically propagating equatorial waves. So you can kind of see that by these wavy arrows here. So as these waves propagate upwards, they deposit their momentum in the QBO region and cause those zonal jets to descend over time. The descent to the QBO zonal winds can be slowed by the mean meridional Brewer-Dobson circulation, which is shown by these white arrows here. And it's generally upwards in the tropical stratosphere, which is counteracting the QBO. And despite the QBO's importance to the global climate, its response to increased greenhouse gas concentrations is still quite uncertain, especially changes in the QBO period. So considering this disagreement among fully coupled climate models, it can be useful to use an idealized model to improve our understanding of atmospheric processes and to better identify these cause and effect relationships between, for example, a CO2 radiative forcing and then ultimate changes in the QBO. So I've kind of shown a list of climate models in order of increasing model complexity, starting with, on the left here, a dry dynamical core, which would simply use a simplified physics scheme, which is maybe a relaxation towards a prescribed temperature profile. And then where my work fits in here is in the aquaplanet framework, which is the simplest climate model that you can fully model the response of the atmosphere to CO2 radiative forcing. So you have the full radiative transfer model here. But you still have very simplified boundary conditions. So for example, you have no land, as the name suggests, no ice, and also no seasons. And you have a prescribed ocean. And so of course we have more complex configurations such as AMEP here, where you also have a prescribed ocean, but you use the full complexity atmosphere model. And then of course a fully coupled model as the most complex. And so this is the first time, as far as I know, that the QBO response to increasing CO2 has been analyzed in such an idealized model. So just to describe this aquaplanet model a little bit more, we're using the community atmosphere model version 7. So this is the most up-to-date version of NCAR's atmosphere model. We're using the spectral element, or SE dynamical core, at a 100 kilometer, roughly 1 degree horizontal spacing. And this is just so that we can adequately resolve the equatorial waves that are important for driving the QBO. We also use a 72 level vertical grid, and this provides sufficient vertical spacing in the stratosphere to resolve equatorial wave breaking. One of the reasons why we're using this latest version is because it incorporates a fix to the convective gravity wave scheme. So these parametrized waves are very important for driving the QBO in models with large horizontal resolution. And then we remove aerosol radiation and aerosol cloud interactions just to simplify the model, and ultimately they don't contribute much to the QBO. And so all greenhouse gas concentrations in this model are fixed except for ozone, which has this profile shown here on the right. And so briefly, the experimental setup is, of course, a control simulation, which I call 1 times CO2, which just uses the default aquaplanet experiment CO2 concentration of 348 ppmv. And then that configuration uses the QOBS sea surface temperature profile shown on the right here as this solid line. And that's really just meant to mimic annual average sea surface temperatures on Earth. And we also have a quadrupled CO2 experiment called 4 times CO2. And then the 4 CO2 4K experiment, where in addition to quadrupling CO2, we add a positive 4 Kelvin offset to the sea surface temperature, as shown by this black dashed line here. And this is really to incorporate an ocean feedback to our idealized climate experiment. So to get into the results a little bit, these are difference plots between, on the left here, the 4CO2 experiment and the control simulation. And then on the right, these are difference plots between the 4CO2 4K simulation and the control run. And if we look in this bottom row here, these are temperature differences. And we see that in both elevated CO2 runs, we have stratospheric cooling. And so this is an effect of the direct radiative impact of CO2, where we have greater long-wave emission cooling the stratosphere. But interestingly, we only have tropospheric warming in this 4CO2 4K simulation, and that's connected with our increased sea surface temperatures. And then we also have some changes in the zonal wind patterns, which are seen also in fully coupled models in climate change. Now, just to specifically talk about the QBO, what I've plotted here is tropical average zonal mean zonal wind. And so you can see the oscillations back and forth between westerly winds in the red shading and easterly winds in the blue shading that characterize the QBO. And so if you look at this bottom plot here, this is for 4CO2 4K. And we actually see a shorter QBO period by about 10 months, and also a slight decrease in the QBO amplitude, especially in the lower stratosphere. And since this is the case where we see the largest change in the characteristics of the QBO, this is what I'll focus on for this talk. And so, of course, we want to understand why the QBO is changing in response to our increased CO2 and sea surface temperatures. And we can do that using what's called the Transformed Eulerian Mean, or TEM framework. This is essentially just a zonal averaging of the equations of motion with this additional transformation shown here to the mean meridional and vertical pressure velocities, giving us the so-called residual velocities. And this zonal mean framework is useful because the stratospheric circulation is essentially a result of the interaction of small perturbations in the longitudinal direction, or waves, with a largely zonal mean stratospheric flow. So think, for example, of the Brewer-Dobson circulation I was talking about earlier. And so in this formulation, we have a TEM zonal momentum equation. On the left here is the time tendency of the zonal wind, which we use as a proxy for the QBO. And then, of course, on the right, we have various different driving terms. The first of which is due to advection by the residual circulation. So this is, for example, how the Brewer-Dobson circulation would influence the QBO. And next we have contribution from resolved waves in the model called the Eliason-Palm flux divergence, or EPFD. We have a contribution from parametrized gravity waves. And then finally, a leftover term, which in climate models is usually due to numerical diffusion. Here, this term is small, so I won't focus on it. And so, of course, we can plot all of these terms in the QBO region. And so I've done that here just for the total tendency and the resolved wave tendency, or EPFD, specifically for the descending westerly phase of the QBO. So you can see by this solid purple line here, we have westerly winds overlying easterly winds centered at 20 hectopascal. And in this rightmost panel here, we have a difference plot between 4CO2 4K and the control simulation. And we see that we have an increase in the zonal wind tendency, largely due to this resolved wave forcing. And since this increase in tendency is located below the core of the westerly jet, that means that resolved wave forcing is actually will hasten the descent of the westerlies and shorten the QBO period. We can also look at the parametrized wave forcing. Again, another difference plot over here, this time in the descending easterly phase of the QBO. And we see once again that this tendency increases in magnitude. So this easterly jet will descend more quickly, and the QBO period will decrease. And so I wanted to kind of figure out why we were seeing this change in gravity wave momentum flux. Usually it's due to a more intense tropical convection, but actually in this case we didn't see very much change at all in the intensity of tropical precipitation. So what I think is causing it instead is this change in tropical tropospheric westerlies, so we have much stronger westerlies. And the mean wind within the convective heating region is actually a very important parameter for generating these gravity waves. So I think that since we're changing that parameter here, we're getting this additional asymmetry in gravity wave momentum flux that's increasing the gravity wave tendency aloft in the QBO region. And then so I also mentioned that we have a decrease in the QBO amplitude. You can see that on the right here, especially in the lower stratosphere. And so this is associated with increase in tropical upwelling, as shown in this left panel here. And this is sort of a well-documented result of increased tropical upwelling that also we see in comprehensive climate models. And essentially the buffer zone, which is where the QBO dissipates despite sufficient wave forcing, the depth of that region is really controlled by the strength of the tropical upwelling. Since we have stronger upwelling here, that zone expands and we see a decrease in QBO amplitude. So just to summarize the points I've made so far, we see that the aquaplanet QBO response qualitatively agrees with comprehensive climate models such as in CMIP 5 or 6 or in the QBO initiative experiments. Namely, when we increase SSTs and carbon dioxide and 4CO2, 4K, we get a shorter QBO period. And this is a result of increased wave momentum flux. The one inconsistency which I mentioned is that the increased gravity wave driving doesn't seem to be a result, at least, of more intense convection, but rather of these increased tropical westerlies. And then we also see a decrease in QBO amplitude for the 4CO2, 4K simulation as a response to this increased tropical upwelling. So that's all I have, and I'd be happy to take some questions.
Questions from the room?
Yeah. Yeah, so actually in the aquaplanet simulation that I'm using, you prescribe sea surface temperature. So there's actually, you're not including any of those teleconnections. So for example, you wouldn't get the QBO MJO teleconnection because there actually is no MJO in an aquaplanet. So really in this study, we're just examining the QBO response to CO2 without really considering any of those complex teleconnections.
Seems like I didn't see any impact of the CO2, and it seemed like it was the plus 4K that made the difference. Is that your conclusion? And
yes, exactly, yeah.
Is that what's been seen before in full GCMs?
Yeah, I think so, because really it's these tropospheric generated waves that are driving the QBO. So it's much less the in situ radiative perturbation from CO2 that's impacting the QBO, but rather tropospheric changes and the response to tropospheric warming that are important.
There are no further questions. Right now, let's move on to the next presentation.
Thank you.
Next, we will have Christiana talking about insights from the most recent DCMIP summer school.
Yeah, I have the pleasure to tell you about an event that happened actually last week here at NCAR. And this is a dynamical core model intercomparison project, and there are many, many people involved, as you see here from my long list. Just want to highlight, this is a collaborative effort from, I guess, the University of Michigan, where I'm from, led by us, and then together with NCAR, Sandia National Labs, Indiana University. Also, we had a representative from the UK Met Office, actually, with us, and CSU, I should maybe not, I should really mention all, CSU, Don Denslig and Colin Zaziki from Penn State University. All right. So what is DCMIP? Maybe you know it, maybe you're not. So if you haven't heard this acronym, this is the Dynamical Core Model Intercomparison Project, and we have been running this a few times. You see it in my next slide. This time around, we had desired to intercompare 3 dynamical cores that are available in the NCAR framework in CAM, plus the UK Met Office, the newest UK Met Office model, which is called Everett. It is actually a summer school. It's 1 week together with 50 students and about 10 mentors, so about 6. And here you see kind of a photo of the 60 participants, including the mentors that were here at NCAR last week. We focused on idealized test cases and also this time a very new element, which was an idealized test of machine learning emulators, which we had never done before in DCMIP. Right, here you see a little bit of the history of DCMIP. So we actually started this endeavor in 2008 and were on a 4-year cycle. Yeah, you see a little bit of that history here with, for example, Peter Lauritsen, always a partner here. Our plan to do it in 2020 fell through due to COVID, so this was actually now our 2020 version, basically. And it was always an event with a lot of modeling mentors, even from the international community. This time around, we kept it a little bit in-house here at NCAR. All right, let's maybe dive a little bit, and this is a really short talk. I just give you the essence of the test cases and a couple of results, and there's a lot to look at. So I want to point you to the DCMIP webpage. It's a wiki that we created last week. There are many, many diagrams and graphics there if you really want to dive deep. But let's maybe just today focus on the design of the test cases, which we created for this event, and we have basically 3. So let's kind of take a look. So the first two are mountain generated, and they are different scales. The first one is kind of looking at inertia gravity waves. The second is mesoscale, where we shrink the Earth to go to so-called gap flows or vortex streets. And the last one is actually a moist one, where we look at physics dynamics interplay at non-hydrostatic scales on a small Earth. And the last one is a little bit independent, which is machine learning. All right. So let's kind of take a look. So scientific motivation for number 1, which is inertial gravity waves, is actually just the presence. When you kind of, take a look at our mountain ranges, the presence of these large mountain ranges, and especially let's maybe take a look here. Oopsie. At the Andes. This is a real long mountain range, which we kind of used for inspiration. And when you then basically kind of see this a little bit down here, the mountain range, if you put that into the mid-latitudes, we put it at 45-ish or so, it's a really long ridge. We are watching basically here the gravity waves bubbling up. So in color here you see actually the hydrostatic divergence on top of potential temperature. So the essence of the test case was actually, you see the perspective element model here to intercompare vertical spacing, so 800 meters in the vertical versus you see it here as 200 meters. And the trick here is to really see how much resolution do we need to have a truthful representation of breaking gravity waves. Because gravity waves bubble up in this regime, they should break, they become actually really short, and 800 meters are not capturing them. There will be aliased, spurious numerics will come in, and that's really what we wanted to learn. So this is an example of this, of the first test case. Okay, number 2 has kind of 2 variants, and here you see our kind of scientific motivation. The first one is a so-called gap flow, and this is actually an example from nature. This is now a gap between 2 mountains. You see them in Mexico. Typically, we have a northern wind. It's squeezed through the gap, and that's really what we wanted to test, because then it's accelerated, it's partially blocked. The other scientific motivation is this nice-looking von Karman vortex street. You see 2 islands here, Madeira and Gran Canaria, used as motivations, and then you see the swirls, and this was something we wanted to mimic, not with clouds, but with a dry setup. Okay, let's take a look. And those are now the gaps. So you see this mountain, and here you can really play with Coriolis force, without Coriolis force. This is an example. Let me just play one with the spectral element dicore. And in red, you see acceleration. You see actually the flow kind of going through the gap. Let's kind of take a look here. Throwing through the gap, partially blocked here, but really accelerated. And this is without Coriolis force. And yes, you can repeat that with Coriolis force. And when we play that one, it's looking actually quite different. So here the Coriolis force is really making a big difference in the flow field. And this is just, again, it's basically an acceleration. Okay. Let me just move on and go to number 2, which is shedding vortices test case. Again, we could play with and without Coriolis forces here, and you see the mountain, a little bit different shape, Gaussian mountain, all analytic initial conditions, so very, very easy to set up. And if you now play that, and you basically see these shedding signatures, so you see behind the mountain, so the flow hits the mountain, and this is now a temperature perturbation from the isothermal initial condition, and it's really nicely shaping up into this swirling flow, and it looks kind of like the fun vortex Karman street, and these are really, really easy to set up in dynamical cores. Okay. I think I should just wrap up a little bit. We intercompared different dicores. Here you see that, different dicores do give us different signatures, SE, FE3, and MPAS, and we will need to dive into these a little more in the future to make statements about, what's the true solution. I can't really make a statement right now. Yeah. But of course, we see, sensitivities to diffusion, to resolution, and that will be explored a little more in the future. Okay. This is another depiction this is from the UK Met Office, from the so-called Everett model. basically it's also showing us, these nice swirls, but also at the very end, look at the noise, that's appearing. So this was actually also news to them. So, it's a test case that served its purpose because the UK Metaverse learned something about their own model. All right. Let's go to number 3, and then I kind of wrap up. Number 3 is now a moist test case. This is really mimicking a squall line, but with idealized initial conditions. You see a little bit of this setup here. Oops. So setup is like, low-level wind shear, no shear in the upper domain. This is zone-to-zonal wind. And the squall line gets triggered by bubbles. So we have here 9 bubbles or 7 bubbles, 1 bubbles, and they trigger convection. And that's really the essence of this test case. Here you see a little bit of that. We run this on a really small planet, the 2-kilometer grid spacing. It's non-hydrostatic. And you see now kind of the progression, 30 minutes in, an hour in, 90 minutes, and so on. After 3 hours, we have that nice kind of bow echo form. While the results are all over with different, dicores, that's again to be explored. And here you see a little bit of that. So here you see a comparison between, the SE, let me point it out, the SE, FE3, and MPAS dynamic core. This is radar reflectivity, a measure that we put as a diagnostic into the model, to evaluate that signature. Okay, I probably should wrap up. Last but not least, let's kind of take a very quick look at machine learning. And this is very exploratory, but I think something to come in the future. And here we used something from NVIDIA. It's called Earth-to-MIP. It's basically a framework for different emulators. And the emulator were GraphCast, ForecastNet, and also Penju Weather. These are 3 emulators from the community. And we used them out of sample a little bit. For example, and I only give you one example, they are trained with ERA 5, full complexity, seasonal cycle, diurnal cycle, everything, topography, and we gave it a really idealized initial condition, which wasn't in the training data set. And we wanted to see whether a steady state would be a steady state, which it would be in a dicore, and of course it isn't. When you give it to a machine learning emulator, that's probably expected. And here's some proof of it. So we should see a steady state. There's no steady state, as you see. We see a couple of different variables, 2-meter temperature. This is water vapor, 10-meter wind, and mean sea level pressure. It's looping, so initially it's a steady state, or it's very zonal, but immediately you see the flickering from the topography. You see a seasonal, not seasonal cycle, but diurnal cycle. So yes, this is actually learned by the model. Maybe that was expected, but we are following up with a couple of new ideas, actually, how to really test physical consistency of emulators. That's the approach we want to use in the future. All right, let's just kind of close here. This was really a quick preview or overview of DCMIP. Again, we looked at a variety of dynamic cores with idealized test cases. We use this as a research tool for ourselves to learn more about dicores, but also it was an educational event with 50 students that we trained on model development, and it was hands-on. It was very lively. And the future maybe goes a little bit more into the machine learning world, but that's to be seen. So, thank you. That's my last slide.
Christiana, we could perhaps accommodate one short question. If not, then let's move on. Let's move on to the next presenter. Then Luan will be talking about QBO, gravity wave, and deep convection responses to surface warming in GFDL's AM5.
Hello, everyone. I appreciate having the opportunity to talk about our research at the CESM workshop. I would like to thank my collaborators, and thanks to Pooh, we have all the simulations. She did the AM5 simulations, and my work is based on those simulations and looking at the QBO gravity wave, deep convection responses to surface warming in GFDL AM5 simulations.
Move your mic a little closer.
Okay.
Oh, pardon, mic. Thank you.
The motivation for our work is there is no QBO in earlier version of the GFDL model, AM4. If you look at the middle panel, you could barely see the QBO signal, and there's only like a seasonal cycle in the earlier version compared to the ERA5 reanalysis. The earlier version of the GFDR model uses the AD99 graduate parameterization scheme, and in the ongoing developing version of the GFDR model, we use the Bayer scheme, and you could see that at the bottom panel, the QBO signal is more realistic compared to the earlier version. And there are several important factors for important parameters for the Bayer scheme. The first important parameter is the maximum heating within the deep plume. It's called Q0. From the model outputs, we only have the great mean heating is the Q. In order to know the maximum heating within that convective plume, we need to divide it by the convective fraction. And in the CAM model, the convective fraction is set to 0.05, and in the vacuum model, it's also 0.05. And in the AMM5 model, the tuned fixed case has the convective fraction set to 0.1, and we also have additional simulations use the prognostic updraft area. And another important parameter for the Bayer scheme is the heating depth within that convective plume. And based on the momentum flux equation, we could notice that the momentum flux is proportional to the maximum heating squared. And based on the lookup table, which is based on the heating depth and the averaged wind within that heating layer, which is a function of the phase speed. And after applying this tuning parameter, we can get the source momentum flux in the AM5 model. And for our AM5 simulations, we have two groups of simulations. The first group is based on the present day simulation. It's the 2010 climatology. And the second group is the increased 4K SST simulation. And for each group, we have three sets of simulation. The first simulation, we have the fixed convective fraction. And for the second and third experiment, we have the prognostic updraft area. And we could see that from the QBO period, it gets shorter for the increased 4K SST simulations compared to the present day simulation. And the largest difference appears in the fixed convective area simulation. And for the bottom, we have like a description of the convective parameter scheme that we used in this model. It uses a finite volume cume, the sphere dynamical core, and the subgrade convection is represented by two bulk plumes for shallow and deep convection. And detailed discussion about the convection parameterization scheme can be found in Zhao et al. 2018. And here, showing the zonal mean wind averaged within 10 degrees north to south. And the panels 1, 3, and 5 are for the present day simulation. And the panels 2, 4, and 6 are for the 4K SST simulation. And you could see that this QBO signal, the period of QBO gets shorter for the future 4K SST simulation compared to a present day simulation. And the largest difference appears in the fixed convective fraction simulation. And the shortest QBO period appears in the panel B, that for the fixed convective fraction case. And the heating depth is an important parameter in the Bayer scheme. And by looking at the present day and 4K SST simulation, the dashed line are indicating the tropopause height. We could see there is an increasing of the tropopause when SST increases. And the black line is the trim observation. And by comparing to the trim observation, we have similar heating depths, except the model have more deepest heating depth cases than the observation. And another important factor in the Bayer scheme is max heating rate. The solid lines are for the present day simulation, and the dashed line are for the 4K SST simulation. The black line is the trim observation. And we could see that there is more strong convection in the when we increase the SST compared to the current climatology. And trim have larger maxi heating rate cases compared to the present day simulations. And we could notice that the maximum heating rate is positively correlated with the QBO period. When we have stronger heating, the QBO period gets shorter. And we also have this 2D PDF showing the distribution of heating depth and maxi Q. And the left panel shows the trim observation, and the red panels are for the simulation we have in the AM5 model. And from this plot, we can notice that the maximum heating rate and the heating depths are positively correlated. If you look at the yellowish color is where most cases happen. So this is a log scale plot. The yellowish color means there's more cases than the other, like the bluish color. And for prognostic convective fraction simulations, the distribution shows wider range at lower, shallower heating depths. And that means this region have wider distribution. And next, we did an offline Bayer scheme calculation looking at 100 hectopascal gravity wave zonal momentum flux phase speed spectrum. And what we see here is the 4K SST simulation show a broader phase speed spectrum and more momentum flux than the present day simulation, and this leads to a shorter QBO period. And the fixed convective area simulation shows a larger change in the phase speed and the momentum flux comparing to the prognostic convective area simulations. Here comes the summary. The number of extreme deep convection events increases with the increasing SST simulation. It leads to more gravity wave momentum flux and a broader phase speed spectrum, and thus a shorter QBO period. The prognostic convective area introduced less strengthening and broadening of the phase speed spectrum for the 4K SST simulation, and it leads to a smaller change in the QBO period compared to the fixed convective area simulation. Yeah. Thank you. I will take any questions.
In the microphone.
Is the lesser change in the 4K SST simulation for prognostic cloud fraction simulation is because are there some compensation from the increasing cloud fraction to cancel out the increase in Q naught? Were there?
Yeah, do you mean why there's a larger change in the fixed convective area case than the prognostic? Yeah, that's a good question. For the fixed case, we only use 0.1, but for the prognostic convective area, it has so for the fixed convective a fixed convective area simulation, you have larger max Q, and that's one point. And for the prognostic simulation, it doesn't, I look at the distribution of the convective area, it doesn't change a lot. So the larger change is in the heating rate.
Cloud fraction rate.
Yeah.
You again. And so in the interest of time, let's move on to the next presentation, which is a Earthworks update from Dave Randle.
Okay, you see the long list of names here. This is a joint project between CSU and NCAR. And I want to particularly call out the important contributions from Brian Dobbins, who's listed on the third line here. And I'll mention him again a little bit later. CGD generally has been very supportive. So we've been doing releases for a few years now, and we're just released 2.5. And this brings us up to date with CESM 3-0-beta 06, which means that we are we're contemporaneous with the developmental version of CESM. And this brings in a lot of optimizations that were developed for the diamond runs, which I'm going to talk about. We have in this new release better support for the MPAS ocean and sea ice, which were developed at the Los Alamos National Lab. And I'll show you some results from that here in a few minutes as well. We also have the same kind of support for finer grids. And there, it says fixes several software issues, fixes a lot of software issues, some of which are still pending. So one of them, I won't spend much time on the slide, but you know, there are various software issues with the model itself. And then there are software issues that relate to the infrastructure that we use from outside, in particular the compilers. And we've had some trouble with the NVIDIA compiler recently. And it turns out that these issues have been due partly to the way the code is written, not just in one place, but in many places throughout the model, but also partly due to issues with the NVIDIA compiler. So we've made good progress with this, but it's not completely resolved yet. We've also made quite a bit of progress with the GPU components of the model. So we have the microphysics, that's Puma/MG3, running on GPUs. We have the radiation code running on GPUs, and we have Club running on GPUs. And there's been a lot of work involved here to make this work, to make this happen. And these are now optionally available in the standard CAM as well as in Earthworks. We also have both the atmosphere and ocean dynamical cores running on GPUs. They're both MPAS, of course, MPAS atmosphere and MPAS ocean. For the atmosphere, we're only running on GPUs with simple physics, and that's only available through the Earthworks repository. The MPAS ocean GPU version will be made available in our next release, but it's running now. So we've done 1.5 diamond simulations. This is the intercomparison, the international intercomparison organized by a long list of people, including Bjorn Stevens and Masaki Sato. And here again, Brian Dobbins has been absolutely key to making this go. A lot of difficult software issues had to be overcome to make this possible. So we ran it with CAM physics with a little bit of tuning. And there were also a number of scalability fixes, which means fixes that allowed us to use a larger grid from both ESMF and PIO, which is an I/O package the model uses. And also memory usage has been reduced. So these things led to improvements in efficiency, and in fact, the code actually runs more than 2.5 times faster than we thought it was going to, because we're using longer time steps. We don't have to restart as frequently, and we are using less memory, which means we can use more cores. And further improvements are in the works. In particular, there's an issue with the land surface model, CLM. It uses a lot of memory on startup. It should be using much less, and that problem will be fixed in the coming weeks, I hope. We've also done recently a coupled simulation with the 15-kilometer grid. So the spin-up of the ocean is described here in the top part of the slide. We're following the OMIP protocol. And so we started with a 295-year spin-up on a 120-kilometer grid, driven by a data atmosphere, of course. And then 118 years on a 60-kilometer grid after interpolation. The middle part of the slide tells what was interpolated. And then down to a 30-kilometer grid, we ran 1 year there, and then to a 15-kilometer grid, 2 more months of spin-up, and then we started the model on March 1. And ran for 1 simulated year. So here's a snapshot of OLR, and this has been, this figure was produced using heel picks. This was done for the kilometer scale hackathon that happened a couple of weeks ago. Don Daslick did this figure. So the heel pick zoom level is 9, which corresponds to roughly 12 kilometers, a little bit finer than the actual simulation. And you can obviously see quite a bit of detail here. Here's an animation of the ocean circulation. This is supposed to loop, but it doesn't, at least not in PowerPoint. It looped in Keynote. So that's running fine. And here are some slides that show a particular tropical storm over the Atlantic. You can see the geometry in the bottom left panel there. You can see Africa and North America on the left. So the low in terms of sea level pressure is that little bluish green spot at about 32 degrees north and 300 east longitude in the top left panel. And then you see the wind speed, sort of bright red spot on the right there top, and then surface temperature. Here you can see the wake of the storm. So this is showing that we are in fact using a coupled model. And the OLR then is shown in the bottom right panel, and you can see a spirally shape, looks like a TC. So conclusions, we're doing real simulations now that are of the sort that we plan to do from the beginning. So I'm going to claim that we're in production mode. Doesn't mean that we're finished fixing problems and making optimizations, but we've reached the point where we can actually use the model. We've completed a Diamond 1 run for summer, and we've done part of a winter. It hasn't been finished yet. We may go back and redo it with a slightly different physics. We've also done the 1-year coupled simulation that I showed you on the 15-kilometer grid, and that was submitted to the hackathon, so a bunch of people got to play with it. And we're hoping to do a Diamond 2 simulation in the not too distant future. So that could be a 1-year run. And we're working on further code improvements and optimization. And I will say, since the beginning of this project, you know, we wrote the proposal in 2019, and I had no idea at the time how much software problems would, how much work would go into fixing them. So it's been educational for me. That is the last slide.
Dave, any questions? Thank you again, Dave. So the next presentation is going to be given by Timothy Andrews, who will be talking about linear stability of divergence and vorticity damping.
Cool, thank you. So this is work with Christiana at the University of Michigan. So I'll be looking at diffusion in dynamical cores, and specifically looking at stability on cubosphere grids. So numerical diffusion is a key part of all dynamical cores for atmospheric modeling. So it's present in the model whether it is implicit or explicit. So implicit diffusion can be from time-stepping methods or maybe your transport scheme, or you might apply it explicitly through additional terms in your equations, such as your horizontal momentum equation. So there are a couple of key features when you apply diffusion explicitly. So the first is that there is a range of stability for your coefficients. So I'll just call these C for the moment. So there are two factors to this. Firstly, if your diffusion coefficient is too small, then you can have instability because you're not damping the small scales enough. However, on the other hand, if you make your coefficient too large, you can actually introduce stability from the diffusion itself. And it's the second feature that we'll look at in this talk and do stability analysis to get some bounds for this coefficient. So firstly, just describe what divergence and vorticity damping are, what the cube sphere is, and then show some application to CAM FV3. So this is the finite volume cube sphere grid that's used within the CAM model. So explicit diffusion, so if we consider this for the horizontal momentum equations, you can apply this to your horizontal velocity through either a Laplacian term or some higher order operator, which we call a hyperviscosity. Conversely, if you look at divergence and vorticity damping, you instead apply this directly to D, your divergence, or your horizontal vorticity. And doing this means that you directly damp the divergent and vorticity modes. And a key benefit of doing it this way is you can specifically damp either the rotation or the divergence in your model. So we're looking at this on cube sphere grids. So these have been becoming ever more popular to avoid the pole problem on long lat grids. And specifically the mnemonic version of this is where you take a cube and you project lines from the faces of this cube onto the sphere. So there are three different cube sphere grids that I like to look at. So the first was the equidistant grid, where basically each of these cube faces was split into equal areas. But the issue with this is if you project it onto the sphere, you get quite a range of cell areas. So the equiangular cube square grid is probably the most common. So this is used in CAM-SE and also by the UK Met Office. And this is where you define equal areas on the sphere itself. Now there's a third grid that's actually special to FV3, and it's the default in CAM-FV3. And this is where the cells along the panel edges are made slightly more regular. And this reduces grid imprinting, which can introduce errors during transport. So just to summarize these three grids, so the equiangular one used by CAM-SE has the smallest range of cell areas. The equi-edge has a slightly larger range, but the benefit is that we have the smaller aspect ratio, if I can, and specifically more uniform cells at the panel edges. So moving forward, I'll look at the equiangular and the equi-edge grids, and recalling that equi-edge is the default for CAM-FV3. Another key point between these two grids is actually the smallest cell is in a different location. So for the equiangular grid, it's in the middle of the panel edges here, whereas for equi-edge, it's at the cell corners. And this will play into the stability of these two different grids. Okay, so let's get to some linear stability analysis. I won't show any of the derivations for the sake of time, but you can see more in our preprint. So here I'm plotting amplification factors to show the effect applying the stability, the diffusion. So here on the y-axis, we're plotting the amplification factor. So if this is between 1 and -1, we're in a stable regime. If this factor drops below -1, then we have amplification from the diffusion, and our simulation will blow up. So thankfully, if we plot the defaults for CAM-FV3 on the equi-edge grid, so these are default diffusion coefficients of 0.15, we see that we're in the stable regime for all wave numbers plotted along the x-axis. So here we go, none of these drop below -1, so the defaults in CAM are all stable. But the thing I want to highlight is then I looked at the equiangular grid, which you can switch on in CAM-FV3. And in fact, for 6th and 8th order divergence damping, the default coefficient of 0.15 is unstable. So the take-home message here is if you're playing around and want to try a different cube sphere grid, you'll need to reduce your divergence damping coefficient. Otherwise, you'll cause instability from this. The reason for this difference is that the equiangular grid has the smallest cell at the middle of the edges, and this is the place where the instability forms. And this actually leads to a stricter coefficient bound on the coefficient than on the equi-edge grid. Yeah, I won't go into more for the sake of time. So then I looked at testing these derived coefficients in CAM-FE3. So just looking at the baroclinic wave test, running this for 15 days, and basically seeing what was the largest value of divergence damping I could use before things blew up, and comparing the equiangular and equi-edge grids. So in CAM-FE3, the diffusion terms that we're interested in are shown here. So here are horizontal momentum equations. We have transport operators, which actually have some diffusion in them. We have vorticity damping terms here, and then we have divergence damping, which I'll look at first. So comparing this, the theory to practice in CAM-FE3, I found very similar values, so this was good. And as expected, equi-edge could use stronger divergence damping before blow up. And again, just reiterating that the equiangular 6th and 8th order divergence damping is unstable with the CAM default coefficient. This is, of course, because it's tuned for the equi-edge grid. Just to show that we have blow up in different locations, if you recall, for equiangular, the smallest cell is at the middle of panel edges, and for equi-edge, it's at the middle of the corners. And if we run baroclinic wave simulations with unstable values and plot vertical velocity, we can see different locations for blow up. And as expected on the equi-edge grid, is at these panel corners, and for the equiangular grid, it's at the center of these panel edges. And this is a value just above the stability range to just show that, again, if you are slightly over this, you will cause a blow up of your simulation. So something to be aware of if you're playing around with diffusion. So just briefly go over vorticity damping. So something interesting in CAM-FE3 is that the transport operators already diffuse vorticity. And so this means that your explicit diffusion is applied on top of this implicit diffusion. And so you can't nearly have as large values as you can for divergence damping. And we saw this in playing around with some results. And in this case, we got that you could only apply about half the theoretical value of vorticity damping before you got blow up. And so the rest of that was from implicit diffusion of the vorticity. I found interestingly that a higher order of vorticity damping actually meant I couldn't make the coefficient as large. Okay, sorry, no, the other way around. Sorry, I could apply a larger coefficient with a higher order, which is counterintuitive from linear stability theory, something I still need to look at. And the last point is that I applied a number of different transport schemes. So we have monotonic ones, which is we have more constraints and are generally more diffusive, and unlimited schemes with fewer constraints. And there were different levels of vorticity damping I could apply before blow up. And my theory from this is that we can actually back estimate the amount of implicit diffusion in the transport scheme by seeing how much vorticity damping we can use, because there's that play between the implicit and the explicit vorticity damping. So this is something I want to look at further. Okay, just to summarize, so I looked at divergence and vorticity damping on the cube sphere, derived some coefficients, upper bounds to the coefficient, found that on the equi-edge grid, which is the default in CAM-FE3, you can use stronger divergence damping than equiangular. And that remember the CAM-FE3 defaults are unstable for equiangular if you're wanting to play around with that. There were different locations of blow up for the two different grids, corresponding to the different locations of the smaller cell area. And with vorticity damping, there are differences depending on your transport scheme, and my theory is that this can provide some intuition around the level of implicit diffusion of that scheme. Thank you, and I'll take any questions.
Any questions for Timothy? If so, please come to the microphone.
Were you using the same time step for all of the simulations you did? Because it seems like that could be an issue as well.
Yeah, that's right. I fixed the time step. And in fact, the diffusion coefficients scale with the times as well.
Okay, thank you again, Timothy. Let's move on to the next presentation. The title is Deep Atmosphere Dynamics in Aquaplanets and E3SM CESM Intercomparison by Owens Hughes.
All right, just as a preamble, there's a bunch of model development work that I don't have time to get into here. I love talking about that offline, and if you'd like to talk about it, I'm always down. So, without further ado, the Intertropical Convergence Zone, or ITCZ, is among the features of equatorial climatology, including like the Madden-Julian oscillation, that have had long-standing biases in Earth system model simulations. And the work that I'm talking about today originated in the Department of Energy's E3SM atmosphere model, where in the second version of their model, they introduced a new version of the dynamical core. The dynamical core solves the resolved fluid motion. And this new version of their dynamical core solves the non-hydrostatic equations of motion and is more suitable for high-resolution simulations. The non-hydrostatic home dynamical core, it's sort of a sister die core to CAM-SE, and it's being reintroduced into CAM and CESM as part of the storm speed project. So what I'm talking about today is basically results from E3SM and CESM. So you can ask, do higher resolution simulations resolve the ITCC bias? If you simulate with a non-hydrostatic dicore, does it fix it automatically? And what I'm showing here is essentially no. So what I'm showing is 10-year average summer precipitation with a 28-kilometer grid spacing on the, let's see here. So on the left, this is with a hydrostatic dynamical core. On the in the center, that's a non-hydrostatic dynamical core, and on the right, that's a reanalysis product. So what you can see is the precipitation biases are very similar with hydrostatic and non-hydrostatic dynamical core, and so you don't get this for free. But removing 2 additional problematic approximations from the dynamical core are likely going to improve CESM and E3SM's equatorial climatology. So I'll talk about those now. The first one is the shallow atmosphere approximation. Assume that the distance between the center of the Earth and a point in the atmosphere is equal to some nominal value, 6,371 kilometers, for example. And as a consequence, you assume that gravity is constant throughout the atmosphere. But when you make this choice, you also have to make a couple of other things to make angular momentum transport work out. So the metric terms you need to keep a parcel that's not moving radially along a surface changes, and you have to discard those. And basically a parcel moving vertically in the atmosphere, if you're assuming that that radius is constant, the angular momentum looks different if you make that assumption versus not. And so these last 2 metric terms and Coriolis terms are called the traditional approximation. And if you discard the Coriolis terms in the traditional approximation, you end up those are called the non-traditional Coriolis terms. So these 2 approximations are treated as a package deal to maintain angular conservation of angular momentum. So these are what the equations end up looking like, and I can talk about them offline if you'd like. But these 2 approximations are justified for large-scale motion in the mid-latitudes, but in the presence of convective motion near the equator, can we still discard these non-traditional Coriolis terms? Ideally, studies indicate no. For example, Hengong's work, who will be speaking after me. And what I want to talk about today are preliminary results from the Deep Atmosphere Home, or SE non-hydrostatic dynamical core in aquaplanets. So we wanted to implement the changes to the die core in the simplest way possible. Home and SE share horizontal numerics, and we wanted to not violate the conservation properties. So we made this list of changes. The main change here is that it's harder to do in a mass-based coordinate model. And I can talk about those details offline. But right now I want to talk about some CESM QPC6 results produced via the storm speed code base. So this is the home or SENH dynamical core with CAM physics. So Aquaplanet simulations, remember that you take full complexity atmospheric physics, in our case CAM6, and an idealized ocean, which is a data ocean, no landmass, no topography, no seasonal cycle, idealized sea surface temperature pattern. We're using the control on the right here. And what I want to show is we have an approximate, so on the, let me see here. On the left here, we have the time mean zonal wind in the deep atmosphere model, so this is our new version. Then in the center, it's the time mean zonal wind in the old non-hydrostatic SE. And then on the right, we have the difference. And so this is the difference of the more physically accurate model minus the less physically accurate model. And what we see is basically there is a 2 meter per second bias on top of a 20 meter per second base wind. So by making these approximations, you get a 10% relative error in your zonal wind climatology. The changes are, you see changes of approximately equal magnitude outside of the tropics. So the linear theory and idealized studies give you a good idea of why the biases in the tropics are happening. Extending this to the mid-latitudes and the poles is going to be a matter of further work. So to return to the ITCZ problem, the QPC6 defaultly shows a double ITCZ, which you can see here in terms of these double off equator peaks. And what you see is that when we introduce the new dynamics, there is more off equator precipitation in the new model than in the old model. And so it actually sort of makes the ITCZ slightly worse, which is opposite to the results that Heng-Ong is going to show with a different die core. So there's something pretty interesting going on here. I made sure, I forced it so that the model would crash if I accidentally ran the shallow case with deep atmosphere dynamics. So I'm sure that I've got the right model here, but more work is needed to say why this is. One other thing. Changing gears a little bit, there is a paper from 2005 indicating that the traditional approximation biases tropical cyclone tracks and precipitation patterns. And so an additional simulation I performed was Reed and Jablonowski designed an idealized tropical cyclone initial conditions, and I ran those with aquaplanet physics in quarter-degree grid spacing. And what you find if you run this for 10 days is that the position of the pressure minimum, here I'm showing wind speed, but you can see that the longitudinal axes ranges are the same. And there's about a 2-degree difference in the center of the measured idealized tropical cyclone. And the only difference between these two simulations is the deep atmosphere dynamics. So to compare this to E3SM, we return to the aquaplanet. We've still got a difference in precipitation. So this is time mean precipitation on the left here, deep atmosphere minus shallow atmosphere. And then what you find is that you have a little bit more precipitation around the equator, but it essentially disappears in a zonal average. The physics package that I'm using here is EAM-V1 with an E3SM, so that doesn't exhibit a double ITCZ. You have similar changes in the zonal wind structure, the sort of 10% relative bias that you would expect from linear theory within E3SM. And hang on, we'll talk more about the reasons behind that in a minute. An interesting result here is that running with a slightly higher model top means that we have 10 meter per second bias in the stratosphere of E3SM. And the reasons for that change aren't super well studied. And further, our immediate future work is going to be looking more at why this is happening. Sort of get these this change in the position of winds with a similar magnitude. So, in summary, we designed a deep atmosphere version of the home dynamical core for E3SM, and we're porting this version into the CAM Storm Speed code base this summer, which will be available to people. And we're starting to look at the systematic biases induced by the shallow atmosphere and traditional approximations in a hierarchy of models. So what we've seen so far is that systematic biases are not just located in the equatorial troposphere. There are stratospheric biases and mid-latitude biases induced by these approximations. And further work is going to be needed to look at, go beyond aquaplanets to AMIP-style simulations, and we're also going to be running some global convection permitting simulations with a 3-kilometer nominal grid spacing this summer to quantitatively look at it on weather timescales. So with that, I will take any questions.
Thank you. So any questions for Owen? So if not, then let's move on to the next presentation. Hing Ong will be talking about mitigation of the double ITCZ bias by inclusion of the non-traditional Coriolis terms.
Hi. Many thanks to, first of all, and many thanks to NCAR CGD for the travel support. Otherwise, I won't be able to be here. And many thanks to my collaborators, Adam Harrington and Dayang. I borrowed the computational resources from him. And first of all, echoing Owens' presentation, the double ITCZ bias has been a problem in generations of our system models and has been studied for decades, as shown here. This is a paper from 1995, and this project this year. And again, talk about non-traditional Coriolis terms. Most of the global atmospheric models share this common approximation of the traditional shallow atmosphere approximation, which neglects the non-traditional Coriolis terms. And non-traditional Coriolis terms arise from planetary rotation. They turn eastward motion upward and upward motion westward, and vice versa. And from my PhD work, I used this idealized model to study using prescribed heating due to convection and study the flow response to that heating. And I found that omitting the non-traditional Coriolis terms yields a westerly wind bias in an ITCZ-like heating region. And then let's think of what if this westerly wind bias extends into the boundary layer? What happens after that? Well, there would be an enhanced cyclonic vorticity in the off-equatorial region and reduced cyclonic vorticity when we neglect the non-traditional Coriolis term because of vorticity tilting. If we neglect that vorticity tilting, it will have this. So we hypothesize that if we neglect non-traditional Coriolis terms, there will be reduced equatorial precipitation because of that lacking vorticity tilting, which leads to a change in Ekman pumping in the boundary layer. And this is, I first used aquaplanet simulations and switch on and off the non-traditional Coriolis terms in them, and of course considering all the conservations details that Owen just mentioned. And here's the result. This is precipitation climatology with the non-traditional Coriolis term. And this is the difference between them. This is the big difference of precipitation due to neglecting the non-traditional Coriolis term. And as you can see, there is a reduction of precipitation at the equator, and there is an enhanced precipitation in the off-equatorial tropics. And that looks like a double ITCZ, which sounds like double ITCZ may be related to this enhanced off-equatorial precipitation due to neglecting the non-traditional Coriolis terms. And the origin of that as I just mentioned, it's related to extension of that westerly wind bias due to neglecting the non-traditional Coriolis term into the boundary layer, which changes the Ekman pumping, and then change it. This figure is showing the difference in zonal wind, and this is showing the stream function difference, which transitioning from red to blue in this figure means there is a subsidence at the equator due to neglecting the non-traditional Coriolis terms. So the aquaplanet conclusion is that on the polar side of the ITCZ, when we neglect the non-traditional Coriolis terms, it has enhanced cyclonic vorticity and enhanced Ekman pumping, and thus enhanced precipitation in the off-equatorial, on the polar side of the ITCZ. And the opposite is true on the equatorial side of the ITCZ. Then what we just show is aquaplanet, but it's hard to evaluate because we don't have a real aquaplanet. So next step is AMIP. We want to evaluate our results against observations. So this is the precipitation anomaly observed. And I created this Pacific Equatorial Precipitation Index to study whether the precipitation is concentrated at the equator or distributed into off-equatorial region. And the larger this index, the more distributed the precipitation is to the off-equatorial region. In the observation, this index is 0.24. And this is my, again, precipitation climatology without the non-traditional Coriolis terms. And this index increased to 0.29, which means that the precipitation is more distributed to the off-equatorial tropics when we turn off the non-traditional Coriolis terms. And this is from the simulation with the non-traditional Coriolis terms. And we see that this PEPI index is in between. I mean, it's getting closer to the observation, which means that the inclusion of the non-traditional Coriolis terms leads to a substantial improvement in this index. And we also look at this index in different months, and in most of the months, the inclusion of the non-traditional Coriolis term improves that index, improves the representation of precipitation, whether in terms of whether it is distributed or concentrated toward the equator. And when we look at the zonal mean, first of all, this is showing only results over the Pacific Ocean. And we see that neglecting the non-traditional Coriolis term tends to distribute. If you look at the red dots, which means without non-traditional Coriolis term, and compare that with the blue dashed line, which is with non-traditional Coriolis term, and then compare those with the black line, which is observation, you see that the blue dashed curves are closer to the observation, which means that we are improving the precipitation by including the non-traditional Coriolis terms. And this is zonal mean. Again, we see similar features if we neglect the non-traditional Coriolis term, as we see here in the red dotted line, the precipitation reduces at the equator. And let's see whether it is due to the same reason. We've shown that how non-traditional Coriolis terms influence the zonal wind and the meridional circulation in the aquaplanet simulations. And then if we compare that with our AMIP simulations, which is more realistic, we still see similar features, which showing zonal wind is changed. There's a westerly wind bias due to neglecting the non-traditional Coriolis term over the ITCZ region, and also a subsidence at the equator, showing in both our AMIP simulation and aquaplanet simulations. So here's the conclusion. The climate models have suffered from the double ITCZ bias for decades, and climate models have neglected non-traditional Coriolis terms for decades, with only a few exceptions. And this study suggests that neglecting the non-traditional Coriolis terms tends to distribute the precipitation to the off-equatorial tropics in the aquaplanet and AMIP simulations. And this is due to enhanced Ackermann pumping on the equatorial side, no, the polar side of the ITCZ. And that concludes my talk. Thank you.
Thank you. Any questions?
Wondering whether you've looked at something like latent heat flux, because you've kind of, all things being equal, you know, your expectations are what you said, but of course if you're changing the surface winds, you're changing the latent heat flux, and then the cycle kind of adjusts potentially.
You mean latent heat flux?
Surface latent heat flux.
Surface latent heat flux. Yes, I also see improvement in that regard. So I compare the, latent heat flux. No, actually, I haven't looked at the latent heat flux. I've looked at radiation flux at top of atmosphere and the surface radiation flux, and both also shown improvement when we include the non-traditional Coriolis terms. I look at pattern correlation and RMSE. All those improved when we include the non-traditional Coriolis term.
So if I understand correctly, for your AMAP simulations, there was a marginal improvement in the precipitation, right?
Yes.
So do you think that's not the, exclusion of these entities is not the primary reason for the ICTZ bias?
Maybe not the primary reason, but at least I found that inclusion of the non-traditional Coriolis term can kind of reduce the bias.
For the AMIP-specific simulations, the difference plots look like there were places where maybe the statistical significance of the difference might be in question. Do you plan to run any ensemble stuff to check for statistical significance?
That's a good question. If I have the resources, yes, and if you want to also work on that, we should work on this together.
Nice talk. So with the marginal change of precipitation with the non-traditional Coriolis force and without, I mean, how much resources you need to run the model with NCT compared to the without NCT?
Good question. There's no difference in computational resource needed when we include non-traditional Coriolis terms. It's including doesn't increase the expense.
Okay, thank you.
These non-traditional terms will be more important at higher resolution since vertical velocity is bigger. I mean, I don't know if there's an area average that you need to account for, but
currently I can only make guesses. Actually, previous studies by Matt Eigel at UC Davis found that including the non-traditional Coriolis term into cloud resolving models also make a difference. And currently I'm using 1 degree resolution, which means most of the precipitation are coming from convection parameterization. And since there is a difference in cloud resolving model due to the inclusion of non-traditional Coriolis term, which may not be represented using convective parameterization, then yes, I would expect if we use higher resolution, it will make a larger difference because of those previous studies. But this needs to be verified.
Any further questions? So if not, then let's thank our speaker again and all the speakers for this session. We have a little bit of time for discussions. As he thinks we are just done. Well, a lot of talks today. Then I already saw some from other working groups. So see you tomorrow then.